The Big Bang wasn't a beginning. It was an eraser scrubbing the universe so clean we weren't supposed to find fingerprints underneath. But the cosmos doesn't look blank. It looks like it remembers. Patterns in the sky, impossible smoothness whispering in the oldest light. So what if before isn't a time at all? And what terrifying thing did our universe survive to get here? There is a limit to what the human mind can picture, and cosmology has learned to aim directly at it. What we call the beginning may be only the first scene we can reconstruct, not the first scene that occurred. The question is not merely what preceded a cosmic fireball, but whether precedence itself survives at extreme scales. Physics can draw a straight line from today's galaxies back to a fraction of a second. Then the line hits a seam, and our language goes thin. In that seam, cause and effect can trade places, and nothing can become a technical word with sharp edges. 7 theories try to cross that seam without pretending it is easy. Some begin with a prior cosmos fading into ours, leaving only subtle debts in the oldest signals we can measure. Others begin with emptiness, not as philosophy, but as a quantum state that refuses to stay empty. Some treat our universe as one event in an endless production line where creation is common and meaning is scarce. One turns the Big Bang into aftermath, an impact between vast domains, where a collision can look like a birth from the inside. So we begin at the boundary where our best models hesitate, and we push carefully into what they permit. If the universe truly has no before, then the question changes us more than it changes the cosmos. And if there was something anything, then whatever it was did not merely precede our universe. It defined the rules by which universes can begin. Across 7 chapters, we move from dying predecessor worlds to quantum emptiness, multiverse machinery, brain impacts, timeless cosmologies, block time, and pure mathematics. Each step tightens the same question until before it becomes either a discoverable structure or a word that finally breaks. The Big Bang sits in our textbooks like a first page, but our equations treat it like a wall. When we run the cosmic story backward, the math does not reveal a clean origin. It reveals a boundary where our best descriptions stop working, as if the universe turns into a question mark right at the moment we most need an answer. That boundary matters because it shapes what we think existence is allowed to do. If the Big Bang is only the edge of reliable physics, then beginning becomes a claim, not a measurement. The central question returns with sharper teeth because language itself starts to wobble. Did anything exist before the Big Bang? And if time began there, what could before even mean? Cosmology is not built on pure speculation, so we start with anchors that can be checked. The cosmic microwave background is the universe's afterglow, released when atoms first formed and light finally traveled freely. In physical terms, it is a faint, nearly uniform glow across the whole sky. Microwaves stretched by expansion into a cold bath sitting at about 2.7 Kelvin today. Large-scale structure maps how matter clumped into galaxies and voids over billions of years, tracing a cosmic web of filaments and empty bubbles that spans the observable universe. Primordial element abundances predicted by Big Bang nucleosynthesis record the first minutes when protons and neutrons assembled into helium and traces of lithium. Each pillar is a different kind of evidence, and they converge on the same early conditions with a consistency that is genuinely remarkable. The cosmic microwave background tells us the universe was once hot enough to keep electrons and nuclei apart, forming a plasma that scattered light. When the cosmos cooled to roughly a few thousand Kelvin, electrons settled into atoms and photons decoupled, free at last to travel without constantly bouncing off charged particles. Those photons have been traveling ever since, their wavelengths stretched by the expansion into the microwave band we detect today. Large-scale structure adds a slower, heavier record, because gravity amplifies small density differences into clusters and superclusters over billions of years. The element abundances add a clock because nuclear reaction rates depend sensitively on temperature and density, and matching the observed ratios of hydrogen, helium, and lithium requires conditions that fit the hot Big Bang picture with precision. These 3 pillars tell a consistent story of a hot, dense, early phase. They do not directly show a first moment, only an early one that is already underway. They also hint that the universe began in an unusually smooth state with tiny fluctuations that later grew. That smoothness is part of the unease because it looks tuned for a long future. In the cosmic microwave background, the temperature varies by only tens of microkelvin across the sky, a whisper of difference on top of near-perfect uniformity. Those variations are not noise in the ordinary sense because they encode primordial density variations. They are the seeds of everything that later becomes dramatic: galaxies, stars, and the chemistry of life. Yet the overall uniformity is so striking that it raises a deeper puzzle. Why should regions of space that appear causally disconnected look so similar in temperature and density? When we push general relativity all the way back, it predicts a singularity at t equals 0. Density and curvature shoot to infinity, and the equations lose predictive power. In practice, the curvature scalars that describe spacetime's bending diverge, and the notion of a smooth geometry collapses. A singularity is not a place we can visit with instruments or even with consistent mathematics. It is a warning light that the theory is being asked to do something it cannot. Historically, this was not just a philosophical discomfort, because it emerged from the same equations that correctly predicted black holes and gravitational waves. The Hawking-Penrose singularity theorems sharpen the problem, showing that under broad conditions singularities are not rare quirks. They are generic outcomes of gravitational collapse, and in standard cosmology, of extrapolating expansion backward. That does not prove the universe began at a singular point, because the theorems assume classical spacetime. They show instead that classical spacetime cannot be the whole story, so the Big Bang in this view is not a proven birth event. It is the point where a successful theory breaks, and where new physics must take over quietly but decisively. The terrifying possibility is simple, and it changes the emotional temperature of the question. If the breakdown is only a limit of our model, then the universe might extend past it. One family of ideas answers by refusing a true beginning while keeping the early hot phase we observe. Cyclic cosmologies imagine a universe that expands, then contracts, then rebounds into another expansion. The Big Bang becomes a bounce, not a creation, and the first universe disappears. In its place is an endless sequence of cosmic eras, each one inheriting something from the last. Classical oscillatory models were once the simplest version of this intuition. Gravity pulls everything back. The cosmos crunches, then somehow restarts. But classical cycles face hard problems, especially entropy, which in plain language is the tendency for usable order to degrade. Each cycle tends to accumulate disorder, making later cycles larger and longer, and making a past eternal sequence difficult to sustain. Even the radiation left over from previous cycles becomes a burden because it changes the dynamics of the next contraction and pushes the model toward instability rather than graceful recycling. Modern cyclic thinking shifts the mechanism away from a purely classical crunch. It asks whether quantum gravity changes the rules at extreme density, where spacetime itself may become granular. In that regime, collapse might not end in a singularity. It might trigger a rebound because the geometry cannot compress indefinitely the way matter resists being squeezed beyond certain quantum limits. The classical picture of infinite density is replaced by a quantum picture of maximum density, where the equations remain well behaved and the story can continue. Loop quantum cosmology offers a concrete example in accessible terms. It applies ideas from loop quantum gravity to the universe as a whole, treating spacetime geometry as quantized. Instead of a smooth continuum that can shrink without limit, space has discrete units that resist being squeezed beyond a minimum scale. At ordinary densities, general relativity is recovered, so the model agrees with what we already test. The novelty appears only when curvature becomes so extreme that the granularity can no longer be ignored. Near the would-be singularity, the quantized geometry produces an effective repulsive contribution. Gravity still attracts, but the quantum structure pushes back when density approaches a critical value. The result is a bounce that replaces infinite curvature with a finite maximum, and the equations remain well defined across the transition. Time can extend through the bounce, making our expanding universe the aftermath of a previous contracting phase. If that happened, the next question is what survives the reset. A bounce is not automatically a clean slate, and physics rarely forgets everything. Entropy is the first complication because a prior universe would have generated enormous disorder through star formation, nuclear burning, and black hole growth. Some bounce models try to dilute entropy through vast expansion phases or relocate it into degrees of freedom that do not reheat our observable patch. Others rely on the idea that what we call our universe may be a limited region, not the whole global spacetime. Even if most details are erased, subtle traces could carry over. And those traces would be the scientific prize. Leftover anisotropies might bias the early expansion, leaving preferred directions or unusual alignments in the sky. Background of primordial gravitational waves could pass through the bounce more easily than matter because gravitational waves interact weakly and do not thermalize easily. Tiny imprints might remain in the cosmic microwave background as non-standard correlations, or in the distribution of large-scale structure as unexpected patterns. The challenge is that these signals would be faint, and faint signals are where false positives love to hide. This is where the central mystery becomes a testable tension. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? The cosmic microwave background is not just a baby picture. It is also a forensic surface where minute temperature variations encode earlier dynamics, acoustic oscillations, gravitational potentials, and the subtle hand of expansion. The variations can be thought of as ripples frozen into light, sound waves turned into a map of temperature differences across the sky. The peaks and troughs in the CMB power spectrum are not decorative statistics because they reflect real physics. They record how pressure and gravity competed in the primordial plasma, setting a characteristic scale. Any pre-Big Bang influence would have to thread its way through that well-measured pattern without breaking what already matches observations so precisely. Another radical proposal reaches the same conclusion by a different route. Roger Penrose's conformal cyclic cosmology argues that the far future of our universe can be mathematically reshaped into a new Big Bang. In the remote future, after stars die and black holes evaporate, the universe could be dominated by radiation and extremely dilute energy. In that limit, the distinction between large and small scales can blur under conformal transformations. The end becomes, in a precise mathematical sense, compatible with a new beginning. Conformal cyclic cosmology hinges on a strange kind of forgetting, and it is easy to misunderstand without a concrete picture. Massive particles define clocks and rulers, but if mass effectively disappears from the relevant description, only light-like behavior matters. Without mass scales, the universe can be stretched or shrunk without changing the physics of those massless degrees of freedom. Penrose suggests that the cold, empty end of one eon becomes conformally equivalent to the hot, dense beginning of the next. The universe in this view is not recycled by force but by symmetry. The transition is less like a collision and more like a change of coordinates, an elegant, unsettling relabeling. In that picture, our Big Bang is not a bounce from contraction. It is a redescription of an exhausted cosmos whose remaining content behaves like radiation. The previous universe ends not with a crunch, but with a long fade into near featurelessness. The last dying light becomes, after a mathematical rescaling, the first light of a new era. The process is not driven by a catastrophic event. It is driven by the internal logic of conformal geometry applied to a universe that has run out of massive structure. Conformal cyclic cosmology also makes claims about possible observational signatures. Penrose and collaborators have argued that events in a previous eon, like supermassive black hole encounters, could leave circular features in the cosmic microwave background. These are described as low-variance circles, regions where temperature fluctuations are unusually uniform. The idea is that violent bursts of energy could propagate through the conformal boundary and seed subtle patterns. If true, the sky would contain scars from a time that is not supposed to be ours, from an era that our cosmological models say cannot leave a message. The controversy is immediate and technical, and it matters for credibility. The cosmic microwave background is noisy, and random fields naturally contain circles of many kinds. Statistical significance depends on how you search, how many patterns you allow, and how you correct for selection effects. Foregrounds from our galaxy, instrument systematics, and data processing choices can mimic or erase delicate signals. Even the act of masking the Milky Way can create artifacts because removing data changes what patterns look rare. So the tension is not only philosophical. It is methodological because extraordinary claims live or die on careful inference. If we claim the universe has memory, we must show that the memory is not a mirage produced by our own pattern hunting. The same human instinct that finds faces in clouds can also find circles in cosmic noise, unless the statistics are ruthless. Still, the unsettling narrative remains because the alternatives are not easily dismissed. A previous cosmos could have ended in heat death, stretched thin until only cold radiation remained. It could have ended in a crunch, collapsing into a state where quantum geometry forced a rebound. Or it could have ended in something stranger, where the meaning of time and scale dissolved before any final moment arrived. Each ending is a different answer to what it means for the universe to finish. Each ending changes what before means in a slightly different way. In a bounce, time continues through the high-density bridge, so before is earlier in the same temporal sequence, just separated by an extreme event. In conformal cyclic cosmology, before is a prior eon connected by conformal equivalence, where the usual measures of time and size lose their authority. In both cases, the Big Bang stops being a first cause and becomes a transition. The beginning becomes a boundary condition, not a metaphysical starting gun, and the emotional weight of origin shifts away from drama toward inheritance. We return to the evidence we trust because mystery without anchors becomes fantasy. The cosmic microwave background, large-scale structure, and primordial elements confirm an early hot phase, but they do not certify an absolute beginning. The singularity problem tells us our main theory breaks exactly where we most want certainty. Cyclic and conformal models exploit that gap, offering ways the universe could be older than its oldest light. They do not overthrow the Big Bang's successes, but they reinterpret what the Big Bang signifies. If we are living in the ashes of something else, then our origin story changes from creation to inheritance. The first moments of our universe might be shaped by conditions we did not generate, like a melody that begins mid-phrase. That is the terrifying twist, because it implies our cosmos may carry debts from an earlier one. Our universe could be a sequel, and the prologue might still be written into the sky, encoded in correlations we have not fully learned to read. Now the question tightens into a final practical edge. If a previous universe existed, what was it made of at the end? Was it matter, radiation, dark energy, or something closer to nothing? And if it was almost nothing, what does it mean for nothing to still have enough structure to become everything we see? Chapter 1 left us at a boundary where classical spacetime stops giving answers and where our familiar intuitions begin to slip. Now the question tightens into a final practical edge. If the prior state was almost nothing, what does nothing mean in physics? The central question returns with a trap built into its grammar because the words themselves smuggle in a timeline. Did anything exist before the Big Bang? And if time began there, what could before even mean? In standard cosmology, time is part of the universe's geometry, not an external stage where events line up. When cosmologists say the Big Bang, they do not mean an explosion into pre-existing emptiness like shrapnel into a room. They mean the earliest hot dense phase our equations can reliably describe, traced back to a limit where densities and curvatures become extreme. At that limit, the coordinate we call time may lose its usual meaning, because the geometry that defines it is itself in question. If the Big Bang is the first moment of time, then asking what happened earlier may be like asking what is north of the North Pole. The metaphor is useful because it highlights a category mistake, not because the universe is literally a globe. North is defined on the surface, and it fails at the pole because the coordinate system runs out. Yet our minds demand causes because causes feel older than effects, and the demand is stubbornly human. We imagine a chain that must extend backward, even if the chain includes time itself. That tension is not a poetic problem. It is a technical one because theories of origin must define the parameter that counts as time. In general relativity, time is not a universal metronome ticking outside the cosmos. It is woven into spacetime, and different observers can slice that spacetime into nows in different ways. Near a singularity, those slices can become ill-behaved, and the very notion of a global clock can break. So the question, what happened before, becomes two questions that sound similar but are not. First, did the universe have an earlier phase described by some deeper theory? Second, is there any meaningful earlier at all once time is no longer fundamental? Physicists use the word nothing in several different ways, and the differences matter more than the drama. The first meaning is empty space, a classical vacuum with no matter present, like a perfectly cleared stage. The second meaning is no particles, but quantum fields still exist everywhere, even when detectors are quiet. The third meaning is no classical spacetime at all, where geometry is not yet a smooth continuum. The fourth meaning is philosophical nothing, no laws, no fields, no mathematics, no possibilities. Most scientific creation from nothing proposals use the third meaning, not the fourth, and that distinction is the hinge. They aim for no classical spacetime, but they still rely on quantum rules that assign amplitudes and probabilities. They still assume a framework where something like a wave function can be written down, even if it is only formal. The hidden issue is that the word nothing becomes a placeholder for assumptions we do not name. To see why, we have to clarify the quantum vacuum in plain terms without turning it into mysticism. In quantum field theory, fields are fundamental, and particles are excitations of those fields, like quantized ripples. A vacuum is the lowest energy state of the fields, not the absence of the fields. Even with no particles present, the fields cannot be perfectly still because perfectly still would require forbidden precision. The uncertainty principle is the simplest doorway into this idea, and it is not about measurement clumsiness. It is a structural feature of quantum theory encoded in the non-commuting nature of certain variables. It limits how precisely certain pairs of quantities can be fixed at once, such as field amplitude and its conjugate momentum. For fields, that means the vacuum has unavoidable fluctuations around its minimum energy configuration. These fluctuations are not tiny classical waves traveling through space. They are probabilistic variations in field values that appear in calculations and in measurable effects. The vacuum has structure because quantum fields have modes, correlations, and a ground state energy that cannot simply be set to zero everywhere. That structure shows up in phenomena like the Casimir effect, where boundaries change the vacuum energy and produce a force. Two uncharged metal plates placed micrometers apart feel a tiny attraction because the allowed field modes between them differ from those outside. The Casimir force is small, but it is conceptually loud because it turns nothing into something that can push. Empty space in this sense behaves like a medium with rules, even when it carries no classical matter. This is where the opening hook gains a sharper edge because it reframes the universe's earliest fingerprints. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? Some of that memory could be the imprint of vacuum fluctuations stretched to cosmic scales, preserved like faint grain in a photograph. When we look at the cosmic microwave background, we do not see a perfectly smooth glow. We see a nearly uniform temperature with tiny variations, 1 part in 100,000, mapped across the sky. Those variations are not noise. They are the seeds of later structure. And in many models, they originate as quantum fluctuations that the early universe amplified into macroscopic density differences. The idea is counterintuitive, but the mechanism is concrete. Expansion can take a fluctuation that begins smaller than an atomic nucleus and stretch it until it spans light years, then millions of light years. Inflation enters here as context because it is our best developed amplifier, and it is built to answer specific puzzles. Inflation proposes a brief era of extremely rapid expansion in the early universe driven by a high-energy state with negative pressure. In simple terms, space itself expands so quickly that regions once close become causally separated. It explains why distant regions look similar in temperature, solving the horizon problem, because they were once in contact before inflation blew them apart. It also drives the universe toward spatial flatness, addressing the flatness problem, because rapid expansion dilutes curvature the way a balloon's surface looks flatter as it grows. Inflation also offers a mechanism for the seeds of galaxies, and it does so with calculable statistics. Quantum fluctuations in the inflatoned field are stretched by expansion and become density perturbations, which later grow under gravity into the cosmic web we map today. This is not a vague story, because the predicted spectrum is close to what the cosmic microwave background measures. The spectrum is nearly scale invariant, meaning fluctuations have almost the same strength across a wide range of sizes, with a slight tilt. That tilt, measured by missions like WMAP and Planck, is one of inflation's strongest empirical successes. The CMB also shows the fluctuations are close to Gaussian, a signature consistent with simple quantum origins. These two features together constitute a fingerprint, and it matches what simple inflation models naturally produce. But inflation does not automatically answer the origin question, and this is where the story tightens again. Most inflation models require a pre-existing field, a potential energy landscape, and an initial patch where inflation can begin. They require a state that is already something, even if it is simple. Inflation explains how a small region becomes our observable universe, not why there is a region at all. It tells us how the universe evolves once inflation starts, but it does not by itself tell us why the inflaton existed or why its initial conditions were suitable. The beginning of inflation becomes a new boundary, and the old question reappears there. So the Big Bang in this view is not a proven birth event. It is the point where we switch descriptions from unknown initial conditions to a hot expanding phase. If we want from nothing, we need a proposal that does not assume classical time before the beginning, and that is a high bar. One famous attempt is Alexander Vilenkin's tunneling proposal, which treats the universe as a quantum system rather than a classical object. It suggests the universe could nucleate by quantum tunneling from nothing. Here, nothing means no classical spacetime, not an empty room waiting to be filled. The proposal treats the universe itself as having a wave function. Tunneling is a quantum process where a system crosses a barrier it cannot cross classically. A simple analogy is a particle that appears on the other side of a hill without climbing over it because the wave function spreads. In quantum mechanics, the wave function can have amplitude on both sides of a barrier. The barrier suppresses the probability, but it does not make it exactly zero, and that not zero is the crack in the classical wall. In atomic physics, tunneling explains phenomena like alpha decay, where particles escape a nucleus despite insufficient classical energy. In cosmology, the object that tunnels is not a particle in space. It is the universe's configuration. In Vilenkin's picture, the barrier is not a wall in space. It is a barrier in the space of possible geometries and sizes of the universe, a landscape of configurations. The universe begins as a tiny closed geometry, then tunnels into a state where it can expand. After nucleation, inflation can take over and blow that tiny beginning into a vast cosmos. This proposal shifts the meaning of cause in a specific way. It suggests that existence can be a quantum event, not a classical trigger pulled by something outside. It replaces a creator-like push with a probability amplitude. It makes the beginning less like an explosion and more like a spontaneous transition. But the proposal still carries hidden structure, and the structure matters because it is doing the explanatory work. It assumes quantum mechanics applies to the whole universe even when there is no external observer. It assumes a notion of a wave function and a rule for calculating probabilities. It assumes a mathematical space where nothing and something are neighboring configurations. That last assumption is subtle because it means we are already inside a framework where possibilities exist. The nothing is not the absence of all description. It is a boundary condition in a theory defined by the theory's own language, and that language is not nothing. A second major attempt is the Hartle-Hawking no-boundary proposal, which aims to remove the sharp edge altogether. It does not picture a universe tunneling from nothing into time. It pictures the beginning as a region where time behaves like a spatial dimension. The universe is finite but unbounded, like the surface of Earth. The Earth analogy is about edges, not about size, and it is worth lingering on the geometry. On a sphere, you can travel without hitting a boundary. Even though the surface area is finite, there is no special cliff where the surface ends. Hartle and Hawking suggest the early universe is like that in time, where the past direction smoothly closes. To ground this, we need one technical distinction stated carefully, because it is easy to misunderstand. Lorentzian time is the time of everyday physics with one time dimension, and a signature that distinguishes time from space. Euclidean time is obtained by a mathematical rotation that makes time behave like another spatial coordinate, smoothing certain infinities. In many quantum gravity calculations, Euclidean geometries make path integrals better behaved because oscillatory phases become decaying exponentials. This is a mathematical move, but it has physical implications for which histories contribute most. The no-boundary idea uses a Euclidean region near what we call the beginning, where the geometry is regular and closed. In that region, the geometry has no boundary in the past direction, because the time coordinate becomes like latitude on a sphere. Then, as the universe grows, the description transitions into Lorentzian time, where time behaves normally and expansion proceeds. The transition is not a switch you could watch on a clock. It is a change in the most useful description. Path integrals are the language often used to express this, and they carry a particular kind of intuition. In quantum theory, you can compute amplitudes by summing over many possible histories, each weighted by a phase. In quantum cosmology, the histories are different spacetime geometries and field configurations. The no-boundary proposal specifies which histories are included by requiring regular, boundaryless geometries. The key claim is not that time literally turns into space as if a dimension changes its identity. The claim is that the quantum description near the origin is best captured by Euclidean geometry, which avoids a singular boundary. That choice changes what initial condition means. Instead of specifying a starting state at a first time, you specify a smooth closure condition. Both Vilenkin and Hartle-Hawking aim to avoid a classical singularity, and both treat the early universe as a quantum object. Both still rely on a mathematical framework that is very far from philosophical nothing. The difference is in the boundary condition, and in how they interpret the emergence of time, whether by tunneling or by smooth closure. To keep the mystery honest, we have to talk about energy bookkeeping, because nothing often gets sold as an accounting trick. A common popular claim is that the universe could come from nothing because the total energy is zero. The idea is that positive mass energy can be balanced by negative gravitational potential energy. In some cosmological models, this balance can make the net energy of a closed universe vanish. This is speculative and subtle because energy in general relativity is not defined globally in the same way as in Newtonian physics. In curved spacetime, the conservation laws we love become local statements tied to symmetries through Noether's theorem. In an expanding universe, defining total energy depends on symmetries and boundary conditions, and those may not exist in the needed form. Still, the intuition matters for why almost nothing is not obviously forbidden by a simple conservation argument. If the net energy can be zero, then creating a universe may not require borrowing energy from an external account. It reframes the question from where did the energy come from to why is there a lawful structure that permits such a balance. Even if the net is zero, the universe is not nothing, and the distinction is more than philosophical hair-splitting. A zero balance can still include fields, geometry, and the rules that relate them. It can still include a probability distribution over possible beginnings. The terror is that our deepest explanations often end by assuming the very structure we hope to derive. This is the philosophical trap of smuggling in hidden assumptions, and physics is not immune to it. When physicists say nothing, they often mean no classical spacetime and no particles. They do not mean no quantum fields, no Hilbert space, no action principle, and no measure. The framework remains, and it quietly does the creative work. That does not make the proposals meaningless, and it does not reduce them to wordplay. It clarifies what kind of answer they are and what kind they are not. They are attempts to replace a singular beginning with a quantum boundary condition, so the origin becomes a calculable question rather than a breakdown. They aim to show that a universe like ours is not an impossible special case, and that the laws we know might naturally allow such a history. But then a harder question waits behind the curtain: why these laws, and why a quantum arena in which histories can even be discussed? What these ideas predict matters because cosmology is constrained by data, not by elegance alone. Inflation already gives us a handle through the spectrum of primordial perturbations. Quantum creation proposals may influence which inflationary initial conditions are likely. They may also affect the probability measure over different histories, which changes what outcomes are expected. Measures are a technical headache with big consequences, and the headache is not optional. If many universes or many histories are possible, you need a rule for weighting them. Otherwise, probability statements float. Different measures can make the same theory predict very different typical universes. Without a principled measure, likely becomes a word without a stable meaning. Some proposals suggest signatures in spatial curvature, and curvature is one of the few global features we can attempt to measure. A universe created as a small closed geometry might leave a preference for slight positive curvature even after inflation dilutes it. Observations currently constrain curvature to be very close to flat, but not exactly proven flat. Future surveys could tighten this and either squeeze or support certain nucleation pictures. Other potential constraints involve primordial gravitational waves and the detailed statistics of CMB fluctuations. Gravitational waves from inflation would imprint a distinctive polarization pattern in the CMB, and their amplitude relates to the energy scale of inflation. The no-boundary proposal in some treatments affects the weighting of perturbation modes, especially on the largest scales, which could influence the expected amplitude of large-scale fluctuations. There's also the question of whether these proposals can be made consistent with a full theory of quantum gravity rather than a controlled approximation. Quantum cosmology often uses simplified models called minisuperspace, where only a few degrees of freedom are quantized, such as the scale factor and a homogeneous field. This makes the math tractable, but it risks missing essential physics like inhomogeneities or topology changes. A complete theory would need to explain why the simplification is justified and what corrections it demands. It would also need to clarify what counts as an observation when there is no outside observer, a problem that sits at the intersection of cosmology and quantum foundations and has not been resolved. Historically, these ideas grew out of the same discomfort that drove singularity theorems and the timeline matters. In the 1960s and 70s, the Hawking-Penrose singularity theorems showed that under broad conditions, classical general relativity predicts singularities. Those theorems did not prove the Big Bang was a physical point. They proved the classical description becomes incomplete. Then Hawking's work on black hole radiation showed that quantum effects matter when gravity is extreme and that horizons have thermodynamic properties. That result made the union of quantum theory and gravity feel unavoidable, not optional. It encouraged the idea that the universe's beginning should also be treated quantum mechanically because the early universe is the ultimate strong gravity regime. The no-boundary proposal was part of that broader attempt to make the beginning a calculable object rather than a place where equations stop. Vilenkin's tunneling picture, emerging in the same era of quantum cosmology, offered a different boundary condition with a different intuition. These were not isolated speculations. They were responses to a shared problem. The classical singularity is a signpost that new physics is required. Still, the most honest outcome may be that from nothing is a limit concept, and limits reveal what a theory cannot say. It is a way of pushing explanations to the edge of what our formalism can express. The closer we get to nothing, the more we rely on mathematics to say what nothing could even be. The universe becomes a question about why there are rules at all. The proposals do something important, and the importance is scientific as much as philosophical. They show how the Big Bang might be a frontier, not a first moment, because the beginning can be replaced by a boundary condition. They show how time could emerge from a regime where time is not fundamental, at least in the classical sense. They show how causality might be an approximate concept that only applies after the universe becomes classical. That last point is easy to say and hard to absorb because causality feels like the skeleton of reality. If causal order depends on a classical spacetime structure, then at the deepest level, the universe may not be arranged as a simple chain. Instead, it may be arranged as a quantum superposition of possibilities from which a classical history condenses. If time is emergent, then before may be a category error, and the deeper question becomes why there is a lawful quantum arena at all. That is where the mystery stops being about our universe and becomes about reality's capacity to produce universes endlessly. If one universe can appear from a vacuum-like state, why not many? The idea of nothing begins to look less like a blank and more like a factory. Chapter 2 ended with a door left open. If one universe can nucleate from a vacuum-like state, why not many endlessly? The central question returns with new pressure because it refuses to stay philosophical. Did anything exist before the Big Bang? And if time began there, what could before even mean? The universe looks strangely calibrated for complexity, and the calibration shows up in equations as much as in starlight. The cosmological constant is small enough to permit galaxies rather than instant dilution. In Einstein's field equations, that constant behaves like a uniform energy density of empty space. In plain language, it is a pressure that can push the universe apart even when matter thins out. If it were much larger and positive, space would accelerate too quickly for gravity to gather gas into clouds and stars. If it were large and negative, the universe could recollapse before long-lived stars ever ignite. Particle masses and force strengths also sit in narrow ranges, and those ranges are not aesthetic. Shift them slightly, and chemistry collapses or stars never stabilize. The electron's mass sets the size of atoms, while the proton's mass anchors nuclei against thermal agitation. Electromagnetic coupling fixes how tightly electrons bind, and it decides which elements can form stable molecules. Even the strong nuclear force appears delicately placed between two failures. Weaken it and deuterium becomes unstable, choking off stellar fusion. Strengthen it and almost all hydrogen converts early, leaving little water-friendly chemistry. This is the fine-tuning problem in its least mystical form. The constants look selected, yet physics offers no obvious selector. Historically, the discomfort sharpened in the late 20th century as cosmology became precision science. When satellites mapped the cosmic microwave background, the numbers stopped being vague, and the coincidences became harder to ignore. One response is to widen the stage, not by adding new forces, but by multiplying arenas. If many universes exist with varied constants, then we observe a compatible one because we could not observe an incompatible one. That move is not comfort because it changes the kind of explanation we are allowed to want. It replaces a single miracle with an enormous machine that produces every option. Inflation is the hinge because it already reshaped early universe thinking, and it did so for practical reasons. It explains smoothness, flatness, and quantum seeds stretched to cosmic scales. The smoothness problem asks why distant regions share nearly the same temperature despite limited time to communicate. Inflation answers by making those regions once close enough to equilibrate before expansion carried them far apart. The flatness problem asks why space is so close to geometrically flat today. Exponential expansion drives curvature toward zero, much like zooming in on a sphere makes the surface look locally flat. But inflation can do more than start our hot phase. In many models, inflation never ends everywhere at once. Eternal inflation proposes a global spacetime still inflating even while local regions stop. Local regions stop inflating and become bubble universes like ours. Inside a bubble, inflation ends and energy converts into particles, and that conversion is reheating. The reheating looks like a Big Bang from inside. So the Big Bang becomes a local event, a beginning with an address. It is the start of our hot dense phase, not necessarily the start of existence. The engine is a scalar field often called the inflaton, defined by its value at each point in space. Its potential energy acts like a vacuum energy, producing negative pressure in the stress energy tensor. In plain terms, it makes gravity effectively repulsive on large scales, so space accelerates outward. In simple terms, the field sits high on a potential landscape like a ball balanced on a plateau. While it lingers, space expands exponentially. The word exponentially matters because it is not just fast, it is compounding. In a tiny fraction of a second, distances can double again and again, erasing earlier irregularities. Eventually, the field rolls down or transitions to a lower state. In some regions it does so, in others it does not. Quantum fluctuations make this uneven. During inflation, fluctuations in the inflaton field become fluctuations in when inflation ends, which becomes fluctuations in density. Some patches decay early, some late, and some get kicked back upward as if random jolts keep them hovering. That stochastic behavior is why inflation can be eternal. Expansion outruns decay, so inflating volume keeps growing overall even if many regions exit. The factory does not need to be stable everywhere. It only needs some regions to keep inflating faster than others stop. The multiverse picture is then geometric in a specific way. An apparently inflating background spawns bubbles, each with its own internal history. From far away, the background looks like a smooth accelerating fabric, but it is riddled with sudden transitions. Each transition is a bubble nucleation event, an abrupt change of state that creates a new domain. To make this concrete, cosmologists use the language of false vacuum decay, borrowed from quantum field theory. A false vacuum is a metastable energy state. Metastable means it can persist for a long time even if it is not the lowest energy configuration. It is locally trapped rather than globally stable. A familiar analogy is supercooled water, which can remain liquid below freezing until a disturbance triggers crystallization. In field theory, the disturbance can be quantum tunneling, which is not a classical climb over a hill. The field transitions through a barrier in its potential, appearing on the other side without traversing intermediate states. When tunneling occurs, a bubble of true vacuum nucleates. The new phase occupies a finite region bounded by a wall where the field changes rapidly. That wall has energy, and in relativistic terms it carries tension like a stretched membrane. The bubble expands at near light speed through the false vacuum. Inside, the vacuum energy is lower and dynamics change, including how quickly space expands. Outside, the false vacuum keeps inflating, and it can stretch away from the bubble wall, preventing a single bubble from consuming everything. That change is a phase transition in the early universe sense, and it echoes older transitions in particle physics. In the early universe, we already expect phase transitions like electroweak symmetry breaking and quark confinement. Those transitions reorganize what particles even mean because particles are excitations of fields whose properties depend on the vacuum. The energy difference between vacua does not vanish. It becomes kinetic energy of fields and then a hot plasma of particles. That is reheating. As reheating proceeds, particle species are produced, scatter, and thermalize, and the universe becomes an opaque soup. Photons, electrons, quarks, and gluons collide constantly, and the concept of a free path is almost non-existent. Our Big Bang in this framing is reheating inside one bubble, and the timing matters. It is a thermal beginning, not an absolute beginning. The familiar Big Bang narrative, hot, dense, expanding, still holds within the bubble after reheating. What changes is the claim that the hot phase marks the start of all reality. This reframes the opening hook without softening it because it makes the mystery more mechanical. If the Big Bang was the beginning of everything, why does the universe look like it remembers something that came before it? The memory is not a literal recollection, but a set of boundary conditions that look chosen. Why these constants? Why these initial smoothness conditions? And why a universe that can grow complexity rather than dissolve into featureless expansion? Eternal inflation makes before ambiguous because it separates local time from global description. There is an apparent spacetime where time continues even if our bubble's time begins at reheating. Inside our bubble, you can trace proper time back to a hot, dense state, and the equations remain well-behaved. Outside, the inflating background has its own clock defined by the evolution of the inflated field and the expansion of the metric. Yet the ambiguity cuts both ways because inflation does not automatically erase every beginning. Even in eternal inflation, singularities may still lurk in the parent spacetime. The Borde-Guth-Vilenkin result is often cited here, and it carries weight because it is not tied to one specific inflated potential. Many inflating spacetimes are past incomplete under broad conditions. Past incomplete does not prove a first moment, and it does not declare a singularity in the usual sense. It says the inflating description cannot be extended indefinitely into the past. In other words, if the average expansion rate along a past-directed world line is positive, that world line cannot be extended forever backward. Something else must take over, another phase, another boundary condition, or a deeper theory. So the factory may be endless forward, yet still require some boundary behind it. The terror shifts, but it does not disappear. If bubbles are real, we can ask for evidence, and the question becomes almost forensic. The cleanest hope is collisions between bubbles in the early epoch. A collision would disturb our bubble's early conditions in a specific geometric way. It could leave anisotropies or localized features in the cosmic microwave background. A bubble collision, if it happened before the surface of last scattering, could imprint a disk-like feature because the intersection of two expanding bubbles projects as a circle on our sky. The circle would not be a perfect ring, but a region with a subtle statistical oddness. Possible signatures include circular temperature anomalies or unusual polarization patterns, especially in the E-mode polarization field. Detection is difficult for basic reasons. First, we have one universe to examine. We see only one sky, and cosmic variance limits certainty at the largest scales. Cosmic variance is the unavoidable uncertainty from having only one realization of the random process that seeded fluctuations. Even with perfect instruments, the largest angular scales offer few independent modes, so anomalies can appear by chance. Foregrounds from the Milky Way complicate the map because our galaxy glows in microwaves through dust and synchrotron emission. Instrument systematics and data processing can create lookalike patterns. Even if a feature is found, interpretation is controversial because inflation itself can produce rare-looking features, and many inflationary models can mimic localized anomalies without any collisions. So the multiverse remains inference-heavy, and that is a scientific discomfort, not a poetic one. It is motivated by theory and fine-tuning, not by a single decisive observation. Still, it is not empty speculation because it is anchored to mechanisms we already use. If inflation is real and if quantum fields can tunnel, then bubble nucleation is not an exotic add-on. It is a natural extrapolation. Then a deeper problem appears, and it is technical but central. In an infinite multiverse, how do you define probabilities? In everyday life, probability is counting outcomes in a finite sample space or measuring frequencies in repeated trials. In an eternally inflating multiverse, the trial never ends, and the sample space is not just large, it is infinite. If inflation is eternal, it produces infinitely many bubbles, and within them infinitely many galaxies. Counting outcomes becomes ill-defined because every outcome occurs infinitely often. This is the measure problem, and it is not a minor bookkeeping issue. Probabilities depend on how you regulate infinities, and different regulators give different answers. One attempt uses a time cutoff. You count bubbles before a chosen time, then take a limit as the cutoff goes to infinity. But the result can depend on the time variable you chose because general relativity allows many slicings of spacetime. Different slicings of spacetime can reorder events and change ratios. A cutoff based on proper time can favor rapidly expanding regions, producing paradoxical predictions like the youngness problem, where most observers should find themselves in extremely young universes. A different time parameter can soften that, but then the choice looks arbitrary. Another attempt uses a scale factor cutoff, which tracks expansion rather than clock time. It counts events before expansion reaches a threshold, trying to reduce gauge dependence. Other measures focus on causal patches, restricting attention to what can influence a single world line. A causal patch approach feels conservative because it never asks you to compare disconnected infinities. Yet it raises its own questions about what counts as a representative world line and whether the restriction hides important global structure. None of these choices is obviously unique, and that is the wound that will not close. The multiverse can become a theory that predicts almost anything depending on the measure. That slipperiness matters because fine-tuning arguments rely on probability even when they try to sound modest. Still, the measure problem is not a fatal flaw by itself. It may be a clue. It may be a sign we are missing a deeper principle. Historically, physics has faced similar moments where infinities signaled incomplete understanding. The ultraviolet catastrophe pointed toward quantum theory. The infinities of early quantum electrodynamics demanded renormalization and new conceptual discipline. The multiverse measure problem may be another such warning, suggesting that our current language is not the final one. Perhaps the correct theory will define probabilities intrinsically without arbitrary cutoffs. The multiverse also connects to high-energy theory in a specific way, and the connection is not merely aesthetic. String theory suggests an enormous landscape of vacuum states. A vacuum state here means a stable or metastable configuration of fields and geometry, not an empty container. It determines low-energy physics, including particle spectra and constants. In string theory, extra dimensions must be compactified, curled into shapes too small to see directly. The shape, size, and topology of that compact space influence which particles appear and how they interact. Fluxes, field lines threading cycles in the compact dimensions, can take many discrete values. Different compactifications and flux choices yield different effective laws. The number of possibilities is often described as vast, and the conceptual point is that there may be many consistent vacua, not just one. In that context, eternal inflation becomes a population mechanism, a way to realize many vacua as actual regions by creating bubbles in different vacua. Then anthropic reasoning enters reluctantly because it seems to fit the logic of selection. Observers can only arise in regions where structure and chemistry are possible. Anthropic reasoning is not a claim that humans are special, and it is not a substitute for dynamics. It is a selection effect like noticing you live where air exists. If you find yourself on a planet with liquid water, you should not be surprised that its temperature range allows liquid water. The surprise would be if the laws forced that outcome uniquely, rather than allowing many outcomes and selecting the habitable subset. This is where tension rises because the method feels like a change in scientific taste. Some physicists see anthropics as the only workable filter. Others see it as surrender. The unsettling point is that the multiverse can make fine-tuning feel inevitable. That inevitability can dull curiosity. It can also make fundamental explanation feel optional. Yet even here the story is not simple, because anthropic arguments can be sharpened into testable expectations. If a distribution over constants can be defined, then one can ask whether our observed values are typical among observer-friendly regions. Cosmological constant is often the flagship example because its observed value is small but not zero. Some argue that it sits near the upper edge of values that still allow galaxy formation, which would be a suggestive, though not decisive anthropic hint. But without a stable measure, even that hint is fragile. The many worlds interpretation offers a different multiverse that does not rely on distant bubbles and comes from quantum mechanics itself. It treats the wave function as real. It denies a physical collapse during measurement and instead treats measurement as an interaction like any other. The cost is ontological. You accept that the full quantum state contains all outcomes. Instead of one outcome crystallizing, interactions entangle systems with environments, and that entanglement spreads rapidly. The combined state branches into effectively non-interfering histories. Decoherence is the key technical idea. It does not destroy superpositions. It makes interference between branches practically impossible by dispersing phase information into the environment. Each branch contains a definite outcome for observers inside it because observers are part of the entangled system. All outcomes exist in the full quantum state. Many worlds can coexist with inflationary multiverses, but it is conceptually distinct. One multiplies regions, the other multiplies histories. In many worlds, before the Big Bang is not directly answered, and it is not meant to be. It changes what reality means at all times, including the early universe. Yet it adds another layer to the factory metaphor because it multiplies outcomes even inside one bubble. Even within one bubble, quantum events generate a branching tree of outcomes. The disturbing consequence is not only multiplicity, although multiplicity is already dizzying. It is the erosion of the idea of a unique beginning. If bubbles are constantly produced, then no beginning becomes plausible, at least as a practical picture. The Big Bang becomes a local origin story, not the origin. But the parent spacetime may still have boundaries, and that boundary could be conceptual as much as geometric. Even an infinite factory can sit on a finite foundation. So the multiverse is both explanatory and evasive, and the tension is not a flaw we can edit out. It can explain why we can exist while weakening what prediction means. We return to the central question now reframed by machinery and by mathematics. Did anything exist before the Big Bang? And if time began there, what could before even mean? Inside our bubble, time may begin at reheating where temperature and entropy become well defined. Outside, time may continue, or it may be replaced by a deeper ordering. Either way, the Big Bang looks less like a first moment and more like a transition, a boundary between phases. It looks like a phase change in a larger system. That larger system may be indifferent to starts and endings because it is governed by statistical processes. It may produce universes the way radioactive atoms produce decays, unpredictable for any single atom, yet precisely describable for large populations. And if that is true, then uniqueness is the illusion, and our sense of specialness is an artifact of perspective. Our cosmos is one outcome among countless others, most forever unobserved. We pivot now to the next consideration because the factory has moving parts. If universes are bubbles, what happens when bubbles meet? Could our Big Bang be the scar of a collision rather than the quiet birth of a lone bubble? We carry that question forward because it is where theory might touch evidence. The next chapter follows the boundary where bubbles touch and where beginnings may be impacts. Chapter 3 ended with a fear that has moving parts because it imagines universes as bubbles with edges that can drift and meet. If universes are bubbles, what happens when bubbles meet? Do they merge, rebound, or tear each other open? The image is simple, yet it carries a technical sting because collisions imply a surrounding arena where motion is even possible. This chapter pivots the meaning of the Big Bang. Not creation from nothing, but an impact that made our region hot. The question is not only what happened, but what kind of thing can be heated without being created. The central question returns with sharper grammar because language breaks when it reaches the edge of time. Did anything exist before the Big Bang? And if time began there, what could before even mean? We use before as if it were a place on a line, yet physics treats time as part of the geometry that can bend, stretch, and even end. In standard cosmology, Big Bang means an early hot, dense, expanding phase described by the Friedmann equations and a thermal history we can test. It does not automatically mean the first moment of existence, even if popular imagery often suggests that. Brain cosmology takes the caution about beginnings and makes it literal by changing what universe refers to in the first place. Our universe becomes a surface embedded in a larger, higher dimensional space with its own geometry and its own notion of distance. To say extra dimensions is not to add fantasy space, even though the phrase can sound like science fiction. It is to follow where certain unification attempts naturally laid when they try to combine quantum mechanics with gravity without mathematical contradictions. The claim is not that dimensions are added for drama, but that the equations demand room to breathe. Historically, the temptation to add dimensions is older than string theory, and it began as a conservative move. In the 1920s, Kaluza and Klein noticed that a fifth dimension could unify gravity and electromagnetism in a single geometric framework. Their idea also introduced a key motif that returns here. Extra dimensions can be hidden if they are compact, curled into tiny circles that ordinary motion cannot resolve. String theory needs additional spatial dimensions for mathematical consistency because quantized strings behave badly in too few dimensions. In many versions, the critical number is 10 spacetime dimensions, where anomalies cancel and the theory remains self-consistent. M-theory reframes them as an 11-dimensional structure with extended objects, suggesting that what looked like separate theories are different limits of one deeper framework. In these frameworks, the fundamental ingredients are not only point particles. They include strings and branes, higher dimensional dynamical surfaces that can vibrate, stretch, and carry energy. A brane can have 3 large spatial dimensions, like our everyday world, while still existing inside a higher dimensional bulk. Standard model fields may be confined to it, while gravity can leak into the bulk, spreading along the extra directions. That confinement is a crucial move because it explains why we do not see extra dimensions directly in particle experiments or daily life. We are stuck to the brane like ink on a sheet, able to slide along its surface but unable to lift off. The bulk is the higher dimensional arena around the brane, and it can carry geometry and fields that our particles cannot access. Now the Big Bang can be reinterpreted as a boundary event on the brane rather than the birth of spacetime itself. It is the moment the brane became hot and filled with radiation, initiating the thermal history that leads to nuclei, atoms, stars, and eventually observers. In this framing, the Big Bang is less like a starting gun for reality and more like the ignition of a particular region's matter content. Ekpyrotic scenarios propose a prehistory that is not expanding, which immediately changes the emotional rhythm of the story. The brain undergoes a slow contraction that prepares the conditions for a hot phase, smoothing the universe before the heating event. The contraction is not a collapse into chaos, at least in the idealized model, but a controlled approach toward a transition. The word ekpyrotic comes from an ancient idea of cosmic fire associated with Stoic philosophy and the notion of periodic conflagrations. Here it means a smoothing contraction driven by a steep negative potential, a particular shape of energy landscape in field theory. In plain terms, the universe is pulled into a state that erases wrinkles because the dominant energy behaves like an ultrastiff substance. In the simplest picture, there are 2 branes separated along an extra dimension, like parallel sheets with a small gap between them. They move, approach, and eventually collide, with the separation acting like a dynamical variable that can change over time. The approach can be slow and almost silent, which makes the collision feel less like a blast and more like a decisive contact. The collision is not an explosion into empty space because there is no outside void waiting to be filled by debris. It is an energy transfer, converting brane motion into particles and heat on our brain as kinetic energy becomes radiation. So the Big Bang becomes a bruise, not a birth. The observable universe begins as aftermath, not as the start of the stage, because the stage, the bulk in the branes, was already there in the model. Some versions are cyclic rather than one time, which turns the collision from a singular event into a repeating motif. Branes repeatedly approach, collide, separate, and reset the hot phase again, with long, cool eras between brief, violent transitions. A cyclic model must manage entropy carefully because thermodynamics is not impressed by narrative elegance. It needs a mechanism to dilute or export disorder between cycles, or cycles quickly degrade, becoming longer, emptier, and less capable of producing structure. Entropy is the bookkeeping of irreversibility, and any cosmology that loops must explain why the books do not explode. The attraction of ekpyrosis is that it can address classic puzzles differently than inflation while staying within a disciplined mathematical framework. It uses contraction to smooth and flatten before the bounce, rather than expansion to do the smoothing afterward. That reversal matters because it changes what initial conditions are required and when they must be set. Inflation smooths by rapid expansion that stretches irregularities away, making distant regions look similar because they were once close. Ekpyrosis smooths by a slow, ultrastiff contraction that suppresses curvature and anisotropy, driving the universe toward uniformity as it shrinks. In both stories, the goal is the same sky we see, nearly flat and nearly uniform, but seeded with tiny variations. In technical terms, ekpyrotic matter has an equation of state with W much greater than 1, meaning pressure dominates energy density in a specific way that makes its energy density grow faster than shear during contraction. so chaotic distortions are damped rather than amplified. In plain language, the contraction is stiff enough to keep the universe from crumpling into a lopsided mess. This changes the horizon story, which is one of the Big Bang's most famous conceptual problems. Regions can become correlated during a long pre-collision phase without requiring a burst of exponential expansion because the relevant scales can interact for a long time. The model tries to explain why the CMB is so uniform across the sky, even though light could not have crossed it in a naive expanding picture. But the pivot comes with costs, and the costs are not just aesthetic. A contracting universe is vulnerable to mixmaster chaos unless the ekpyrotic phase is strong enough because anisotropies can dominate in generic contractions. Then comes the bounce problem, which is where the story meets the stubbornness of general relativity. General relativity resists a smooth transition from contraction to expansion without violating energy conditions or adding new physics because ordinary matter and radiation tend to focus geodesics and drive singularities. A bounce is easy to draw and hard to achieve, which is why the collision picture becomes attractive. In brane pictures, the bounce is replaced by a collision, and the singularity is traded for a higher dimensional event whose microphysics must be specified. The hope is that what looks singular in 4 dimensions is less pathological in the full geometry because additional degrees of freedom can soften the transition. The scientific question is whether the story reproduces the observed pattern of primordial perturbations, the tiny seeds that later become galaxies and clusters. Our universe's structure begins as tiny density variations, and those variations leave multiple fingerprints. The CMB shows a nearly scale-invariant spectrum with a slight tilt and near-Gaussian statistics. The acoustic peaks in the CMB power spectrum, produced by sound waves in the primordial plasma, also lock in the physics with remarkable precision. Inflation produces that spectrum naturally from quantum fluctuations stretched outside the horizon. Ekpyrotic models must work harder to match the same data because contraction changes how perturbations evolve and what becomes frozen in. In the simplest single-field ekpyrotic contraction, curvature perturbations are not automatically scale-invariant, which is a serious problem. They tend to be strongly blue, with too much power on small scales, implying a universe that would form structure too early and too violently. The model must therefore add structure, additional fields, or mechanisms to shape the perturbations into what we observe. To fix this, many ekpyrotic models use an entropic mechanism, which introduces at least 2 fields during the contraction. 2 fields generate nearly scale-invariant entropy perturbations, later converted into curvature perturbations, so the right kind of wiggles end up in the metric. That conversion can happen near the bounce or during a turn in field space when the background evolution changes direction. It is a technical step, and it introduces new parameters and new failure modes because the timing and efficiency of conversion affect the final spectrum. Non-Gaussianity becomes a pressure point because it probes the interactions of the fields rather than just their linear behavior. Some ekpyrotic conversions naturally produce larger non-Gaussian signals than simple inflation predicts, especially of the local type associated with mode coupling in the sky. That would mean the fluctuations are not perfectly random, but slightly skewed or correlated in a specific pattern. Observations constrain non-Gaussianity tightly using the CMB and large-scale structure surveys, which forces ekpyrotic models into narrower corners or toward more elaborate conversion dynamics where cancellations reduce the signal. Then there is the clean discriminator that does not depend on galaxy formation details, primordial tensor modes. Gravitational waves from the earliest phase would propagate almost freely and preserve information about the energy scale and dynamics. Inflation generically predicts a stochastic gravitational wave background, a sea of tensor fluctuations produced by quantum effects during rapid expansion. Its amplitude is tied to the energy scale of inflation and encoded in the tensor-to-scalar ratio, which compares tensor power to scalar power. If large enough, it should imprint a distinctive pattern in the polarization of the CMB. Ekpyrotic contraction typically predicts very small tensor amplitudes because the mechanism that generates scale-invariant scalars does not simultaneously boost tensors on large scales. That difference becomes a test, and it is one of the few tests that feels almost binary. CMB B-mode polarization searches look for the curl pattern that primordial gravitational waves would imprint, distinct from the gradient-like E-modes produced by density perturbations. Detection of large-scale primordial B-modes at appreciable amplitude would strongly favor inflation-like dynamics because it would imply a high-energy early phase that excites tensors. A continued non-detection pushes many inflation models down while remaining consistent with ekpyrotic predictions. Yet the logic is asymmetric because silence can mean many things. non-detection is not a clean victory for ekpyrosis. Inflation can also produce low tensor amplitudes in many well-motivated models. Foreground dust can mimic or hide signals, and lensing of E modes into B modes adds a confounding background that must be subtracted carefully. Brain collision models also invite more specific scars. Because collisions are rarely perfectly clean, a collision might not be perfectly symmetric, and asymmetry could leave anisotropic imprints like a preferred direction or a gradient across the observable universe. Those imprints could appear as statistical anisotropy in the CMB, meaning the fluctuations would not be identical in every direction. They could also appear as localized features or unusual polarization correlations, where certain patches behave differently than the rest. The difficulty is that the universe gives us only one realization, so pattern recognition can become a mirror for our own expectations. There is also the question of what counts as before, and brain cosmology forces the question to split. In these models, our brain time can begin at the collision while bulk time continues, providing a wider ordering of events. The word before can be meaningful in the bulk, even if it is not meaningful within our four-dimensional effective description. The timeline depends on which clock you trust. A brain observer may have a natural time coordinate that fails at the collision, while the bulk geometry still admits an extension. If gravity propagates in the bulk, then the bulk is not a passive container because gravity is geometry and geometry backreacts. Its dynamics can influence brain motion, separation, and collision timing, altering the effective physics on the brain. Even if bulk time exists, pushing the question back a layer does not solve it. The bulk itself may still be past incomplete, meaning that geodesics cannot be extended indefinitely into the past. A brain collision can replace a singularity in 4 dimensions, which is a significant conceptual shift. It does not automatically remove the need for a deeper beginning of the bulk, because the bulk may have its own singularities, boundaries, or quantum origin. The collision story can therefore be a middle layer, explaining our hot start while leaving the ultimate origin question intact. So the Big Bang becomes a frontier again, a boundary of our effective description rather than an unquestionable origin. It is the point where our effective 4-dimensional description begins, not necessarily where reality begins. Before can mean earlier along our brain time, earlier along bulk time, or earlier in a deeper ordering that does not map cleanly onto either. Each meaning implies a different kind of explanation, and each demands a different kind of evidence. If bulk time exists, then the question becomes sharper, not softer, because we have merely moved the mystery outward. What sets the bulk's initial conditions, and why does the bulk exist at all? A larger stage does not eliminate the need for a first cue unless the stage is itself eternal or self-contained. If bulk time does not have a first moment, then the collision is not an origin, and that changes the philosophical weight of the Big Bang. It is a transition inside an eternal or self-contained structure where beginning is a local feature rather than a global one. The Big Bang would be like dawn on a planet, real, dramatic, and bounded, yet not the beginning of time. That brings us to the next pivot. What if even the bulk has no first moment? And what if time itself had no beginning? The question is unsettling because it suggests that the deepest layer may not be a longer timeline, but a different concept altogether. We carry the central question forward because the collision does not end it. The Big Bang may not be a first moment but a frontier, and the frontier might be a bruise on a brain inside a reality with no start. If time can exist outside our universe, then time might also be an illusion inside it, emergent from deeper relationships rather than fundamental. Next, we follow the question past collisions and bulks. We ask whether time is fundamental or whether it is something that emerges and can disappear. Chapter 4 ended by pushing the mystery outward from our hot beginning to time itself. If the Big Bang is a frontier, then before may be the wrong question. We ask the central question again, but we change its grammar and its assumptions. Did anything exist before the Big Bang? And if time began there, what could before even mean? Everyday language treats time like a container that events sit inside, like water filling a glass. We picture moments stacked in order, each one waiting patiently for the next. That picture is useful for calendars and memory, and it matches the way our brains sequence cause and effect. Yet it quietly smuggles in a background clock that ticks the same everywhere, regardless of motion or gravity. Modern physics treats time as part of the system, shaped by energy and motion. Time is not merely a stage, it is part of the script. In general relativity, time is stitched to space into spacetime, a 4-dimensional fabric that can bend. Matter and radiation tell spacetime how to curve, and that curvature tells matter how to move. A clock is not a universal referee. It is a physical object tracing a world line through that geometry. Two identical clocks can disagree after following different routes because time is a measure of spacetime distance, not an external metronome. So before the Big Bang quietly assumes a background clock that keeps ticking behind the scenes, but the Big Bang may be where that clock stops being defined because the notion of a smooth time coordinate breaks down. When cosmologists say the universe was hotter and denser in the past, they mean something precise. They mean the scale factor was smaller and the energy density in radiation and matter was higher. The scale factor is a bookkeeping device for cosmic size, and it translates directly into redshift. Run the equations backward and the temperature rises. Yet that mathematical extrapolation may be pointing toward a boundary of the model, not a literal first frame. Cosmology tempts us with a simple alternative that feels almost like relief. Maybe the clock never started because time extends indefinitely into the past. A past eternal universe sounds like a way to dissolve the origin problem. If there is no first moment, there is no need for a first cause. But past eternal does not mean static or unchanging, and it does not mean calm. It means the timeline has no earliest page, even if chapters begin, end, and restart. The idea has a long history because it is as old as the discomfort with beginnings. Aristotle favored an eternal cosmos while other traditions insisted on a definite beginning, and the tension never fully disappeared. When Einstein's equations arrived, they turned the argument into geometry, forcing expansion or contraction unless special conditions were imposed. We begin with the intuition behind steady-state thinking, updated for modern data and modern humility. The universe could be eternal yet locally evolving if creation or transitions keep it looking similar on large scales. In the mid-20th century, the steady-state model offered a striking promise. As the universe expanded, matter would be continuously created, keeping the average density constant and the cosmos statistically unchanged. It was elegant in one sense because it made the universe the same at all times. It also carried a philosophical charge because the universe would have no special moment of birth. The model leaned on what was called the perfect cosmological principle, extending uniformity not just across space but across time. That extension was audacious, and for a moment it felt like a clean escape from cosmic origin stories. Classic steady-state failed because the universe changes with redshift, and the sky keeps records. The cosmic microwave background discovered in 1965 is not a minor detail. It is a relic radiation field with a near-perfect blackbody spectrum. A blackbody spectrum is a thermal fingerprint, and it is hard to counterfeit by late-time astrophysics. Its smooth curve tells us the radiation once equilibrated in a hot, dense environment, then cooled as space expanded. When we look farther away, we look back in time and we see younger galaxies, different star formation rates, and a universe that does not resemble the present. Radio surveys, quasar counts, and the abundance of galaxy clusters all shift with distance in a way steady state could not absorb. The universe has a history written into its populations, and that history points toward a hotter, simpler past. Yet the deeper impulse survives in newer models because the desire for an eternal past never truly left. Replace continuous creation with phases, bounces, or an emergent prehistory, and the old question returns wearing new mathematics. One family is the emergent universe scenario, which tries to keep the past without keeping the old steady-state machinery. The cosmos exists for an arbitrarily long time in a quasi-static state, then transitions into inflation. In these models, the scale factor can hover near constant for ages, neither collapsing nor expanding rapidly. The universe is not empty in this phase, but behaves as if it is balanced on a knife edge. Then a trigger destabilizes the state and rapid expansion begins, smoothing and stretching space. The transition is meant to be graceful, like a quiet room suddenly filling with wind. The appeal is surgical because it targets the origin problem without discarding the successes of the hot Big Bang picture. You keep an eternal past, but you still generate a hot Big Bang-like phase after inflation and reheating. Reheating matters here because inflation by itself is cold and sparse. In many models, the energy stored in the inflationary field must be converted into particles and radiation, repopulating the universe with a thermal bath. That conversion is not just a narrative flourish because it sets the initial conditions for everything that follows. It determines how many photons exist per baryon, how quickly the plasma thermalizes, and whether later nuclear reactions have the right starting point. That thermal bath is not an aesthetic preference. It is demanded by what we see. The danger is also surgical because the quasi-static eternal state can be unstable in subtle ways that are easy to underestimate. Small perturbations can grow under gravity. A universe that sits still for too long may not remain homogeneous because quantum fluctuations, even tiny ones, can seed structure that gravity then amplifies. If the quasi-static phase lasts forever, those fluctuations have infinite time to grow, which would destroy the homogeneity the model needs. The model must therefore be carefully constructed so that the quasi-static phase is genuinely stable against small perturbations, while remaining destabilizable by the specific mechanism that triggers inflation. This is a narrow target, and hitting it requires specific choices in the potential and in the matter content that supports the quasi-static configuration. Some models use a closed universe supported by a particular combination of a scalar field and radiation, where the field's potential energy balances gravitational attraction. Others use a loitering phase in a universe with specific curvature and energy content that naturally slows expansion to near zero before resuming. The word loitering is borrowed from older cosmology, where it described universes that spent a long time near a nearly static configuration before resuming expansion. The name is casual, but the physics is precise because the scale factor's behavior is dictated by the Friedmann equations, and the equation of state of whatever drives the near stasis. In a closed universe model, spatial curvature provides a natural tendency to recollapse, while a scalar field or cosmological constant provides an outward push. Balancing these can produce a quasi-static configuration, but the balance is delicate in exactly the way a pencil balanced on its tip is delicate. Any perturbation tips it one way or the other. The model needs a mechanism that allows the quasi-static phase to last long enough to be philosophically useful, meaning arbitrarily long in the past, while still transitioning cleanly into inflation. That transition must happen without producing detectable anomalies in the CMB or in the pattern of primordial perturbations. The sky must look like it came from a clean inflationary start, not from a complicated prehistory, or at least the prehistory's fingerprints must be faint enough to hide within current observational uncertainties. A related idea appears in string gas cosmology, which approaches the question from a different direction by asking what the very early universe would look like if strings were the fundamental degrees of freedom rather than point particles. In this picture, the universe begins as a small, compact space filled with a hot gas of fundamental strings. Strings are not point-like, and they have unusual properties at high energies. One of the most important is that they have a maximum temperature called the Hagedorn temperature, beyond which adding energy does not raise the temperature, but instead creates more string modes. The Hagedorn temperature acts as a natural ceiling on the thermal energy of the string gas, which changes the dynamics of the early universe dramatically. In ordinary radiation-dominated cosmology, the temperature rises without bound as you compress the universe. But in a gas of strings, the temperature approaches the Hagedorn limit and then plateaus while energy goes into creating new string configurations rather than raising the temperature further. This changes the pressure and the equation of state, and it changes how the scale factor evolves. Instead of a singular Big Bang where temperature and density diverge, the universe may bounce through a hot string phase where the Hagedorn ceiling prevents the temperature from reaching infinity. The cosmological implications are striking because string gas cosmology offers an alternative mechanism for generating a nearly scale-invariant spectrum of primordial perturbations. In this picture, the spectrum arises from thermal fluctuations of the string gas near the Hagedorn temperature rather than from quantum fluctuations stretched by inflation. The mechanism is different, but the output can be similar, producing a spectrum that is nearly flat with a slight tilt. The details depend on the specific dynamics of the string gas and on how the transition from the string phase to ordinary radiation domination proceeds, but the basic idea is that thermal physics near a maximum temperature can mimic some of the properties of inflationary quantum fluctuations. String gas cosmology also has implications for extra dimensions and for why we live in 3 large spatial dimensions rather than more. In a universe with several compact dimensions, different winding modes of strings wrap around different cycles, and their interactions determine which dimensions can grow large. Dimensions that are wrapped by winding strings cannot expand freely because the strings resist being stretched. For a dimension to expand, its winding modes must annihilate with anti-winding modes. In 3 spatial dimensions, winding modes can find each other efficiently enough to annihilate, allowing those dimensions to grow. In higher numbers of large dimensions, the probability of meeting drops and winding modes persist, keeping those dimensions compact. This gives a statistical argument for why space appears 3-dimensional at large scales, not a proof but a preference that arises from the dynamics of string interactions. The connection to the question of time is indirect but real because string gas cosmology changes what the very early phase looks like. Instead of a classical singularity or a quantum tunneling event, the early universe is a hot string gas in a compact space, and the transition to our familiar expanding universe is driven by the thermal and dynamical properties of that gas. Time still exists throughout this phase, so there is no question about before in the sense of before time. But the question shifts to what set up the initial string gas state and whether the compact phase could have existed for an arbitrarily long prior time, or whether it also required an origin. Pre-Big Bang cosmology, developed by Gabriele Veneziano and Maurizio Gasparini, takes a related but distinct approach using the duality symmetries of string theory. String theory has a remarkable property called T-duality, which relates a universe with large dimensions to one with small dimensions through a specific transformation. If you take a universe with scale factor and transform it to one with scale factor inversely proportional to the physics looks the same because strings see both regimes as equivalent. A string propagating in a small compact space behaves like a different kind of string in a large space, and the two descriptions are physically indistinguishable at the level of the string dynamics. This duality suggests that the Big Bang might be connected to a pre-Big Bang phase through a duality transformation. In the pre-Big Bang scenario, the universe before the Big Bang is described by a solution called the dilaton-driven phase, where the string coupling grows and the universe contracts in the Einstein frame while expanding in the string frame. The distinction between frames matters because general relativity and string theory use different natural variables, and the two descriptions of the geometry can look different. In the string frame, which is the natural home for the string dynamics, the pre-Big Bang phase looks like an accelerating expansion from very weak coupling. In the Einstein frame, which is the natural home for general relativity, it looks like a contraction from a large, cold, dilute state. The bounce that connects the pre-Big Bang phase to the post-Big Bang phase is the difficult part of the construction. Near the transition, the string coupling becomes strong, and the dilaton, the field that controls the coupling strength, runs through a regime where perturbative string theory breaks down. Higher-order corrections in both the string coupling and the curvature must be included, and they must conspire to produce a smooth transition rather than a singularity. This is technically demanding, and the outcome depends on the specific form of the corrections, which are not fully known from first principles. Some models show that the corrections can indeed smooth the transition and produce a bounce, while others produce new singularities in different guises. The construction is promising but incomplete, which is an honest assessment of where the field stands. What pre-Big Bang cosmology offers is a concrete realization of the idea that the hot Big Bang phase may be preceded by a cold, dilute, slowly evolving phase connected by a string-theoretic duality. The pre-Big Bang universe is not empty, and it is not nothing. It is a specific physical state with its own dynamics and its own spectrum of perturbations. The perturbations generated in the pre-Big Bang phase have a very blue spectrum in the simplest models, meaning they are strongly scale-dependent, with more power on small scales. This differs from what we observe in the CMB, so additional mechanisms are needed to produce the right spectrum. The dilaton field and other moduli can generate perturbations with different spectral properties, and curvaton-like mechanisms, where a secondary field generates the observed perturbations after the bounce have been explored. These are not arbitrary patches, but they do add complexity to the picture. Now we return to a more fundamental version of the eternal question, because all the scenarios we have considered so far still operate within a framework where time exists, even if its properties change. The radical possibility is that time itself is not fundamental but emergent, arising from a deeper description in which time has no independent existence. This idea has a long philosophical history, but it gained technical traction in physics through an unexpected source, the problem of quantum gravity. When you try to combine quantum mechanics with general relativity in the most straightforward way, you run into a remarkable equation called the Wheeler-DeWitt equation. This equation describes the quantum state of the universe, and it is derived by applying the machinery of quantum mechanics to general relativity's constraints. The result is an equation that contains no time variable at all. The wave function of the universe satisfies a timeless equation, meaning the quantum state does not evolve from one moment to another in the usual sense. The equation does not say the universe is frozen. It says that the universe's quantum description is outside time in a specific technical sense. This is known informally as the problem of time in quantum gravity, and it is one of the deepest puzzles in theoretical physics. In ordinary quantum mechanics, the Schrödinger equation describes how a quantum state evolves with respect to an external time parameter. That external time is provided by the classical background, by the laboratory clock, by the experimenter's watch. But in quantum cosmology, there is no external background. The universe is everything, so there is no outside clock against which to measure its evolution. The Wheeler-DeWitt equation reflects this by simply not containing an external time. The response to this puzzle divides into several camps, and the division reflects deep disagreements about what time is. One camp says time is fundamental, and the Wheeler-DeWitt equation must be reinterpreted or modified to restore it. Another camp says time is indeed not fundamental and must be understood as emergent. If time is emergent, then the question of what existed before the Big Bang changes its meaning entirely. Before is a temporal concept, and if time is not fundamental, then before has no foundation in the deepest description of reality. It is a derived concept that applies in the semi-classical limit, where the quantum state picks out a preferred time direction, but it has no meaning in the fundamental timeless description. The most developed version of the emergent time idea is related to what is called the Page-Wouters mechanism, developed by Don Page and William Wouters in the 1980s. Their insight was that time can emerge from quantum entanglement between a system and what serves as a clock. In a timeless quantum state, different subsystems can be correlated in a way that mimics time evolution when viewed from the perspective of one subsystem. If you condition on the state of a subsystem that acts as a clock, the rest of the system appears to evolve relative to that clock's readings. Time is not a background parameter. It is a relational property, a way of describing correlations between parts of an entangled quantum state. This is subtle and easy to misread as a mere interpretation game. But it is not. The Page-Wouters mechanism makes concrete predictions about the statistics of measurements on entangled systems, and those predictions have been tested and confirmed in laboratory experiments using photon systems that simulate the quantum structure of the mechanism. The tests do not prove that cosmological time is emergent in the same way, but they establish that the emergent time idea is not internally inconsistent, and that it reproduces ordinary quantum evolution in the appropriate limit. If time is relational and emergent, then the question of what the universe looked like before the Big Bang becomes the question of what the quantum state looks like in a regime where the relational clock has not yet been established. The answer may be that the concept simply does not apply, not because something prevents us from looking, but because the very notion of looking at a time requires a clock, and a clock requires a spacetime in which clocks can exist. In the timeless quantum description, the universe may not have a before in the same way that the surface of a sphere does not have a north of the North Pole. Causal dynamical triangulations, or CDT, takes a computational approach to this problem by constructing spacetime from tiny building blocks and asking which global geometries emerge from the quantum sum over those building blocks. The idea is to take the path integral over geometries seriously as a computational procedure, discretizing spacetime into small simplices, the higher dimensional analogs of triangles and tetrahedra, and summing over different ways to glue them together. The constraints of the sum, particularly the requirement that the gluing respects a causal ordering, turn out to be crucial. When the causal structure is enforced, the sum produces a universe that looks four-dimensional at large scales and has sensible geometry. When causal structure is relaxed, the sum produces pathological geometries that crumple into two dimensions or blow up into branching trees. The emergence of sensible geometry from this discrete quantum sum is remarkable because it is not put in by hand. The large-scale structure of spacetime, including its dimensionality and its smooth appearance, arises from the quantum dynamics of the discrete building blocks. Time plays a special role in CDT because the causal ordering is built in from the start, distinguishing past from future at each step. This is different from purely Euclidean approaches, where all directions are treated symmetrically. The causal structure is what makes the construction work, which is a hint that time's distinction from space may be physically important even at the quantum level. What CDT tells us about the very early universe is that near what would be the Big Bang in the classical description, the quantum geometry becomes highly irregular, and the notion of a smooth spacetime begins to dissolve. The scale factor, which measures the universe's size, fluctuates wildly at the smallest scales. The concept of a definite geometry becomes ill-defined, but the simulation does not produce a singularity in the classical sense. It produces a quantum regime where the geometry is genuinely quantum and where semi-classical notions simply do not apply. Whether this quantum regime has a before in any meaningful sense is a question the simulation cannot yet answer because it requires extending the computation into regimes where the discretization becomes the dominant effect. Spin foam models offer another approach to quantum gravity that addresses time in a different way. In spin foam models, the quantum state of geometry is represented by a network of spins and intertwiners, the spin network, and its evolution is described by a history of such networks, the spin foam. The spin foam is a four-dimensional structure that encodes the quantum amplitude for a given spacetime history. Time in this picture is not a background parameter, but is encoded in the combinatorial structure of the spin foam itself. The ordering of the spin foam's vertices and edges provides a notion of causal structure, but it is a quantum causal structure that can be in a superposition of different orderings. This quantum superposition of causal orders is one of the most radical features of quantum gravity approaches. In ordinary physics, causes precede effects, and this ordering is fixed by the classical spacetime structure. In quantum gravity, if spacetime itself is quantum, then the causal ordering may be in a superposition. Recent work in quantum information has shown that quantum causal structures, where the causal order is itself in superposition, can enable computational and informational tasks that are impossible with fixed causal order. This suggests that quantum causality is not merely a philosophical curiosity, but has physical consequences that might in principle be tested, though the tests currently envision controlled laboratory experiments rather than cosmological observations. If the causal structure of the very early universe was genuinely quantum, meaning in a superposition of different causal orderings, then the question of what came before the Big Bang may be doubly ill-posed. Not only does before require a time parameter that may not exist fundamentally, it also requires a definite causal ordering that may itself be quantum and indefinite. The universe near its beginning may have been in a state where asking what caused what is as meaningless as asking what is north of the North Pole, but for a deeper reason, not just because the coordinate runs out, but because the very structure that defines earlier and later was itself in superposition. Relational quantum mechanics, developed by Carlo Rovelli, takes this relational view of time and extends it to all of quantum mechanics. In relational quantum mechanics, quantum states are not absolute. They are defined relative to an observer or a reference system. What one observer describes as a definite quantum state may be described differently by another observer, and both descriptions are equally valid because there is no view from nowhere that captures the absolute state of the universe. This is a radical departure from the standard picture, where the quantum state is an objective mathematical object that encodes all the information about the system. In the relational view, time is just another relational quantity. The time that appears in the Schrödinger equation is the time measured by a specific physical clock, not an absolute background time. Different clocks give different descriptions of the same physical situation, and these descriptions are all valid. The coherence of physics arises not from an absolute background, but from the consistency of the correlations between different observers' descriptions. This relational structure is inspired by the lessons of general relativity, where coordinates are arbitrary labels and only coordinate-independent quantities have physical meaning. For cosmology, the relational picture has a striking implication. If there is no absolute time, then asking about the state of the universe before the Big Bang is asking about a relational quantity without specifying what it is related to. The question is incomplete in the same way that asking about the position of an object without specifying a reference frame is incomplete. The answer depends on the reference, and if no physical reference exists in the pre-Big Bang regime, the question may have no answer, not because the answer is hidden, but because the question is malformed. This is not defeatism. It is a change in what we should be asking. Instead of asking what was there before the Big Bang, we might ask what are the relational quantities that remain well-defined through the transition, what correlations survive from the pre-Big Bang phase to the post-Big Bang phase, and what physical clocks existed in both regimes that allow a comparison. These are harder questions, but they are questions that physics can in principle approach, whereas asking about absolute time before the Big Bang is asking physics to do something it may be fundamentally incapable of doing. The thermal time hypothesis, proposed by Kahns and Rovelli, offers a specific mechanism for how time could emerge from a statistical state. The idea is that in a quantum gravitational setting, what we experience as time is the flow generated by the thermodynamic state of the universe. In ordinary statistical mechanics, a thermal state defines an equilibrium distribution, and the dynamics of the system can be described by a modular Hamiltonian associated with that distribution. The time evolution generated by this modular Hamiltonian is thermal time. In ordinary physics, thermal time and ordinary time coincide because the universe is in approximate thermal equilibrium with respect to ordinary time. But in more general settings, thermal time could differ from clock time, or could even define a notion of time in regimes where no classical spacetime clock exists. For the early universe, the thermal time hypothesis suggests that the arrow of time, the fact that time has a direction, is connected to the thermodynamic state of the universe and its deviation from equilibrium. The low-entropy initial state of the universe near the Big Bang is what gives time its direction. Without that initial low-entropy state, there would be no arrow of time. The beginning of the universe is therefore not just the beginning of time in the sense of the first moment. It is the beginning of the arrow of time, the establishment of the thermodynamic gradient that gives the universe its directionality. This connection between time's arrow and the initial state of the universe is not new. It goes back to Boltzmann's struggles with irreversibility in the 19th century and was sharpened by Roger Penrose's whale curvature hypothesis. Penrose argued that the initial state of the universe must have had extremely low whale curvature, a measure of gravitational entropy, even though thermodynamics does not require this. The observed smoothness of the Big Bang initial state is not thermodynamically generic. It is extraordinarily special. And its specialness is what gives us an arrow of time, the tendency for entropy to increase, the existence of memory and causation and narrative. The puzzle is why the initial state was so special. This is related to the fine-tuning problem, but it is a different aspect of it. Not just the constants of nature, but the initial conditions of the universe were set in an extraordinarily non-generic way. A random initial state would be dominated by black holes and thermal radiation, not by a smooth, low-entropy hot plasma. The smooth initial state is enormously improbable from a statistical standpoint, which raises the question of how it came to be and whether a pre-Big Bang phase could have set those initial conditions. Cyclic and bounce models offer one answer, as we discussed in the first chapter. They propose that the initial conditions were set by the dynamics of a previous phase, so the specialness is inherited rather than miraculous. Inflation offers another answer, proposing that the initial conditions were generic at the start of inflation, and that inflation itself is what produced the smooth, flat universe we observe. But inflation shifts the specialness to the initial conditions of the inflationary phase, which must also be special in some way. The problem does not disappear. It migrates. The timeless picture offers a different kind of answer. If time is emergent, then asking why the initial state was special is asking why the quantum state of the universe, which has no temporal structure at the fundamental level, projects onto a particular classical history when we extract a semi-classical description. The specialness of the initial state becomes a question about the quantum state itself, about why the universe's wave function is what it is. The Hartle-Hawking no-boundary proposal is one attempt to answer this question, arguing that the wave function is determined by a specific geometric condition, smooth closure, and that this naturally selects histories with low entropy initial conditions. Whether that argument succeeds is technically disputed, but the approach at least frames the question in a way that can be investigated mathematically. The deep lesson of this chapter is that time may be less fundamental than it feels. Our experience of time, the sense of flow, of past, present, and future, of cause preceding effect, may be a macroscopic emergent phenomenon, like temperature or pressure, which has no fundamental microscopic counterpart. Temperature emerges from the statistical behavior of many particles, and it is perfectly real at the macroscopic level even though no single particle has a temperature. Similarly, time may emerge from the quantum correlational structure of many degrees of freedom, and it is perfectly real at the macroscopic level, even though the fundamental quantum state is timeless. If time is emergent in this sense, then the question of what existed before the Big Bang is not a question about an earlier time. It is a question about the structure of the quantum state in a regime where the emergence of time has not yet occurred. And that question, while still deep and difficult, is at least a question that could in principle be addressed by a complete theory of quantum gravity. It becomes a question about the wave function of the universe and about the conditions under which a semi-classical time emerges from it. The mystery remains, but it changes its address from before time to the structure of the timeless quantum state. This leads naturally to the question of what that timeless quantum state is, and whether it has any analog of a history or a structure that could be called a before in some generalized sense. That question points toward the most radical of our 7 theories, the ones that question not just time but the very nature of space, matter, and law. We carry the central question forward because the timeless picture does not answer it. It transforms it. Did anything exist before the Big Bang? If time is emergent, then the question becomes, what is the quantum state from which time and the Big Bang themselves emerge? And is that quantum state itself eternal, or does it too require an origin? Chapter 5 established that time may be emergent rather than fundamental, transforming our central question from what existed before the Big Bang to what is the timeless quantum state from which time and the Big Bang emerge. Now we push further into the most unsettling territory that cosmology permits. The question returns with its most stripped-down form. Did anything exist before the Big Bang? And if time began there, what could before even mean? If time is not fundamental, and if space may also be emergent, then the question of what came before the Big Bang may dissolve into a question about the structure of a mathematical object. And if the mathematical object is all there is, then the terror is not that we cannot find the answer. It is that the answer may turn reality into an abstraction that our intuitions were never built to hold. The block universe view, also called eternalism, is the first step on this road. It is not a new theory, but a natural consequence of taking special and general relativity seriously at the level of ontology. In special relativity, different observers moving at different speeds have different simultaneities. What is simultaneous for one observer is not simultaneous for another. This means that there is no single universal now, no privileged global instant that divides past from future for everyone. All moments in time exist on equal footing in the four-dimensional spacetime manifold. The past is not gone and the future is not unreal. They are simply other locations in spacetime, just as other places in space are real even when you are not there. In the block universe, the Big Bang is a particular region of spacetime, a region of high density and temperature located at one end of the cosmic time coordinate. It is not an event that happened and is now finished. It simply is, located at a particular spacetime address. Our experience of the Big Bang as a past event, of time flowing from it toward the present, is a feature of our macroscopic, thermodynamically governed experience. It is not a feature of the fundamental spacetime geometry. The fundamental geometry is static and complete. It is a four-dimensional block in which all events coexist. In this picture, before the Big Bang means at a different spacetime location than the Big Bang, one that is further in the past direction. If the Big Bang is the boundary of the spacetime manifold, then there is nothing before it, not because nothing existed, but because there is no spacetime region at that address. The question of what existed before the Big Bang is like asking what is at a location outside the grid of a map. The map does not say the location does not exist in some absolute sense. It says the map does not extend there. Whether reality extends there is a question about the geometry of spacetime, not about whether the block universe picture is correct. The block universe becomes more radical when combined with the idea that laws of physics themselves may be emergent or structural rather than externally imposed. In the standard picture, the laws of physics are rules that the universe obeys, imposed from outside or existing in some realm of abstract necessity. But this picture has always had a philosophical problem. Where do the laws come from? Why these laws rather than others? If the laws are external to the universe, then what enforces them? And if the laws are internal, then they are part of the universe and must themselves be explained. Lee Smolin and Roberto Mangabeira have argued for the reality of time and the evolution of laws, proposing that the laws of physics are themselves subject to change over cosmic timescales. In this view, the universe is not governed by eternal immutable laws, but by historically contingent regularities that emerged and evolved along with the universe itself. The laws we observe are not necessary truths but frozen accidents, the current state of a lawful process that has changed in the past and may change again in the future. This picture is deeply controversial and lacks a concrete mathematical framework, but it raises a genuine question that the block universe tends to suppress. Why are the laws of physics what they are, and is their fixity a fundamental fact or an approximation? The idea that laws could evolve connects to cosmological natural selection, proposed by Lee Smolin, which suggests that black holes give birth to new universes with slightly mutated constants. In this picture, the parameters of physics are subject to a kind of selection pressure analogous to biological natural selection. Universes that produce many black holes also produce many offspring, and their offspring inherit similar parameters. Over many generations, the distribution of parameters in the multiverse converges toward those that maximize black hole production. Since black hole formation requires long-lived stars, complex chemistry, and possibly life, this selection process could explain why our universe has parameters conducive to complexity. The proposal makes a testable prediction that our universe should be near a local maximum of black hole production for its parameter values, and attempts to test this have produced mixed results. It is controversial, but it is genuinely scientific in the sense that it makes falsifiable predictions, which is more than can be said for some multiverse proposals. The mathematical universe hypothesis, proposed by Max Tegmark, takes the abstraction one step further and arrives at the most radical destination in this chapter. Tegmark argues that our universe is not merely described by mathematics. It is a mathematical structure, not a physical system that happens to have mathematical properties, but a mathematical object that exists in the same way that the number 7, or the set of all prime numbers, exists. In this view, there is no distinction between physical existence and mathematical existence. To be a consistent mathematical structure is to be physically real. All mathematical structures exist, which means all possible universes exist, and we find ourselves in this one because it contains observers. The mathematical universe hypothesis is easy to misread as a poetic metaphor, and it is important to state what Tegmark actually means. He means it literally. The electrons and photons and dark matter are not physical things that happen to obey mathematical equations. They are mathematical relationships. The spacetime manifold is not a physical arena that has geometric properties. It is a geometric object in the mathematical sense. The difference between the physical world and mathematics is, in Tegmark's view, a psychological artifact of our position as observers inside one particular mathematical structure. From outside, if outside made sense, it would all look like mathematics. This hypothesis addresses the origin question in the most radical way possible. There is no origin because mathematical structures do not come into existence. They simply are, in the same timeless way that mathematical truths are timeless. The integers were not created at the Big Bang. 2 plus 2 equaled 4 before the universe existed, will equal 4 after it ends, and equals 4 in every possible universe. In the same way, if our universe is a mathematical structure, it does not come into being. It simply is, and it always was, in the sense that mathematical structures exist timelessly. The Big Bang is a feature of the structure, a particular region with particular properties, but the structure itself has no origin. The appeal of this view is that it sidesteps the problem of why there is something rather than nothing. If mathematical structures necessarily exist, as mathematical Platonists argue, then a universe that is a mathematical structure exists necessarily. There is no need to explain why it came into being because it did not come into being. It simply is. The question of what came before the Big Bang dissolves because the Big Bang is a location in the mathematical structure, not an event in an external time. There is no external time for it to occur in, and there is no before because before requires an external time. The problems with this view are profound and multiple. First, it is unclear what it means for a mathematical structure to be physically real. The standard view is that mathematical structures exist abstractly, in a way that is independent of any physical instantiation. But physical existence seems to be something over and above abstract existence. A universe that exists physically contains experience, causation, energy, and the kind of reality that can be bumped into. A mathematical structure that exists abstractly does not obviously have any of these properties. Tegmark's claim that physical existence just is mathematical existence is a bold assertion, not a demonstrated fact, and it requires a theory of how experience and causation arise from abstract mathematical structure. Second, the mathematical universe hypothesis predicts that all mathematical structures are real, which means an enormous range of universes exist with an enormous range of properties. The measure problem which we encountered in the multiverse chapter returns here in its most severe form. With infinitely many mathematical structures, each containing infinitely many observers, defining typical observations requires a measure over the space of all mathematical structures. No such measure has been convincingly defined, and different choices lead to wildly different predictions about what we should expect to observe. Third, the hypothesis makes it very hard to explain why physics is as simple as it is. The universe we observe has a remarkably compact mathematical description. The standard model of particle physics and general relativity together can be written on a few pages. In a landscape of all mathematical structures, most are vastly more complex, containing arbitrary and inexplicable patterns. Why do we find ourselves in one of the simple ones? The usual anthropic answer, that simple universes may be more likely to contain observers, is not convincing because many complex universes also contain observers, and the notion of more likely requires a measure that we do not have. Despite these problems, the mathematical universe hypothesis identifies something important. The question of why mathematics is so effective at describing the physical world, what Eugene Wigner called the unreasonable effectiveness of mathematics, suggests a deep connection between mathematical structure and physical reality. Whether that connection goes all the way to identity, as Tegmark proposes, or stops short of it, the connection itself demands explanation. And any explanation of that connection is relevant to the question of what preceded the Big Bang, because the laws of physics that govern the Big Bang are mathematical in form, and the origin of those laws is part of the origin problem. A softer version of the mathematical universe idea focuses not on all mathematical structures, but on a specific kind of structure, the class of self-referential or self-consistent structures that can describe themselves. Kurt Gödel's incompleteness theorems showed that sufficiently powerful formal systems contain statements that cannot be proven true or false within the system itself. This places a fundamental limit on what any mathematical system can know about itself. Applied to the universe, this suggests that there are facts about the universe that cannot be derived from within the universe's own laws, which is a kind of cosmic incompleteness. Whether this incompleteness is relevant to the origin problem is speculative, but it adds another layer to the question of why the universe's laws are what they are, and whether those laws could have been otherwise. The inflationary landscape of string theory is sometimes described in terms reminiscent of the mathematical universe hypothesis. The enormous number of possible string vacua, each with different low-energy physics, looks like a realization of many different mathematical structures within one overarching framework. But the string landscape is not the same as the mathematical universe hypothesis. The string landscape is a specific claim within string theory about the space of possible vacuum states. It is bounded by the consistency requirements of string theory, which are specific and not obviously satisfied by all mathematical structures. The mathematical universe hypothesis is far more general, claiming that all consistent mathematical structures are physically real. The string landscape is a subset of mathematical structures selected by the requirement of consistency with string theory, and string theory itself is just one candidate theory among many. The anthropic landscape approach uses the string landscape as a population of possible universes and argues that we observe particular values of the constants because we exist in a region where those values are compatible with observers. The cosmological constant is the leading example. The observed value of the cosmological constant is about 120 orders of magnitude smaller than naive field theory estimates. This enormous discrepancy is one of the hardest problems in theoretical physics. If the landscape contains vacua with a range of values, including very small positive values, then the anthropic argument says we observe a small positive value because larger values would prevent galaxy formation and smaller or large negative values would cause a rapid recollapse. The argument is uncomfortable, but it has a specific quantitative content, and the predicted range of the cosmological constant is at least in the right ballpark, which is more than naive field theory can claim. The difficulty is that the landscape argument requires a measure over the string vacua, and defining that measure is as hard as the measure problem in eternal inflation. Different measures give different predictions for the distribution of the cosmological constant, and without a definite measure, the argument cannot be made precise. Attempts to define the measure using de Sitter entropy, causal patch counting, or other methods each have their own assumptions and their own predictions, and it is not clear which, if any, is correct. The landscape is a framework for thinking about the origin of the constants, but it is not yet a predictive theory in the quantitative sense that would be needed to test it convincingly. There is also the swampland program in string theory, which aims to identify which effective field theories can be consistently embedded in string theory and which cannot. The swampland is the set of effective theories that look consistent from a low-energy perspective, but are actually inconsistent with a full quantum gravitational completion. If the swampland conjectures are correct, then many effective theories that we might think could be valid are actually excluded, which would dramatically reduce the size of the landscape and make more specific predictions about which vacua are actually possible. The swampland program is an active area of research, and its conjectures are being tested against both theoretical consistency requirements and observational data. If the swampland program succeeds in significantly restricting the landscape, it would change the measure problem by changing the space over which the measure is defined. One of the swampland conjectures is the de Sitter conjecture, which suggests that stable de Sitter space, a space with a positive cosmological constant and accelerating expansion, may not be consistently realizable in string theory. Our universe appears to be in a de Sitter-like phase of accelerating expansion driven by the observed positive cosmological constant. If the de Sitter conjecture is correct, then our universe cannot be in a true de Sitter vacuum. It must be in a metastable state that will eventually decay, or in a slowly rolling state rather than a true minimum. This would have implications for the long-term future of the universe and for the structure of the landscape, potentially excluding the region of vacua where eternal de Sitter expansion is possible. The question of what all this means for the origin of the universe is that it changes the prior over possible universes. If the swampland significantly restricts which vacua are consistent, then the space of possible universes is smaller and more structured than the raw landscape suggests. The question of why we exist in this universe rather than another becomes more tractable because the space of alternatives is smaller. But it does not become trivial because even a restricted landscape is a large space, and the question of why any consistent vacuum is realized rather than another remains. We have arrived at the edge of what current physics can say. The mathematical universe hypothesis is more a philosophical position than a scientific theory, in the sense that it is not clear what observations could falsify it. The string landscape is a scientific framework, but one that lacks a definite measure, and therefore cannot make precise predictions about which vacuum we should expect to observe. The Swampland program is an attempt to sharpen the predictions of string theory, but it is still developing, and its conjectures are not yet fully established. What we have is a set of frameworks, each addressing part of the origin problem, none solving it completely. The terror of this chapter is not that we lack answers. It is that the answers we might find could make reality feel less real. If the universe is a mathematical structure, then the meaning of existence changes. If all mathematical structures are real, then reality is vastly larger than anything we can observe, and our universe is one element in an infinite abstract library. If time is not fundamental, then the story of the universe, with its beginning, middle, and eventual end, is a story we tell from inside a timeless structure. Our narrative of origins, of before and after, of cause and effect, may be a useful fiction that our macroscopic minds impose on a reality that has no beginning, no time, and no story. That is a form of terror that is hard to name. It is not the fear of death or of emptiness. It is the fear that meaning and narrative are not features of the universe but of our minds, and that the universe, viewed from a sufficiently fundamental level, is not a story at all. It is a structure. And structures do not have beginnings. They simply are, but we are not done because one more possibility remains. What if the universe is not a structure that simply is, but a necessity, something that could not have been otherwise, not contingently but necessarily? That question leads to the final chapter, where we ask not just what preceded the universe, but whether the universe could have failed to exist. And whether the answer to that question is yes or no, it changes everything about what existence means. We have moved across 6 chapters from dying predecessor worlds to quantum emptiness, from multiverse machinery to brain impacts, from timeless cosmologies to block time and mathematical structures. Each step has tightened the same question. Did anything exist before the Big Bang? And if time began there, what could before even mean? Now we take the final step, and it leads not outward to a larger stage, but inward to the question of necessity itself. The central question in its final form is not what existed before the Big Bang. It is whether the universe could have not existed, whether existence is contingent, a matter of specific conditions being met, or necessary, a fact that holds regardless of conditions. The distinction matters because a contingent universe requires an explanation of why these conditions were met rather than others. A necessary universe requires no such explanation because there are no alternatives to compare it to. The idea that the universe exists necessarily has roots in the ontological argument in philosophy, which attempted to prove the existence of God from the concept of a most perfect being whose essence includes existence. The cosmological version of necessity is different. It does not argue that God exists necessarily. It argues that the universe, or the mathematical structure that the universe is an instance of, exists necessarily, and it tries to ground that necessity not in theological intuition, but in mathematical logic and in the structure of physical law. The strongest version of this idea is connected to the modal realist philosophy of David Lewis, who argued that all possible worlds are equally real. In Lewis's framework, our universe is one of infinitely many possible worlds, each equally real, each containing whatever its laws and initial conditions specify. The sense in which other worlds are real is the same sense in which our world is real. They are not imaginary or merely logical possibilities. They exist concretely and separately from each other. We happen to be in this world, and its particularity seems important to us, but from the view of all possible worlds taken together, it is one among countless equally real alternatives. Lewis's modal realism is a philosophical position that is difficult to refute on purely logical grounds, but equally difficult to motivate from a scientific standpoint. It makes no specific physical predictions and is not connected to any particular theory of quantum gravity or cosmology. Its relevance to the origin question is indirect. If all possible worlds are real, then the question of why this world exists rather than another does not arise, because all worlds exist. The selection problem, why these laws, these initial conditions, this universe, is dissolved by multiplication. Every alternative is real, so there is nothing to explain about why this one is actual. The scientific multiverse, whether inflationary or from the string landscape, can be seen as a physically grounded version of a similar idea. Not all logically possible universes, but all universes consistent with the underlying framework, whether string theory or eternal inflation, are realized. The selection problem is softened by the same logic. We observe a universe with these properties because we are observers, and observers require certain conditions. The conditions narrow the possible universes we could observe, and among those, we find ourselves in one. No further explanation is needed or available. But the selection problem does not fully dissolve because we still need to explain the framework itself. Why eternal inflation? Why string theory? Why quantum mechanics? Why any laws at all? These questions point toward a regress that has no obvious stopping point. Every explanation assumes a framework, and the framework itself requires explanation. The hope for necessity is that at some deepest level, there is a framework that explains itself, a set of laws or a mathematical structure whose existence follows from its own logical properties. Such a framework would be necessary in the strongest sense because its non-existence would be logically contradictory. Whether any such self-explaining framework exists is unknown, and it may be unknowable in principle. But there are hints in the structure of physics that something like this may be at work. The laws of physics have a mathematical elegance and a symmetry that suggests they are not arbitrary. The standard model of particle physics is built on specific symmetry groups, and those groups are not chosen for aesthetics. They are the ones consistent with the observed particles and interactions. General relativity follows from the requirement that physics be the same for all observers, a principle of general covariance. Quantum mechanics follows from the requirement that probabilities be consistent and non-negative, together with certain algebraic requirements on observables. Each of these laws looks like it follows from a small number of deep principles, rather than being chosen from an arbitrary menu. This does not prove the laws are necessary, but it suggests they may be more constrained than they appear. If the laws of physics follow from a small set of very general principles, and if those principles themselves follow from the requirement of logical consistency, then the laws might be close to necessary. Not necessary in the sense that no other laws are conceivable, but necessary in the sense that any universe capable of containing self-consistent observers must have something like these laws. The anthropic argument connects to this because observers place constraints on the universe they inhabit. A universe that cannot support self-referential information processing systems cannot contain anything like a physicist asking origin questions. If we require the universe to be able to ask questions about itself, then we impose a set of constraints on the laws that may be quite restrictive. The universe must be complex enough to support local computation, but not so chaotic that patterns cannot persist. It must have an arrow of time to support memory and prediction. It must have forces that allow structure formation over the range of scales relevant to biological complexity. These requirements, if pressed hard enough, might narrow the space of possible universes considerably. This is the anthropic constraint taken seriously as a selection principle rather than a philosophical dodge. If we are rigorous about what a universe must be able to do to contain observers, and if we use that requirement as a constraint on the laws, then the selection is not arbitrary. It follows from the requirement of self-reference. The universe must be structured in a way that allows parts of it to accurately model other parts of it, which requires sufficient regularity, sufficient complexity, and a specific relationship between the simplicity of the laws and the complexity of the outcomes they generate. Universes with random or maximally complex laws cannot support this because there would be nothing to model. Universes with trivially simple laws cannot support it because there would be nothing interesting to happen. This argument does not prove that our universe is necessary. It suggests that the class of observer-containing universes is significantly smaller than the class of all mathematically consistent universes, and that our universe may be in some sense typical within that smaller class, if a measure can be defined over it. The measure problem returns, but now in a form where the relevant space is not all string vacua, but all observer-containing universes, which is a different and possibly more tractable space. There is a deep circularity lurking here that cannot be fully escaped, and acknowledging it is part of intellectual honesty. The argument uses observers as a selection criterion, but observers are physical systems defined within the universe's laws. To say the universe must have laws that support observers is to say the universe must have laws that support systems defined by those laws. This is not obviously circular in a vicious sense, because it simply says that the laws must be self-consistent in a specific way. But it does mean that the argument is not fully external to the universe it is trying to explain. We are using our existence to constrain the explanation of our existence, which is inevitable, but also limits what the argument can establish. The most honest thing we can say at the end of this journey is that the question of what preceded the Big Bang has been transformed, but not answered. We began with a seemingly simple historical question, what came before the earliest moment we can reconstruct, and we have found that the question dissolves into deeper questions about time, causality, existence, and necessity. Each answer we have found has pushed the mystery back one step or transformed it into a different kind of mystery. From dying predecessor worlds, we learned that the Big Bang may be a transition rather than a beginning, but we needed to explain what drove the preceding phase. From quantum emptiness, we learned that nothing is never truly nothing, but we needed to explain the quantum framework that makes nothing productive. From the multiverse, we learned that our universe may be one of many, but we needed a measure to make sense of probability in an infinite space. From brain collisions, we learned that the Big Bang may be an impact rather than a creation, but we needed to explain the bulk and its initial conditions. From timeless cosmologies, we learned that time may be emergent, but we needed to explain the timeless quantum state. From the block universe and mathematical structures, we learned that existence may be necessary rather than contingent, but we needed to explain why this structure rather than another, or why anything rather than nothing. At each step, the mystery has deepened and the vocabulary has changed. The question that began as a cosmological question about origins has become a question about the nature of time, the nature of laws, and the nature of existence itself. It has become a question that stands at the intersection of physics, mathematics, and philosophy, and it cannot be fully addressed by any one of these disciplines alone. What physics can offer is specific, testable proposals that make predictions about what we should observe if particular origin stories are correct. The primordial gravitational wave background distinguishes high-energy inflation from low-energy alternatives. The statistics of the cosmic microwave background constrain pre-Big Bang models through their predicted spectra and non-Gaussianities. The spatial curvature constrains quantum creation proposals. The patterns of large-scale structure constrain cyclic and bounce models. None of these tests has yet decisively confirmed one story over all others, but each new generation of instruments brings us closer to answers. The Simons Observatory, CMB-S4, the Euclid Satellite, the Vera-Rubin Observatory, and the Einstein Telescope are among the experiments that will probe these questions with unprecedented precision over the coming decades. What mathematics can offer is the vocabulary and the tools to make the questions precise. The timeless Wheeler-DeWitt equation, the path integral over geometries, the spin foam amplitudes, the CDT simulations, and the string landscape are mathematical frameworks that give the questions about origin a technical form. They allow us to distinguish well-posed questions from ill-posed ones, to identify hidden assumptions, and to calculate consequences of proposed answers. Without this mathematical precision, the questions would remain philosophical speculation. With it, they become part of science, even when the science is incomplete. What philosophy can offer is the clarification of concepts and the examination of assumptions. The distinction between Lorentzian and Euclidean time, the difference between several kinds of nothing, the question of whether time is fundamental or emergent, the analysis of what before means when time may not exist, these are conceptual distinctions that physics alone cannot make. They require the careful examination of language and presupposition that is philosophy's specific contribution. When physicists say the universe emerged from nothing, philosophers can ask what kind of nothing, and the answer changes the physics. The synthesis of all three approaches is what cosmology of origins requires. It is not enough to have precise measurements without theoretical frameworks to interpret them. It is not enough to have beautiful mathematics without observable predictions. It is not enough to have conceptual clarity without the discipline of empirical constraint. Origin cosmology is at the frontier where all three must work together, and that frontier is where the question is most alive. The universe may have had a predecessor, or it may have emerged from a quantum state that was not in time, or it may be one bubble in an eternal sea of inflation, or it may be the result of a brain collision in a higher dimensional bulk, or it may be a region of a timeless mathematical structure, or it may be necessary, the only universe that could exist given the requirement of self-consistency. Or it may be something else entirely, something that our current concepts cannot yet frame, waiting for a revolution in understanding as profound as the revolutions that brought us quantum mechanics and general relativity. What we know for certain is this: the universe exists. It has been doing so for nearly 14 billion years according to our clocks. It began in the sense that our current descriptions fail at a particular early time, in a state of extraordinary simplicity and extraordinary smoothness that gave rise to everything we observe. That beginning is written into the sky in the form of the cosmic microwave background, in the distribution of galaxies, in the abundance of light elements, and in the gravitational waves we are learning to detect. It is a beginning that is real in every empirical sense, even if its ultimate nature remains beyond our current understanding. The question of what came before that beginning is not a question we can answer today, but it is a question we can ask more precisely than ever before, and the asking has already changed how we understand time, causality, and existence. The universe began with a Big Bang, or something that looks like one from the inside. Before that, if before means anything, there may have been something or nothing, or the question may be the wrong question. That uncertainty is not a failure of science. It is the horizon of science, the edge where the known meets the unknown, and where the most interesting questions live. The Big Bang was not, in the end, a simple beginning. It was a question dressed up as an explosion. And we are still learning to read the question that the universe wrote in fire at what may or may not have been its start. The question has been asked in 7 different languages now, each one a different theory, each one a different way of reaching toward the same darkness. We have followed the mathematics of bouncing universes, the physics of quantum creation, the geometry of inflating multiverses, the dynamics of colliding brains, the emergence of time from timeless equations, and the radical possibility that existence itself is mathematical and necessary. Each approach has illuminated part of the problem while casting new shadows elsewhere. Now we return to where we started, not to repeat the journey, but to see what the journey has done to the question itself. The central question one final time: did anything exist before the Big Bang? And if time began there, what could before even mean? The question sounds the same as it did at the beginning, but it is not the same question. The journey has changed what the question contains. Before we began, the question felt like a historical one, a question about what happened earlier, about what events preceded the earliest event we know. Now it is clear that the question contains at least 4 separate sub-questions, each of which requires a different kind of answer. The first is whether the universe had a prior physical phase, an earlier state connected to our hot Big Bang by some physical process. The second is whether time existed before the Big Bang in any meaningful sense, or whether time itself began with or after the Big Bang. The third is whether there is any meaningful sense of before in a regime where time may not be fundamental. The fourth is whether existence itself requires an explanation, or whether the universe's existence is necessary, in a sense that makes the question of what came before it dissolve. These 4 questions are not the same question, and conflating them is one of the most common sources of confusion in popular discussions of cosmology. The first question is scientific in a relatively straightforward sense. It asks about physical processes and physical states, and it can in principle be addressed by measurements and by physical theories. The second question is also scientific, but requires a more careful handling of what time means in the context of quantum gravity. The third question is at the intersection of physics and philosophy, requiring both technical input from quantum gravity and conceptual analysis of what notions like before and cause mean in timeless frameworks. The fourth question is primarily philosophical, though physics informs it, and it may never have a purely empirical answer. Separating these questions is not a way of avoiding difficulty. It is a way of being honest about what kind of difficulty we are facing. Origin cosmology tends to blur these questions together, and the blurring makes the field look more mysterious than it needs to be while also obscuring genuine mysteries that deserve more attention. The question of whether the universe had a prior physical phase is hard but tractable. The question of why there is something rather than nothing in the deepest philosophical sense may not be tractable at all, but it is a different question, and treating it as if it were the same as the physical question does neither a service. With that clarification in place, we can take stock of what the 7 theories have established, what they have failed to establish, and what the prospects for future progress look like. This is not a summary in the sense of a simplified repetition. It is an assessment of the state of the field, honest about its limitations, and honest about its genuine achievements. The genuine achievement of loop quantum cosmology and related bounce models is to show that the classical singularity at the Big Bang is not an inevitable feature of quantum gravity. In the classical theory, the singularity is a theorem, a consequence of the Penrose-Hawking results applied to an expanding universe run backward. But the classical theory breaks down at the scales where the singularity would occur, and in a theory where space has a discrete quantum structure, the singularity is replaced by a bounce. This is a significant conceptual advance because it shows that what looks like a beginning in classical physics may be a transition in quantum physics. The mathematics is under control in simplified models, and the qualitative picture is robust across several different formulations. The limitation of these models is that they are still simplified. The minisuperspace approximation treats the universe as having only a few degrees of freedom, which makes the mathematics tractable, but which ignores the full complexity of quantum geometry. In homogeneities, the variations in density and structure that are crucial for understanding the seeds of galaxies are added perturbatively after the fact rather than being fully quantum from the start. The question of what the full quantum theory of gravity looks like and whether bounce models remain valid in the full theory is open. The connection between loop quantum cosmology and the full theory of loop quantum gravity is not yet complete, and it is possible that the full theory changes the picture in important ways. The genuine achievement of quantum creation proposals, the Hartle-Hawking no-boundary wave function, and Vilenkin's tunneling proposal, is to show that the initial state of the universe can in principle be a calculable quantity rather than a free parameter that must be specified by hand. In ordinary physics, we specify initial conditions and then evolve them forward using the laws. In quantum cosmology, the idea is that the laws themselves determine the initial conditions through a quantum boundary condition that selects the wave function of the universe. This is a profound shift in how we think about the relationship between laws and initial conditions. If the no-boundary proposal is correct, then asking why the universe started in such an unusually smooth, low-entropy state is not a question about contingent history. It is a question about the consequences of a fundamental quantum principle. The limitation of these proposals is that they are not unambiguously defined. The no-boundary wave function requires a sum over geometries, and defining that sum precisely turns out to be technically very difficult. Different ways of regulating the sum give different answers, and recent work has raised questions about whether the standard interpretation of the no-boundary proposal gives a wave function that is peaked on the classical histories we observe, or whether it is peaked on different pathological histories. Vilenkin's tunneling proposal has its own ambiguities in defining what constitutes the tunneling process in the absence of a classical spacetime. Both proposals are promising frameworks, but neither is a complete, unambiguous theory, and the question of which one is correct, if either, cannot yet be answered. The genuine achievement of eternal inflation and the multiverse is to show that fine-tuning problems, the extraordinary specificity of the constants of nature and the initial conditions, are at least in principle addressable without invoking a special creative act. If the laws of physics are environmental, varying across different regions of a vast multiverse, then the constants we observe are the result of a selection process rather than a fundamental necessity. This reframes the fine-tuning problem from a miracle to a statistical question, from why were we so lucky to how large must the multiverse be to make our luck unsurprising. That reframing is intellectually significant even if the multiverse cannot yet be directly confirmed. The limitation is the measure problem, which is severe enough to make the multiverse's predictions ambiguous. Without a definite measure over the multiverse, statements about the probability of observing particular constants are not well defined. The multiverse can accommodate almost any observation by choosing an appropriate measure, which means it risks becoming unfalsifiable in practice, even if it is falsifiable in principle. Some physicists regard this as a temporary technical problem that a more complete theory will resolve. Others regard it as a sign that the multiverse is not a scientific theory in the relevant sense. The debate is genuine and has not been resolved. The genuine achievement of ekpyrotic and brane collision models is to provide a concrete alternative to inflation for explaining the smoothness and flatness of the universe, and for generating a nearly scale-invariant spectrum of primordial perturbations. Having a well-developed alternative to inflation is scientifically valuable because it sharpens what we must measure to distinguish between different early universe theories. The prediction of very small primordial gravitational waves distinguishes ekpyrosis from many inflation models, and upcoming CMB experiments will put this prediction to a sharp test. If a primordial gravitational wave background is detected at a level inconsistent with ekpyrosis, the brane collision picture would be in serious trouble. If no gravitational waves are detected at the level many inflation models predict, inflation models would be squeezed and ekpyrosis would gain credibility. The limitation is the bounce problem, which has not been convincingly solved. Transitioning smoothly from contraction to expansion without producing a singularity requires new physics beyond general relativity, and the specific form of that new physics is not established. The higher dimensional brane collision picture replaces the singularity with a collision event, but the dynamics of that collision at the moment of maximum compression are not under good mathematical control. String theory provides the framework, but the relevant regime is strongly coupled and far from where perturbative string theory is reliable. The model is suggestive and mathematically motivated, but incomplete at its most crucial point. The genuine achievement of emergent time and quantum gravity approaches, including loop quantum gravity, spin foams, and causal dynamical triangulations, is to show that time may not be a fundamental feature of the deepest physical description. The Wheeler-DeWitt equation and related structures in quantum gravity naturally produce a timeless description at the fundamental level, with time emerging as an approximate concept in the semi-classical limit. This changes the question of what came before the Big Bang from a question about earlier times to a question about the structure of the timeless quantum state. The question is transformed rather than answered, but the transformation is clarifying because it shows which aspects of the question are artifacts of our time-based intuitions and which are genuinely physical. The The limitation is that the emergent time picture is not yet fully developed. The mechanism by which classical time emerges from a timeless quantum state, whether through the page-router's mechanism, through decoherence, or through some other process, is understood in simple models but not in full quantum gravity. The transition from the timeless quantum regime near the Big Bang to the classical spacetime we observe at late times is not described by any complete theory. The framework is suggestive and theoretically motivated, but the detailed mechanism of time emergence is an open problem. The genuine achievement of the mathematical universe hypothesis and related ideas about necessity is to force the question of existence to its most fundamental form. Why is there something rather than nothing? Why these laws? These questions have always lurked behind cosmology, but the mathematical universe hypothesis makes them precise enough to engage with analytically. If the universe is a mathematical structure, then its existence is of the same kind as the existence of mathematical objects, which some argue is necessary rather than contingent. This does not solve the problem, but it changes its character from a causal question to a mathematical question. Instead of asking what caused the universe, we ask why this mathematical structure is instantiated as a physical universe, or equivalently, why there is a distinction between mathematical existence and physical existence at all. The limitation is that the mathematical universe hypothesis is extremely hard to test and may be impossible to falsify. It makes a sweeping claim about the nature of existence that goes far beyond what any observation could establish. It also faces the serious objection that most mathematical structures are vastly more complex than our universe, making it unclear why observers should find themselves in a relatively simple one without a measure over mathematical structures that strongly favors simplicity. And the measure over all mathematical structures is even harder to define than the measure over string vacua or inflationary bubble universes. The mathematical universe hypothesis is a genuine philosophical position with serious scientific motivations, but it is not yet a scientific theory in the sense of making testable predictions that would distinguish it from alternatives. Taking stock of these achievements and limitations, what is the honest assessment of where origin cosmology stands? The field is in an unusual position. It has made genuine progress in understanding what the alternatives are and what each alternative predicts. It has developed mathematical frameworks that give the questions precise form. It has identified observational tests that can distinguish between at least some of the alternatives. But it has not converged on a single answer, and the deepest questions remain open. This is not a failure of the field. It is a reflection of the genuine difficulty of the problem. The question of what came before the Big Bang is not just a difficult scientific question. It is a question that pushes against the limits of what science can address. Science is an empirical enterprise, constrained by what can be observed and tested. The regime before the Big Bang, if there is one, may be permanently inaccessible to direct observation. Even if signals from a pre-Big Bang phase survive into our observable universe, they would be faint and ambiguous, difficult to distinguish from noise or from the effects of early universe physics that we do not yet fully understand. The honest scientist must acknowledge that definitive answers to origin questions may not be achievable within the current paradigm, and possibly not within any empirical paradigm. But this acknowledgement is not defeatism, and it is not an invitation to abandon the enterprise. It is a recognition that origin cosmology is at the frontier of what science can do, and frontiers are where the most important work happens. The history of science is full of questions that seemed permanently beyond reach and turned out not to be. The structure of atoms, the composition of stars, the age of the universe, the existence of other galaxies, the nature of black holes, all of these seemed inaccessible until new instruments, new theories, and new conceptual frameworks made them accessible. The question of what came before the Big Bang may turn out to be similarly transformable, if not by direct observation, then by the indirect constraints that precision cosmology can impose. The instruments coming online in the next decade will probe the primordial universe with unprecedented precision. The CMB Stage 4 experiment, known as CMB-S4, will measure the temperature and polarization of the cosmic microwave background with sensitivity that could detect primordial gravitational waves at a level of the tensor scalar ratio of about 0.1, or place upper limits that would rule out large classes of inflation models. The Simons Observatory will provide intermediate steps toward that sensitivity. Together, these experiments will either detect the gravitational wave background predicted by many inflation models, or push the upper limits low enough to challenge those models, while leaving room for alternatives like ekpyrosis or models with very low energy scales of inflation. The Euclid satellite, launched in 2023, and the Vera Rubin Observatory's legacy survey of space and time, beginning science operations in the mid-2020s, will map the large-scale structure of the universe with statistical power that far exceeds anything previously achieved. These surveys will measure the power spectrum of matter fluctuations, the clustering of galaxies, the abundance of galaxy clusters, and the statistics of gravitational lensing with enough precision to constrain the primordial power spectrum, the amount of primordial non-Gaussianity, and the equation of state of dark energy. Non-Gaussianity is particularly important for distinguishing different origin scenarios because different mechanisms for generating primordial perturbations produce different non-Gaussian signatures. Gravitational wave astronomy through the LIGO Virgo KAGRA network, and eventually the space-based LISA mission will open a new window on the early universe. A stochastic gravitational wave background from the very early universe, whether from inflation, from phase transitions, or from other early universe processes, would be detectable by these instruments if the background is strong enough at the relevant frequencies. LISA, operating at millihertz frequencies, is particularly sensitive to gravitational waves from cosmological phase transitions around the electroweak scale, which could have occurred in the early universe and could provide information about physics at energies far above what particle colliders can reach. The Einstein Telescope and Cosmic Explorer, next-generation ground-based gravitational wave detectors planned for the 2030s and beyond, will operate at frequencies and sensitivities that could detect gravitational waves from the very early universe at energy scales approaching the end of inflation. Together with CMB polarization measurements, these gravitational wave observations could triangulate the energy scale of inflation and the mechanism of reheating, providing information about the earliest moments of the hot Big Bang phase. The combination of CMB and gravitational wave observations would constitute a multi-wavelength, multi-messenger picture of the early universe that goes far beyond what either approach can achieve alone. These observational programs will not directly answer the question of what came before the Big Bang, but they will significantly constrain the answer. If primordial gravitational waves are detected at a level consistent with large-field inflation, then models like ekpyrosis and many quantum creation proposals would be strongly challenged. If no gravitational waves are detected down to very low levels, then high-energy inflation would be disfavored, and alternatives would become more competitive. If non-Gaussianity is detected at a level above what simple single-field inflation predicts, then multi-field models, entropic mechanisms, and other complex early universe dynamics would become more plausible. Each measurement outcome would narrow the space of viable origin theories, even if it would not uniquely determine one. On the theoretical side, the most important developments expected in the coming years involve advances in quantum gravity. The holographic principle, formalized in the anti-de Sitter space conformal field theory correspondence discovered by Juan Maldacena in 1997, has provided a framework for thinking about quantum gravity in which the gravitational theory in a bulk space is equivalent to a quantum field theory on its boundary. This correspondence has been enormously productive for understanding quantum gravity in the anti-de Sitter setting, where the mathematics is tractable, and it has generated insights about black holes, quantum information, and the emergence of spacetime from entanglement that may be relevant to cosmology. The application of holographic ideas to cosmology is not straightforward because our universe has a positive cosmological constant and is asymptotically de Sitter rather than anti-de Sitter. Anti-de Sitter space has a boundary at spatial infinity where the conformal field theory lives, which makes the holographic dictionary well-defined. De Sitter space does not have a simple spatial boundary, and defining holography in de Sitter is technically and conceptually harder. Progress on de Sitter holography would be enormously valuable for cosmology because it might provide a non-perturbative definition of quantum gravity in a setting relevant to the early universe, where a phase of de Sitter-like inflation may have occurred, and to the late universe, where accelerated expansion driven by the cosmological constant is ongoing. The connection between quantum information theory and quantum gravity, developed through concepts like entanglement entropy, quantum error correction, and quantum complexity, has produced a new perspective on the emergence of spacetime from quantum mechanics. The Ryutak-Yanagi formula relates the entropy of a region in the conformal field theory to the area of a minimal surface in the bulk gravitational theory, connecting quantum information to geometry in a precise way. Extensions of this formula have shown that the reconstruction of bulk spacetime from boundary data involves quantum error correction, and that the connectivity of spacetime may be related to the quantum entanglement structure of the boundary theory. These ideas are still being developed, but they suggest that spacetime is not fundamental, but emerges from a quantum informational structure. If spacetime emerges from quantum entanglement, then the question of what came before the Big Bang becomes a question about the entanglement structure of the quantum state in a regime where classical spacetime has not yet emerged. The Big Bang would correspond to the point at which a classical spacetime description becomes valid, emerging from a pre-classical quantum state in which the familiar notions of time and space do not apply. The question of before would be a question about the quantum informational structure of the pre-classical state, which may have a definite answer within a complete quantum gravity theory, even if it has no answer in terms of classical spacetime. The ER equals EPR conjecture, proposed by Maldacena and Susskind, connects quantum entanglement to spacetime geometry by suggesting that entangled pairs of particles are connected by Einstein-Rosen bridges, which are wormholes in the spacetime geometry. In the anti-de Sitter context, this means that two entangled copies of the boundary conformal field theory correspond to a spacetime in which the two boundaries are connected by a wormhole. The conjecture suggests a deep connection between quantum information, quantum entanglement, and the topology of spacetime. If spacetime connectivity is related to entanglement, then the creation of new spacetime regions is related to the establishment of new entanglement, and the origin of the universe might be related to the creation of entanglement in a pre-geometric quantum state. These ideas are speculative and far from established, but they point toward a future theory in which the origin of the universe is described in terms of quantum information rather than in terms of classical geometry. In such a theory, the question of what came before the Big Bang would be a question about the quantum informational state of the universe before classical spacetime emerged. The answer might be that the preclassical state has no temporal ordering at all, so before has no meaning, or it might be that the quantum informational state has its own kind of ordering that constitutes a generalized notion of before, different from but related to the classical temporal concept. The progress of science toward understanding the origin of the universe is therefore occurring on multiple fronts simultaneously. Observationally, precision cosmology is constraining the properties of the primordial universe with ever greater accuracy. Theoretically, quantum gravity research is developing frameworks in which the earliest phase of the universe can be described consistently. Conceptually, the analysis of what time, causality, and existence mean at the quantum gravitational level is clarifying what questions can and cannot be meaningfully asked about origins. And philosophically, the examination of necessity, contingency, and the relationship between mathematical and physical existence is sharpening the deepest questions about why there is a universe at all. Progress on all these fronts simultaneously is unusual in physics. Most of the time, theoretical and observational developments proceed somewhat independently, with theory far ahead of observation in some areas and observation revealing unexpected phenomena that theory must scramble to explain. In origin cosmology, theory and observation are proceeding in tandem, with each new theoretical framework suggesting new observational tests, and each new observational result constraining and redirecting theoretical development. This productive tension between theory and observation is the hallmark of a maturing field, even if the field is maturing around questions that may never be fully answerable. What would constitute a satisfying answer to the question of what came before the Big Bang? The answer depends on what kind of satisfaction we are seeking. If we are seeking empirical certainty, a direct observation of the pre-Big Bang state, the answer is almost certainly that we will never achieve full satisfaction, because the Big Bang's hot phase has erased most of the information about what preceded it. If we are seeking theoretical completeness, a single consistent theory that describes the universe from before the Big Bang to the far future without any approximations or ambiguities, the answer is that we are very far from that, and may remain so for a very long time. If we are seeking conceptual clarity, an understanding of what the question means and what kinds of answers are possible, the answer is that we have made real progress and continue to do so. The most honest and most satisfying response to the question may be the one that acknowledges all three dimensions. The universe may have had a prior physical phase, or it may have emerged from a quantum state without a classical precedent, or the concept of before may not apply to the earliest stages of existence. We have specific proposals for each of these possibilities, and we have observational and theoretical tools to constrain them. The question is alive and productive, generating real science with real consequences for our understanding of the universe. And the question is deep enough that its complete resolution may require not just new data but new concepts, not just better instruments but better ideas. The history of cosmology supports this optimism. A century ago, we did not know whether other galaxies existed. We did not know the universe was expanding. We did not know how stars generate energy or how old the universe is. We did not know about dark matter or dark energy. We did not know about the cosmic microwave background or the detailed structure of primordial perturbations. Each of these discoveries required both new instruments and new ideas, and each transformed not just what we know, but how we think about the universe. The question of what came before the Big Bang is the next frontier, and the track record of cosmology gives us reason to expect that progress will come, even if we cannot predict its form. There is also something valuable in the question independent of its answer. The question of what came before the Big Bang is one of those rare questions that forces us to examine our most basic assumptions about reality. What is time? What is existence? What does it mean for something to begin? What is the relationship between mathematical structure and physical reality? These are not merely cosmological questions. They are questions about the nature of knowledge, the limits of language, and the character of human understanding. Engaging with them seriously, with the full force of mathematical and observational science behind us, is one of the most ambitious things human minds have ever attempted. The universe does not owe us an answer. The laws of physics do not guarantee that the origin of the universe is accessible to beings evolved to navigate the macroscopic world of everyday experience. Our brains are optimized for social interaction, predator avoidance, tool use, and pattern recognition at the scales of human life. The scales of quantum gravity are more than 30 orders of magnitude removed from everyday experience. The timescales of cosmic history are more than 15 orders of magnitude longer than a human lifetime. There is no evolutionary reason why human minds should be capable of understanding physics at these extremes, and yet, remarkably, they seem to be. The mathematics of general relativity, which describes gravity at cosmic scales, and the mathematics of quantum mechanics, which describes physics at subatomic scales, are human inventions that have been confirmed to extraordinary precision by experiment. Human minds have been able to extend their understanding from the everyday scales, where they evolved to the extremes of the very large and the very small. Whether this extension can continue all the way to the question of the universe's origin is the deepest open question in all of science. The cosmic microwave background, when mapped with full precision, tells us about the universe when it was 380,000 years old. Before that, the universe was opaque to light, and photons scattered so frequently that no direct information from earlier times reaches us in the form of light. But gravitational waves propagate even through dense plasma and can in principle carry information from much earlier, from the inflationary epoch, from phase transitions, from any early universe process that disturbed the metric. If a primordial gravitational wave background is detected, it will extend our direct observational reach back to within a tiny fraction of the first second of cosmic history, far earlier than any photon can probe. Neutrinos also decoupled from the rest of the matter very early, when the universe was about 1 second old, and a cosmic neutrino background should exist, analogous to the cosmic microwave background, but consisting of neutrinos. Detecting this neutrino background directly is technically extraordinarily challenging because neutrinos interact so weakly with matter, but it is not in principle impossible, and future neutrino detectors may make progress on this. If the cosmic neutrino background were measured with enough precision to extract its temperature and spectral distortions, it would provide information about the universe at 1 second, adding another probe of the very early universe to complement the CMB. Even more ambitiously, the cosmic gravitational wave background from inflation, if it exists, represents photons, or rather gravitons, that have been propagating since the end of inflation, when the universe was a tiny fraction of a second old. Detecting this background directly is the goal of several proposed space-based gravitational wave missions beyond LISA, and while the technology is not yet available, the scientific case for developing it is compelling. A direct detection of gravitons from the inflationary era would be the deepest direct probe of the early universe ever achieved, providing information about the energy scale and mechanism of inflation from the universe itself, rather than from theoretical extrapolation. The development of better theoretical tools is equally important. Lattice quantum gravity calculations, numerical relativity extended to quantum regimes, and computational approaches to quantum cosmology are all areas of active development. The goal is to be able to calculate the predictions of quantum gravity theories for observable quantities, which requires both better theoretical frameworks and better computational methods. The scale of computation required is formidable, and progress depends on advances in both quantum computing and classical high-performance computing. But the trajectory of computational physics over the past few decades gives reason to expect that quantitative predictions from quantum gravity theories will become increasingly available. The intersection of cosmology with quantum information theory is also producing new conceptual tools that may be relevant to origin questions. The development of quantum error correction as a framework for understanding the emergence of spacetime, the use of tensor networks to represent quantum gravitational states, and the application of complexity theory to the interior of black holes are all examples of how quantum information concepts are reshaping quantum gravity. These tools may eventually be applicable to the question of the universe's origin, providing a language in which the pre-Big Bang state can be described in quantum informational terms that do not rely on classical spacetime concepts. None of these developments will definitively answer the question of what came before the Big Bang in the near term, but they will change the question. Every generation of cosmologists has inherited a version of the origin question and passed on a transformed version to the next generation. The transformation is cumulative and directional, moving toward greater precision, greater conceptual clarity, and greater empirical constraint, even if the ultimate question retreats before every advance. The version of the question we inherit from the current generation is far more precise than the version inherited from earlier generations. We know the age of the universe to about 1%. We know the geometry of space to better than 1%. We know the composition of the universe to a few percent. We know the spectrum of primordial perturbations to a fraction of a percent. We have a theoretical framework, the standard model of cosmology with inflation, that fits all these observations with remarkable precision. The question of what came before is now a question about what physics lies beyond this successful framework, at scales and times that the framework does not describe. The 7 theories we have explored are not final answers. They are the current generation's best attempts to extend the framework beyond its limits. Each one takes the successful framework and asks what it implies about what might lie beyond the Big Bang. Each one finds a different answer, and each one makes different predictions that future observations might test. The scientific conversation among these theories, mediated by observations and by theoretical consistency requirements, is the frontier of origin cosmology. That conversation is what makes origin cosmology alive. A field without competing theories is a field without progress because progress requires something to push against. The competition between inflation and ekpyrosis, between the Hartle-Hawking and Vilenkin proposals, between eternal inflation and emergent time, is not a sign of confusion. It is a sign of genuine scientific engagement with a problem that is hard enough to resist easy resolution. When the problem finally gives way, when the observational evidence and theoretical consistency requirements narrow the field of viable theories to one, the resolution will be all the more significant for having been so hard to reach. In the meantime, the question stands. The universe began, or it did not. Time started, or it emerged, or it has always existed in some form. Something preceded our hot, dense early phase, or nothing did, or the concept of something preceding is inapplicable. Each of these possibilities is a coherent scientific proposal. Each has mathematical form. Each makes predictions. And each changes in a different way what it means to exist in a universe that might have had no beginning. We live in a universe that seems to remember something we cannot quite see. The smoothness of the early universe, the particular spectrum of its primordial perturbations, the specific values of its constants, all of these look like they were set by conditions we have not yet identified. Whether those conditions were set by a previous universe, by quantum creation from nothing, by a collision of brains, by the timeless structure of the wave function, or by mathematical necessity, they were set somehow. And the setting happened either before our universe or at its very beginning, in a regime that our best theories approach but cannot yet fully describe. That regime is where the most important physics of the 21st century will be found. The experimental programs of the coming decades will not only test specific predictions of specific models, they will map the terrain of what is possible in the very early universe, constraining the space of viable theories and pointing toward the new physics that must eventually replace or extend our current understanding. That pointing is itself progress, even when it does not yet amount to an answer. The cosmic microwave background is the universe's oldest message, written in light at 380,000 years after the hot phase began. Future instruments will read that message with greater and greater precision, extracting more and more information from its temperature, polarization, and spectral properties. But the message was written over a background that was set even earlier, by processes we cannot directly observe. Reading the message requires understanding the background, and understanding the background requires understanding what happened before the message was written. That is the project of origin cosmology. Reading a message written in fire on a background we cannot see directly, using instruments we are still building, guided by theories we are still developing, constrained by logic and by mathematics that will eventually tell us what is possible and what is not. It is one of the most ambitious scientific projects in human history, and it is ongoing. The Big Bang was not a beginning in any simple sense. It was a beginning of something, the hot, dense phase we can trace and measure. But it may have been preceded by something else, something that set the stage, or it may have emerged from a quantum state that has no stage, or it may be all there is, the universe's only moment of origin in a timeline that extends infinitely forward, but not at all backward. We do not yet know which of these is true, but we are learning how to find out. And that learning, that reaching toward the edge of what can be known, is what science looks like when it is doing the most important thing it can do. The question remains. The question will remain for some time. But it is not the same question it was. And the universe, whatever it is, whatever it was before what we call its beginning, is still out there, carrying its history in every photon, every gravitational wave, every cluster of galaxies, every ratio of light elements, and every subtle statistical pattern in the oldest light we can see. We just have to learn to read it well enough, and carefully enough, and honestly enough to hear what it is saying about where it came from. Now we return to territory that the earlier chapters only touched on the edges of. We have established that time may be emergent, that the universe may have had predecessors, that creation from quantum states is mathematically formalized, and that the multiverse redistributes the fine-tuning problem without eliminating it. But there is a thread that runs through all 7 theories that we have not yet pulled on directly. It is the thread of information. Every theory of cosmic origins is, at some level, a theory about where information comes from. The universe we observe contains an enormous amount of structured information. The positions and velocities of 100 billion galaxies, each containing hundreds of billions of stars, each star with its own history of nuclear burning and its own planetary system, each planet with its own geological and possibly biological history. The information content of the observable universe is staggering, and all of it, ultimately, traces back to the tiny fluctuations in the primordial plasma that the cosmic microwave background records. Those fluctuations trace back to whatever process generated them, whether quantum fluctuations during inflation, thermal fluctuations in a string gas, perturbations from a brain collision, or imprints from a previous cycle. And those processes trace back to the initial state of the universe, or to whatever preceded it. The question of what came before the Big Bang is therefore partly a question about the origin of information. Where did the information content of the universe come from? If the universe began in a very simple state with very little information, as the Hartle-Hawking proposal might suggest, then the complexity we observe today was generated by the dynamics of the universe from that simple beginning. Inflation is very good at this because it takes simple initial conditions and generates a specific statistical distribution of perturbations that provides the seeds for all subsequent structure. The complexity of the present universe is not in the initial conditions. It is in the dynamics that amplified simple initial conditions into complex structure. If the universe had a predecessor, then some of the information content of our universe might be inherited from the predecessor. This is what cyclic models and conformal cyclic cosmology suggest. The information is not created at the Big Bang. It is transmitted through it, in modified form, from a previous state. The transmission is not perfect because the bounce or conformal transition changes the form of the information. But something is preserved, and that something might be detectable as a non-standard pattern in the CMB or in gravitational waves. If the universe was created from a quantum state with no classical precedent, as Vilenkin's tunneling proposal suggests, then the information content of the universe was in some sense encoded in the quantum state from which it nucleated. But quantum states are described by wave functions, and wave functions are mathematical objects that exist in the timeless framework of quantum mechanics. The information in the wave function is not information about events in time. It is information about the probability amplitudes for different outcomes. The question of where that information came from is the question of why the wave function is what it is, which is the question of the boundary condition that selects the wave function, which is what the no-boundary and tunneling proposals are trying to answer. In this sense, the origin of cosmic information is connected to the origin of cosmic law. The information content of the universe is generated by the application of laws to initial conditions. If the laws are fixed and the initial conditions are specified by a boundary condition, then the information content of the universe is determined by the boundary condition and the laws together. Asking where the information came from is asking why the boundary condition was what it was and why the laws are what they are. These are, again, the questions we have been asking in different forms throughout this journey. The holographic principle adds a striking dimension to this information theoretic perspective. The holographic principle, in its strongest form, states that the information content of a region of space is bounded by the area of its boundary, not by its volume. This is counterintuitive because in ordinary physics, the information content of a region should grow with its volume. A box with twice the volume should be able to contain twice as much information. But in a theory that includes gravity, this intuition breaks down because black holes limit the information density. If you try to pack too much information into a region, you form a black hole, and a black hole's entropy, which is a measure of its information content, is proportional to the area of its event horizon, not its volume. For cosmology, the holographic principle suggests that the information content of our observable universe is bounded by the area of its cosmic horizon, which is a sphere surrounding us at the distance light can have traveled since the Big Bang. The total information in our observable universe, expressed in fundamental units, is a finite number, enormous but finite, and all of that information was, in some sense, present at the beginning of the universe in the form that generated it. The origin of the universe is the origin of this bounded quantity of information, and a complete theory of the origin would be a theory of how this specific finite quantity of information came to be organized in the way that produced our universe. The anti-de Sitter conformal field theory correspondence makes this information-theoretic picture concrete in a specific mathematical setting. In this correspondence, the information content of the bulk gravitational theory, including all its spacetime structure and all the particles and fields it contains, is exactly encoded in the conformal field theory on the boundary. The boundary theory is non-gravitational and has a well-defined Hilbert space with a well-defined notion of information. The bulk theory with its dynamical spacetime emerges from the boundary theory in a way that is not yet fully understood, but that is well established as a duality in many examples. If something like this correspondence holds for our universe, then the information about the very early universe, including whatever preceded the Big Bang, is encoded in some boundary theory. The question of what came before the Big Bang would be a question about the state of the boundary theory at early times. In the anti-de Sitter setting, the boundary theory is defined on a fixed background spacetime at the boundary, and its time evolution is well defined. The bulk time emerges from the boundary time through the holographic reconstruction. If this picture can be extended to de Sitter space or to cosmological spacetimes, then the origin question might become a question about the initial state of a well-defined quantum field theory, which would be a much more tractable problem than the full quantum gravity problem. Progress on de Sitter holography would therefore be enormously important for origin cosmology. It would provide a non-perturbative framework for thinking about the very early universe in which the degrees of freedom are well defined, the dynamics are specified, and the question of what came before the Big Bang can be asked in a precise mathematical form. Answer might still be that time has no meaning before a certain point, but it would be a precise statement about the mathematical structure of the theory rather than a vague intuition about the limits of physics. The connection between information theory and gravity goes even deeper through the concept of quantum error correction. It has been shown in the anti-de Sitter conformal field theory setting that the reconstruction of bulk operators from boundary operators has the structure of quantum error correction. This means that the information about the bulk is encoded redundantly in the boundary, so that even if you lose part of the boundary data, you can still reconstruct the bulk. This redundancy is what protects quantum information from being lost, and it is also what makes the holographic encoding robust. For the early universe, this suggests that whatever information was present before the Big Bang might be encoded redundantly in the early universe's state, so that even though the hot, dense phase erased most of the details of what came before, some information might be preserved in a redundant encoding. This is different from a direct imprint, which would be a specific, localized signal. A redundant encoding would be distributed across many degrees of freedom and would be statistical in character, showing up as a non-random pattern in the correlations of the CMB or in the distribution of matter at large scales. The search for such patterns is one of the most sophisticated and most speculative parts of observational cosmology. It requires looking for statistical anomalies in the CMB and in large-scale structure that could not plausibly have been generated by the known physics of the hot Big Bang phase, and attributing those anomalies to physics from an earlier era. The difficulty is that the known physics of the hot Big Bang phase is rich and can itself generate complex patterns, and distinguishing pre-Big Bang imprints from hot Big Bang physics requires very precise theoretical predictions for both. The hemispherical power asymmetry in the CMB is one such anomaly that has attracted attention. The temperature fluctuations on one side of the sky are slightly stronger than on the other side, at a level that is unlikely but not impossible by chance. various explanations have been proposed, including a superhorizon perturbation, a cosmic dipole from a very large-scale mode, and pre-inflationary physics that bias the initial conditions. None of the explanations is convincingly established, and the anomaly remains unexplained. It is a hint, but hints in cosmology can be misleading, and the history of CMB anomalies is full of features that appeared significant and turned out to be statistical fluctuations or foreground effects. The cold spot in the CMB, a region of significantly lower temperature than surrounding areas, has similarly attracted attention as a possible imprint of a pre-inflationary or pre-Big Bang influence, or as the signature of a collision with another bubble universe. Various explanations, including a supervoid along the line of sight, a statistical fluctuation, and exotic physics have been proposed. The supervoid explanation has received some support from galaxy surveys that found a region of lower than average density in the direction of the cold spot, but whether the supervoid is large enough and empty enough to explain the full temperature depression is debated. The alignments of the largest scale CMB multipoles, the dipole, quadrupole, and octupole, with each other and with the direction of the ecliptic, are another set of anomalies that have been noted and studied extensively. These alignments are unlikely by chance, and they have been scrutinized for systematic effects from instrument calibration, data processing, and foreground subtraction. The consensus is that the alignments are real features of the CMB sky rather than artifacts, but their interpretation is debated. Some researchers see them as hints of pre-inflationary physics or of non-trivial topology of the universe. Others regard them as statistical fluctuations that are significant only in retrospect, after they have been noticed and selected for attention. The difficulty with all of these anomalies is the look elsewhere effect, the fact that if you look at enough features of the data, some of them will appear significant by chance. The CMB contains a vast amount of statistical information, and the probability that at least some of it will look anomalous is not small. Assessing whether a particular anomaly is a genuine signal or a statistical fluctuation requires careful frequentist analysis that accounts for the number of ways the data could have appeared anomalous, not just the probability that this particular anomaly would occur. This analysis is technically demanding, and the results are often sensitive to choices in the analysis pipeline. The future of origin cosmology, therefore, depends not just on new data, but on new statistical and analytical methods that can reliably extract pre-Big Bang signals from the noise of the hot Big Bang phase and the foregrounds of our galaxy and local environment. Machine learning and artificial intelligence methods are beginning to be applied to CMB analysis, with the goal of identifying patterns that human analysts might miss and of better separating signal from noise. These methods are promising, but they require careful validation to ensure that they do not introduce new biases or confuse the real signal with artifacts of the training data. Quantum computing may also play a role in the future of origin cosmology, both in the simulation of quantum gravity theories and in the analysis of large cosmological data sets. Simulating quantum systems on classical computers becomes exponentially hard as the number of degrees of freedom grows, which limits our ability to study quantum gravity in regimes relevant to the early universe. Quantum computers, which can in principle simulate quantum systems efficiently, might eventually allow calculations that are currently impossible, potentially revealing the predictions of quantum gravity theories for the early universe with much greater precision. The philosophical questions about origin do not go away as the observational and theoretical tools improve, but they change character. The question of what came before the Big Bang is partly an empirical question about what physical processes occurred before the hot phase we observe, and partly a conceptual question about what before means in a regime where time may not be fundamental. As the empirical question becomes better constrained by data and theory, the conceptual question becomes more pressing, because we need to understand what we are measuring and what our theories are telling us in order to interpret the results correctly. The conceptual question, in turn, connects to the deepest philosophical questions about time, causality, and existence. These questions have been discussed by philosophers for millennia, but they have been sharpened by the physics of the 20th and 21st centuries in ways that would not have been possible without the mathematical precision that physics brings. The concepts of Lorentzian and Euclidean time, of quantum superposition of causal orders, of emergent spacetime from entanglement, these are not traditional philosophical concepts. They are concepts that physics has developed and that philosophy must now engage with if it wants to make progress on the questions about time and causality that have always been at its core. The dialogue between physics and philosophy on these questions is more productive now than it has been for a long time, and that productivity is itself a sign of progress. When physicists say that time may be emergent, they are making a claim that has deep philosophical implications, and philosophers who work on the metaphysics of time can help clarify what that claim means and what evidence would count for or against it. When philosophers argue about the nature of mathematical existence, they are addressing a question that is directly relevant to the mathematical universe hypothesis and to the string landscape, and physicists can use those philosophical distinctions to sharpen their own claims. The conversation across the boundary of physics and philosophy is one of the most important intellectual developments in origin cosmology, and it is ongoing. The public engagement with origin cosmology is also important and worth noting in an honest assessment of the field. Questions about the origin of the universe engage people who have no professional interest in physics or philosophy because they touch on the most fundamental human concerns about existence, meaning, and place in the cosmos. The accurate communication of what science knows and does not know about cosmic origins is therefore not just a matter of scientific outreach. It is a matter of cultural importance. Overstating what we know or understating the genuine uncertainty both do a disservice to public understanding. The honest message is that science has made remarkable progress in understanding the history of the universe back to tiny fractions of the first second, and that this progress has revealed a universe that is stranger and more wonderful than any previous generation could have imagined. But the question of what came before the Big Bang, in the sense of what physical state or physical process preceded the hot, dense phase we observe, remains genuinely open. The honest message is that we have several candidate theories, each with serious scientific motivations and each making testable predictions, and that the coming decades of observations will significantly constrain these theories even if they do not definitively settle the question. And the honest message is that the deepest questions about time, existence, and necessity may never be fully answered by empirical science, but that engaging with them seriously is one of the most important things human minds can do. The universe began with a bang or something that looked like one from the inside. Before that, if before means anything, is where science is heading, guided by mathematics, constrained by observation, and illuminated by the growing understanding that the deepest questions about origins are also questions about the nature of time, the character of existence, and the remarkable ability of finite human minds to reach toward the infinite. We have covered the scientific landscape from multiple angles now, but there remains a dimension of the origin question that has been present in the background throughout and deserves direct attention. It is the question of what origin stories mean to us, not as scientific theories to be tested, but as ways of understanding our place in the cosmos. This is not a detour from science. It is a recognition that science does not occur in a vacuum of pure logic, and that the questions we ask and the frameworks we use to answer them are shaped by deeper concerns that are not purely scientific. Every civilization has had a creation story. The ancient Babylonian Enuma Elish described creation as the result of a battle between primordial gods. The Hebrew Genesis described creation as a deliberate act of a single God who spoke the world into existence. The Hindu cosmologies described cycles of creation and destruction on timescales that dwarf anything modern cosmology has proposed. The ancient Greek atomists described a universe that had always existed, with matter moving eternally through the void. The common thread in all of these stories is the attempt to answer not just what happened at the beginning, but why the universe exists, why it is the way it is, and what our existence within it means. Modern cosmology has replaced these stories with mathematical frameworks and observational data, but it has not replaced the questions that motivated the stories. The question of why the universe exists rather than nothing remains as open as it ever was. The question of whether the universe has a purpose, or whether purpose is a concept that applies only to agents within the universe rather than to the universe as a whole, remains as contested as ever. The question of what our existence in this universe means, given that the universe appears to be enormously large, enormously old, and largely indifferent to the conditions that allow life, remains as challenging as ever. Modern cosmology has changed our relationship to these questions by changing the scale and character of the universe we must ask them about. When the universe was thought to be a few thousand years old and the size of the solar system, the question of why it exists seemed easier to address with a personal creator who made it for a purpose. When the universe is known to be 14 billion years old, 93 billion light-years across in its observable portion, containing hundreds of billions of galaxies, each containing hundreds of billions of stars, and extending possibly much further beyond what we can observe, the question of why it exists and what our place in it means is correspondingly more challenging. The 7 theories we have explored give 7 different answers to the question of our place, even when they do not explicitly address it. In the cyclic universe picture, we are inhabitants of one phase in an endless sequence of cosmic eras. Our universe is not special. It is one iteration of a recurring process, and the conditions that allow our existence are reproduced in each cycle. In the quantum creation picture, we are the outcome of a quantum event that selected a particular initial state from a range of possibilities. Our existence is not necessary, but it is not miraculous either. It follows from the probability amplitudes of the wave function of the universe. In the multiverse picture, we are inhabitants of one bubble in a vast sea of bubbles, and our universe's properties are the result of a sampling process among possible vacua. Our existence is unremarkable because it is one realization of a common process. In the brain collision picture, we are the aftermath of a collision between higher dimensional objects, and the hot phase that produced us was the result of a mechanical event rather than a creative act. In the emergent time picture, we are part of a structure that generates its own sense of time from timeless quantum correlations, and our experience of a past, present, and future is an emergent property of the macroscopic structure we inhabit. In the mathematical universe picture, we are part of a mathematical structure that exists timelessly along with all other consistent mathematical structures, and our sense of being in a universe that came into being and will eventually end is an artifact of our temporal location within a structure that has no beginning or end in the mathematical sense. In the picture of necessary existence, we are part of a universe that could not have been otherwise, whose existence is guaranteed by logical necessity, and whose properties are the unique expression of what consistency and self-reference require. Each of these pictures has a different emotional and existential valence. The cyclic picture offers a kind of comfort through repetition, a sense that the universe is not a one-time event but a reliable process. The quantum creation picture offers a sense that our universe is one outcome among many, real but not unique. The multiverse picture can feel either liberating, because the fine-tuning that seemed to require an explanation is dissolved into sampling, or alienating, because our universe loses its specialness. The brain collision picture feels almost accidental, our hot Big Bang the result of a collision that need not have happened when or where it did. The emergent time picture is deeply abstract, challenging the reality of the temporal dimension that structures all our experience. The mathematical universe picture is the most alienating of all, suggesting that our sense of being in a physical universe with real material existence is a kind of projection onto a mathematical structure that has no intrinsic physical nature. The necessary existence picture offers a strange kind of reassurance that there had to be a universe, that existence is not a contingent accident, even if the specific form of that existence remains puzzling. None of these pictures maps cleanly onto the traditional categories of meaning that human cultures have developed. They are not theistic, with a personal creator who cares about the outcome. They are not nihilistic, with no structure or order at all. They are not simply mechanistic, with the universe as a clockwork that just happens to run. They are something new, emerging from the combination of mathematical precision and observational constraint that is modern cosmology, and our cultural and emotional frameworks have not fully caught up with them. The process of catching up is itself valuable, and it is part of what makes origin cosmology more than a technical scientific enterprise. When physicists work on the question of what came before the Big Bang, they are not just doing physics. They are extending the human conversation about existence that has been going on for as long as human beings have looked at the sky and wondered. The mathematical frameworks are new, and the empirical constraints are more precise than anything previous generations had access to, but the questions are the same questions that have always motivated that looking. Why is there something rather than nothing? Why is the something structured the way it is? And what does our existence within that structure mean? These questions do not have easy answers, and they may never have complete answers. But asking them rigorously, with the full force of modern science behind the asking, is one of the most important things human culture does. It is what separates idle speculation from genuine inquiry, and it is what makes the frontier of origin cosmology one of the most intellectually and humanly significant places in contemporary thought. The Big Bang was not a beginning in the simple sense that the word beginning suggests. It was a moment of extraordinary density and temperature from which everything we see has expanded and cooled over nearly 14 billion years. What preceded that moment, if anything did, remains one of the deepest open questions in science. The theories we have explored suggest that the question is not unanswerable in principle, and that the coming decades of observations and theoretical developments will transform our understanding of it significantly. The honest scientist acknowledges that we do not yet know the answer. while the honest science communicator acknowledges that we know enough to say with confidence what the question really is. The question is not simply what happened before the Big Bang, as if the Big Bang were an event in an ordinary sequence of events. The question is what kind of a thing the Big Bang is, whether it is a beginning of time itself, a transition in a larger physical history, a quantum boundary condition, a brane collision, a moment of emergent classicality from a timeless quantum state, or a location in a mathematical structure. Each answer to this question about the nature of the Big Bang implies a different answer to the question of what preceded it, if anything did, and each implies a different account of what existence means. We are the first generation with the tools to ask this question in its full depth, with the mathematical precision to formulate it clearly, with the observational power to constrain the answers, and with the theoretical frameworks to evaluate the implications. We are unlikely to be the last generation to ask it, and we will probably not be the generation that answers it definitively. But we are doing the work that makes the eventual answer possible, and that work is the most important frontier in contemporary science. The universe began, or it did not, or beginning is the wrong concept. The story goes on, and we are part of it, asking questions at the edge of what can be known, reaching toward what cannot yet be seen, and finding that the reaching is itself one of the most distinctively human things we can do. The journey through 7 theories has brought us to a place where the question of what came before the Big Bang has been transformed into something richer and stranger than it first appeared. We have seen that the question is not one question but many, that each theory answers a different version of it, and that the answers collectively reveal something important about the nature of time, existence, and knowledge itself. Now we turn to what may be the most important dimension of the question that we have not yet fully explored. It is the question of how we know what we know, and how we can distinguish genuine understanding from sophisticated storytelling. This epistemological question is not a detour from the science. It is at the heart of it. Origin cosmology is unusual among scientific disciplines because its subject matter is partly inaccessible to direct observation. We cannot travel back to the Big Bang and watch it happen. We cannot run the universe in reverse and see what was there before. We cannot compare our universe to other universes in the multiverse to check whether the constants vary. We are constrained to observe a single universe from a single location within it, at a single moment in its history, with instruments that have finite sensitivity and finite resolution. Everything we claim to know about the origin of the universe is inferred from those observations, using theoretical frameworks that are themselves inferred from a broader body of physical knowledge. The inferential chain from observation to origin is long, and each link in it is subject to uncertainty. The cosmic microwave background tells us about the universe at 380,000 years. To infer what the universe was like before that requires a theoretical model, and the model must be tested against multiple independent observations. The hot Big Bang model passes those tests impressively, which gives us confidence in extrapolating back to the first few minutes when nucleosynthesis occurred, and to the first second when neutrinos decoupled, and when the density of the universe was comparable to that of an atomic nucleus. Beyond that, the extrapolation becomes increasingly model-dependent because we have no direct observations from those epochs. Inflation is the most widely accepted framework for describing the universe before the hot Big Bang phase, but it is not confirmed in the sense that the hot Big Bang is confirmed. The hot Big Bang makes specific quantitative predictions that have been checked against observations of the CMB, large-scale structure, and element abundances, and the agreement is precise. Inflation makes predictions that are consistent with observations, particularly the nearly scale-invariant spectrum of primordial perturbations, but those predictions are also consistent with some alternatives. The detection of primordial gravitational waves would be a more distinctive confirmation of inflation because it would require a specific energy scale that alternatives do not naturally provide. Until such a detection, or a definitive upper limit that rules out large classes of inflation models, inflation remains a highly successful and widely accepted theoretical framework that has not yet been confirmed at the level of the hot Big Bang. This matters for assessing the theories we have explored, because most of them are built on top of inflation or are alternatives to it. If inflation is wrong, then eternal inflation and the inflationary multiverse are wrong. If inflation is wrong, then the quantum creation proposals that use inflation as their mechanism for generating structure are incomplete. If inflation is wrong, then the brane collision models that must compete with inflation in explaining the primordial spectrum must be evaluated against a different backdrop. The 7 theories are not independent of each other. They share assumptions and they compete in a landscape of observational constraints that is itself uncertain at the frontier. The history of cosmology provides important context for this uncertainty. The history of the field is full of ideas that seemed compelling and were later abandoned or significantly modified. The steady-state model was a serious and sophisticated alternative to the Big Bang for decades before the CMB, and the evidence for cosmic evolution made it untenable. The original cyclic models of the mid-20th century seemed physically motivated, but ran into the entropy problem that was only later appreciated as fatal to the simplest versions. The inflationary paradigm itself went through multiple revisions as observational data constrained the models, and the current landscape of inflation models is vastly different from the original Guthlin picture in its details, even if the basic mechanism is preserved. This history does not mean that current theories are wrong. It means that confidence in current theories should be calibrated to the strength of the evidence for them, and that the evidence for theories of cosmic origin becomes thinner the further back in time we extrapolate. The hot Big Bang is very well supported. Inflation is supported, but not yet at the level of the hot Big Bang. The specific inflationary models are more speculative. The quantum gravity theories that describe the universe before inflation are even more speculative. And the philosophical frameworks that address the deepest origin questions, the mathematical universe hypothesis, necessary existence, emergent time, are at the frontier of what can even be called scientific rather than philosophical. Recognizing this gradient of confidence is not defeatism. It is scientific honesty, and scientific honesty is what gives the claims we can make their authority. When a scientist says the universe is about 14 billion years old, that claim is backed by multiple independent lines of evidence converging on the same number with percent-level precision. When a scientist says inflation probably occurred in the early universe, that claim is backed by the success of the inflationary predictions for the CMB, but lacks the confirming evidence that would come from primordial gravitational waves. When a scientist says the universe may have had a predecessor connected by a quantum bounce, that claim is backed by a mathematical framework in loop quantum cosmology that is internally consistent but has not been tested against distinctive observational predictions. When a philosopher-physicist says the universe is a mathematical structure that necessarily exists, that claim is backed by an interesting argument, but not by any specific observational evidence. The gradient from observational certainty to philosophical speculation is not a defect of origin cosmology. It is an accurate reflection of the structure of the problem. The parts of the question that are well-defined and tractable have received well-defined and tractable answers. The parts that remain open are open because they are genuinely hard, not because scientists have failed to think carefully about them. The frontier of origin cosmology is genuinely at the edge of what empirical science can address, and acknowledging that is more useful than pretending the edge does not exist. With that calibration in place, we can assess more carefully what the 7 theories have actually established and what they have not. Loop quantum cosmology has established that a quantum bounce is possible in a quantized cosmological model, and that the classical singularity can be replaced by a well-defined quantum transition. It has not established that this is what actually happened in our universe, that the quantization procedure used is the correct one, or that the simplified minisuperspace model captures the essential physics. Eternal inflation has established that if inflation occurs, it tends to be eternal in the sense that the inflating region never completely stops inflating globally, and that this generically produces a multiverse of bubble universes. It has not established that inflation occurred, that the specific form of eternal inflation is realized, or that the bubble collision and measure problems have solutions. The no-boundary and tunneling proposals have established that the initial state of the universe can in principle be determined by a quantum boundary condition, and that such boundary conditions can be written down mathematically. They have not established which boundary condition is correct, whether the mathematical framework is adequate for full quantum gravity, or how the predictions of these proposals can be distinguished observationally. Ekpyrosis and brane cosmology have established that a contracting universe can generate a nearly scale-invariant spectrum of perturbations through an entropic mechanism, and that a brane collision can in principle replace the classical singularity in a higher dimensional framework. They have not established that the bounce problem is solved, that the specific brane dynamics required by the model are realized in string theory, or that the model's predictions are distinguishable from inflation in the observational data currently available. Emergent time proposals have established that the timeless Wheeler-DeWitt equation is a natural consequence of applying quantum mechanics to general relativity, and that time can in principle emerge from relational quantum correlations. They have not established that this emergence mechanism is correct, how it connects to the full theory of quantum gravity, or what observational signatures it would produce. The mathematical universe hypothesis has established that the relationship between mathematical existence and physical existence is deep and worth taking seriously. It has not established that physical existence just is mathematical existence, that all mathematical structures are physically real, or what observational predictions would distinguish the mathematical universe hypothesis from alternatives. These are honest assessments of where the theories stand. They are not criticisms of the theories. All of these frameworks represent genuine intellectual progress, genuine mathematical development, and genuine physical insight. They have moved the question of cosmic origins from the realm of pure speculation to the realm of science with mathematical structure and observational implications. That is a significant achievement, but the achievements should not be overstated, and the genuine uncertainties should not be swept under the rug. The future progress of the field depends on maintaining this honest assessment of what is established and what is not, because the research program must be calibrated to where the genuine uncertainties lie. If we incorrectly treat inflation as confirmed at the level of the hot Big Bang, we might invest insufficient effort in testing its distinctive predictions and in developing alternatives. If we incorrectly treat the multiverse as established, we might prematurely abandon the search for more fundamental explanations of the constants of nature. If we incorrectly treat the no-boundary proposal as determining the initial state of the universe, we might not invest enough effort in developing alternative approaches to quantum cosmology. The honest assessment of uncertainty is not just philosophically important, it is scientifically necessary for directing future research. The most important near-term scientific developments for the origin question are observational. The detection or non-detection of primordial gravitational waves will significantly constrain the energy scale of inflation and the viability of specific inflation models and alternatives. The precise measurement of the spectral index of primordial perturbations and of primordial non-Gaussianity will constrain the mechanism of perturbation generation. The measurement of large-scale anomalies in the CMB, including the hemispherical asymmetry, the cold spot, and the large-scale multipole alignments, will either support or undermine the idea that there are pre-inflationary imprints in the primordial perturbation spectrum. The measurement of spatial curvature will constrain quantum creation models, and the measurement of the dark energy equation of state will constrain models of the very late universe that connect to cyclic cosmologies. These observational programs are already underway, with experiments like the Planck satellite having completed its analysis, and the next generation of ground-based CMB experiments and space missions preparing to push the measurements to the next level of precision. The combination of all these measurements will provide a much more detailed and more precisely constrained picture of the primordial universe, which will in turn provide stronger constraints on theories of its origin. The constraints may not uniquely select one theory over all others, but they will significantly narrow the space of viable theories, and that narrowing is progress. On the theoretical side, the most important developments will likely come from advances in quantum gravity and from the better understanding of the connections between quantum information, holography, and cosmology. The development of a non-perturbative framework for quantum gravity in de Sitter space, whether through holography or through other approaches, would be transformative for origin cosmology. It would provide a mathematical framework in which the question of what came before the Big Bang could be asked and answered precisely, without relying on semi-classical approximations that break down in the very early universe. The development of such a framework is a major open problem, and progress on it is likely to require new conceptual tools as well as new mathematical techniques. The connection between quantum gravity and quantum information, developed through holography, tensor networks, and quantum error correction, may provide some of those new conceptual tools. The insight that spacetime may emerge from quantum entanglement, and that the reconstruction of bulk spacetime from boundary data involves quantum error correction, suggests a new way of thinking about the early universe. The early universe in this picture is not a spacetime that we extrapolate back to ever earlier times. It is a regime where the quantum informational structure from which spacetime emerges is becoming apparent, and the Big Bang is the transition from a pre-geometric quantum phase to a geometric one. This is a very different picture from the one that classical cosmology provides, and developing it in detail will require a synthesis of quantum information theory, quantum gravity, and observational cosmology that does not yet exist, but the pieces are being assembled. The holographic understanding of black holes, the development of tensor network models for holography, the application of quantum information concepts to cosmological problems, all of these are steps toward the synthesis that origin cosmology ultimately requires. The philosophical questions about the nature of time, causality, and existence will continue to be important as the scientific frameworks develop. The question of whether time is fundamental or emergent will be better constrained as theories of quantum gravity become more precise and as their observational implications become clearer. The question of whether the universe could have been otherwise, whether the constants of nature are contingent or necessary, will be better constrained as the string landscape is better understood and as the swampland program restricts the space of consistent vacua. The question of why there is something rather than nothing will remain, because no physical theory can answer it by purely empirical means. But physics can narrow the question by showing which aspects of the universe's existence are contingent and which may be necessary, which aspects require explanation, and which follow from more fundamental principles. The engagement with these philosophical questions is not a distraction from the science. It is part of it. The history of physics shows repeatedly that the deepest advances come not just from new data, but from new ways of framing the questions. The development of general relativity required a new understanding of the relationship between space, time, and gravity that was philosophical as much as mathematical. The development of quantum mechanics required a new understanding of the relationship between observation, measurement, and physical reality that challenged every previous assumption. The development of a complete theory of the universe's origin will similarly require new conceptual frameworks that may be as philosophically radical as general relativity and quantum mechanics were in their time. We are not there yet. We are working toward it with the best tools that human knowledge has produced, guided by the questions that human curiosity has always asked. The question of what came before the Big Bang will eventually be answered, or it will be shown to be a question that cannot be answered, or it will be transformed into a better question that we have not yet learned to ask. Each of these outcomes would be a form of progress, and each would change what we understand about the universe and about our place within it. The universe is not a simple place, and its origin is not a simple question, but the complexity is what makes it worth the effort, and the effort is what makes cosmology one of the most ambitious and most important intellectual enterprises in human history. The Big Bang was not a beginning in the sense that there was nothing before it. It may not have been a beginning in any simple sense at all, but it was the beginning of the story we can tell with confidence, the story written in light and gravity and the abundance of atoms across 14 billion years of cosmic history. Whatever came before that story, it was the precondition for everything we are and everything we know, and learning what that precondition was is the deepest question we can ask. There is a particular kind of terror that the origin question produces when you sit with it long enough. It is not the terror of death or of emptiness, though it contains elements of both. It is the terror of regress, the feeling that every answer opens onto another question, every foundation rests on another foundation, and the chain extends downward without ever reaching bedrock. The universe came from a quantum bounce, but what set the conditions for the bounce? The universe nucleated from a quantum vacuum, but what defined the quantum theory governing that vacuum? The universe is one bubble in an eternal inflation, but what started the inflating background? The universe is a mathematical structure that necessarily exists, but why does mathematical existence entail physical existence? Every answer to the origin question generates a new version of the origin question applied to whatever the answer invokes. This is not a failure of the answers. It is a feature of the problem. The origin question has a self-referential quality that resists resolution in the same way that Gödel's incompleteness theorems show that sufficiently powerful formal systems cannot fully ground themselves. Any framework powerful enough to answer the origin question will contain elements that the framework itself cannot justify without stepping outside itself. And stepping outside raises the same question at the next level. This regress is not infinite in a vicious sense because it does not mean that we can never make progress. It means that the progress is asymptotic, approaching, but never reaching a final complete account. Each level of explanation is genuine progress. Each framework that answers one version of the question and raises the next is better than the framework that left both versions unanswered. The sequence of better explanations is itself meaningful even if it does not terminate in an ultimate explanation. The physicist's response to this regress is to ask for the deepest framework that makes testable predictions, knowing that even the deepest framework will rest on assumptions that the framework itself cannot justify. The standard model of particle physics rests on the assumption of quantum field theory, which rests on the assumption of quantum mechanics, which rests on the assumption that probabilities are well defined and that observations have definite outcomes. At some level, the chain of justifications ends not in a bedrock of self-evidence, but in a choice of framework that is justified by its success in organizing experience rather than by derivation from something deeper. Physics is not a chain of logical deductions from first principles. It is a web of overlapping frameworks, each valid in its domain, each connected to the others by correspondence principles and by the requirement of consistency, and the whole resting on the pragmatic foundation of empirical success. The origin question pushes this web to its limit because the domain in question is the universe itself, and there is no external domain from which to view it. We are inside the framework we are trying to explain, using tools provided by the framework, constrained by the framework's own structure. The question of why the framework exists or what it rests on is one that the framework cannot answer without assuming itself. This is not a defect of the framework. It is a fundamental feature of self-reference that applies to any sufficiently powerful system of knowledge. The philosopher's response to this regress is different from the physicist's, and the difference is instructive. The philosopher may argue that the regress shows that the demand for explanation must eventually terminate in something that is self-explanatory, something whose existence requires no further justification. The candidates for this self-explanatory terminus include logical necessity, where the terminus exists because its non-existence would be contradictory; mathematical necessity, where the terminus is a mathematical structure whose existence follows from its own logical properties; and metaphysical necessity, where the terminus is a being whose essence entails its existence. Each of these candidates has been defended by serious thinkers, and each faces serious objections. The physicist's pragmatism and the philosopher's search for necessity are not incompatible. They address different levels of the same question. The physicist asks what framework best organizes our empirical knowledge, and what that framework implies about the origin of the universe within the domain where the framework applies. The philosopher asks what the deepest possible justification for having any framework at all might be, and whether existence itself requires explanation. Both questions are legitimate, and answering them well requires engaging seriously with both. The uncomfortable middle ground is where origin cosmology actually lives. It is neither purely empirical, in the sense of directly testable by observation, nor purely philosophical, in the sense of resolvable by conceptual analysis alone. It requires the interplay of mathematical frameworks, observational constraints, and philosophical analysis. That interplay is difficult and sometimes frustrating, because the standards of evidence and argument in physics and philosophy are different, and what counts as a satisfying answer depends on which standard you apply. The productive response to this discomfort is not to retreat to one discipline or the other, but to develop better tools for working at the interface. The development of mathematical frameworks that make philosophical claims precise enough to have observational implications is one such tool. The development of philosophical frameworks that can engage with the technical content of quantum gravity and quantum cosmology without distorting it is another. The development of statistical and analytical methods that can extract reliable information from the ambiguous observational data at the frontier of origin cosmology is a third. All of these are ongoing projects, and all are part of the enterprise of understanding what came before the Big Bang. The question itself has a history that is worth tracing briefly, because the history illuminates the progress that has been made and the challenges that remain. In the early 20th century, the prevailing view among physicists and astronomers was that the universe was eternal and static. Einstein's original formulation of general relativity actually included a cosmological constant that was designed to keep the universe static by balancing the gravitational attraction of matter. When Hubble's observations in the late 1920s revealed that galaxies are moving away from us in proportion to their distance, implying that the universe is expanding, the static picture was overthrown. The logical implication that an expanding universe must have been smaller in the past, and therefore hotter and denser, led to the Big Bang theory. The resistance to the Big Bang in its early decades was partly scientific, because the theory made predictions that could be checked, and partly cultural and philosophical, because the idea of a cosmic beginning had theological implications that some scientists were uncomfortable with. The steady-state theory was developed partly as a scientific alternative, and partly as a way of avoiding those implications. The discovery of the cosmic microwave background in 1965 was the crucial observation that confirmed the Big Bang and falsified the steady-state theory, demonstrating that the universe had indeed been in a hot, dense phase in the past that left a thermal relic detectable today. The subsequent development of inflationary cosmology in the 1980s by Alan Guth, Andre Linde, Paul Steinhardt, Andreas Albrecht, and others was a response to specific problems with the naive Big Bang picture, the flatness problem, the horizon problem, and the magnetic monopole problem. Inflation solved all three problems elegantly and made a specific prediction, the nearly scale-invariant spectrum of primordial perturbations, that was later confirmed by CMB observations. Inflation became the dominant paradigm for early universe cosmology, not because it was confirmed beyond doubt, but because it solved real problems, made testable predictions, and fit within the framework of quantum field theory in a natural way. The development of string theory in the 1980s and its maturation into a candidate theory of quantum gravity in the 1990s opened new possibilities for thinking about the very early universe and the origin question. The discovery of the vast landscape of string vacua in the early 2000s by Bauso, Polchinski, and others changed the way the fine-tuning problem was framed, shifting the conversation from why are the constants what they are to how does the multiverse sample the landscape, and leading to the anthropic reasoning that has been influential but controversial. The development of loop quantum gravity as an alternative approach to quantum gravity by Ravelli, Smolin, Ashtekar, and others, and its application to cosmology in the form of loop quantum cosmology by Bojhold, Ashtekar, Singh, and others, provided a different framework for thinking about the very early universe that avoided the singularity without invoking string theory. The development of causal dynamical triangulations by Amj²Rn, Jerkiewicz, and Lal provided a computational approach to quantum gravity that showed how sensible spacetime geometry could emerge from a quantum sum. These developments have given origin cosmology a richer theoretical landscape than it had a generation ago. The current state of the field is therefore the result of 50 years of rapid development, from the confirmation of the hot Big Bang to the multiverse and quantum gravity frameworks of today. The progress has been real and substantial. The questions are better formulated, the mathematical tools are more powerful, and the observational data are more precise than at any previous time. But the deepest questions remain open, and the field is continuing to develop rapidly. The next 50 years will likely bring comparable progress, driven by new instruments, new theoretical ideas, and new conceptual frameworks. The experiments planned for the coming decades in CMB polarization, large-scale structure, gravitational waves, and possibly direct detection of the cosmic neutrino background will transform our empirical knowledge of the primordial universe. The theoretical developments in quantum gravity, holography, and quantum information will transform our conceptual frameworks for understanding the very early universe and the origin question. And the philosophical developments in understanding what time, causality, and existence mean in the context of quantum gravity will transform what we think the question of origin even means. What we can say with confidence at this moment in the development of the field is that the origin question is alive in a way that it has not been for centuries. It is alive as a scientific question, with specific proposals, specific predictions, and specific observational tests. It is alive as a theoretical question, with mathematical frameworks that give it precise form and allow its implications to be calculated. And it is alive as a philosophical question, with conceptual dimensions that require analysis and argument that goes beyond what any single scientific theory can provide. The liveliness of the question is itself a sign of intellectual health, of a field that has not retreated into complacency, but continues to push toward the hardest problems. The universe keeps its secrets well. It does not reveal its origins easily, and it does not reward lazy thinking or wishful reasoning. But it does reward careful attention, mathematical precision, and the willingness to follow the evidence wherever it leads, even when it leads to conclusions that are strange and uncomfortable. The question of what came before the Big Bang is one of those questions where careful attention and mathematical precision have already led to strange and uncomfortable conclusions, and where the full strangeness is probably still ahead. The cosmos is older than its oldest light, or it began with that light, or neither of these sentences is quite right, because the concepts they rely on do not apply cleanly to the regime they are trying to describe. Somewhere in that tangle of near-right statements and almost applicable concepts is the truth about the origin of the universe, waiting to be found by methods we are still developing, expressed in language we have not quite learned to speak, confirmed by observations we are not yet able to make. That is where we are. That is the honest state of origin cosmology at this moment in its history, and it is, in its way, the most exciting place in science. There is one more perspective that deserves direct engagement, one that has been implicit throughout, but has not been made fully explicit. It is the perspective of time itself, not as a physical parameter to be measured, but as the medium through which science progresses and through which the question of cosmic origins takes on its human meaning. Science is a process that takes place in time. Theories are proposed, debated, tested, modified, and sometimes abandoned. Evidence accumulates gradually, not in sudden revelations, but in the slow accretion of measurements and calculations. Understanding deepens through the collective effort of generations of scientists, each building on the work of those who came before and creating the foundation for those who come after. The question of what came before the Big Bang is not just a question that exists at a moment in time. It is a question that has a history, a present state, and a future trajectory. Understanding that trajectory is part of understanding the question. The trajectory of the origin question over the past century has been consistently toward greater precision and greater complexity. The simple question of whether the universe had a beginning has given way to the complex question of what kind of beginning it had, or whether beginning is the right concept, and whether the framework in which we ask the question is adequate to the answer. This is progress, even if it looks like complication from the outside. The questions that seem simple often become complex as we understand them better, because the apparent simplicity was an artifact of ignorance. The genuine complexity that emerges from careful investigation is closer to the truth, even if it is harder to explain. The trajectory of the observational evidence over the same period has been toward firmer and firmer support for a hot, dense early phase, with increasingly precise constraints on its properties, and toward the recognition that explaining that early phase requires physics beyond the standard Big Bang picture. Inflation, quantum gravity, and the various alternative and complementary frameworks we have discussed are not complications added to a simple story for the sake of complexity. They are responses to genuine observational puzzles, genuine theoretical difficulties, and genuine gaps in the explanatory power of the simpler picture. The trajectory of the theoretical frameworks has been from simple, elegant proposals that solve the immediate problems to richer, more complex frameworks that address deeper questions while raising new ones. The hot Big Bang was simple and successful. Inflation added complexity to solve the flatness and horizon problems. The quantum creation proposals added more complexity to address the singularity problem. The multiverse added even more complexity to address the fine-tuning problem. Each step was motivated by genuine problems with the previous step, and each step solved those problems while creating new ones. This is how science advances, not by finding simple final answers, but by replacing simple wrong answers with complex better ones. The trajectory of the philosophical engagement has been from dismissal to serious integration. Early in the development of cosmology, the philosophical questions about the nature of time and existence were regarded by many physicists as beyond the scope of science, matters for theologians or metaphysicians, rather than for people who get their hands dirty with equations and experiments. The development of quantum mechanics and general relativity changed that, because both theories raised philosophical questions about the nature of measurement, observation, and reality that could not be avoided. Quantum cosmology has taken this further, raising questions about the nature of time, causality, and existence that are as central to the physics as they are to the philosophy. The integration of philosophical analysis with physical theories is not always comfortable, because philosophers and physicists have different standards for what counts as a satisfying answer, different relationships to mathematical formalism, and different intuitions about what is and is not a genuine progress. But the discomfort is productive, because it forces both sides to be more precise about what they mean and what evidence they are relying on. The most important advances in origin cosmology have come at the interface of physics and philosophy, where mathematical frameworks and conceptual analysis reinforce and challenge each other. This integration is likely to deepen in the future as the questions become harder and the available frameworks become more sophisticated. The questions about the nature of time in quantum gravity, the meaning of probability in the multiverse, the relationship between mathematical and physical existence, and the conditions under which the concept of a cosmic origin is well defined, are all questions that require both physical precision and philosophical clarity. Addressing them well will require scientists who can think philosophically and philosophers who can engage seriously with physics. Both exist, and their collaboration is one of the most promising features of contemporary origin cosmology. The long view of the origin question is therefore optimistic, not because the question will be answered soon, but because the tools for addressing it are improving steadily, and the collaboration across disciplines that the question requires is becoming more productive. The universe is not going to reveal its secrets easily, but it is going to reveal them eventually, to the patient and the persistent and the rigorous. And the revelation, when it comes, will be one of the most profound achievements of human knowledge. In the meantime, the question stands: what came before the Big Bang? We have 7 answers, each partial, each genuine, each pointing toward a different facet of a truth we have not yet fully grasped. the dying predecessor universe of cyclic cosmology. Quantum nothing of the creation proposals, the eternal inflating background of the multiverse, the colliding brains of ekpyrotic theory, the timeless quantum state of emergent time cosmology, the mathematical structure of the block universe and the Tegmark hypothesis, the necessary existence of a universe that could not have been otherwise. Each of these is a story about where we came from. Each is grounded in serious mathematics and serious physics. Each makes predictions that can in principle be tested. And each changes in a different way what it means to exist in a universe that might have had no beginning. The Big Bang was not a beginning, or it was, or the question of whether it was a beginning is not yet well posed enough to have an answer. We are working on the posing as much as on the answering, and that work is science at its most alive, most difficult, and most important. The cosmos remembers something, or it does not, or remembering is the wrong concept for what the CMB encodes about the earliest moments of a universe that may have had no first moment. We are learning to read what it has written, in light and gravity and the abundance of light atoms and the statistical patterns of the largest structures, and what we read is changing our understanding of what the universe is, what we are, and what it means to ask where we came from. The question remains. It has always remained. It will remain until we answer it, or until we find that the question was wrong, or until we develop a better question that dissolves the old one into a clarity we cannot yet imagine. That is the nature of frontier science. That is the nature of origin cosmology. That is the nature of the deepest questions that human minds can ask. Every measurement we have ever made of the cosmic microwave background has confirmed the same basic picture. The universe at 380,000 years was a hot, nearly uniform plasma with tiny fluctuations of 1 part in 100,000. Those fluctuations have a specific statistical character, nearly Gaussian, nearly scale invariant, with a specific tilt and a specific set of acoustic peaks in the angular power spectrum. This picture is so well confirmed and so internally consistent that it serves as the bedrock of modern cosmology. Everything else we believe about the early universe is built on this foundation, but the foundation itself rests on something deeper, on the physical processes that produce the nearly uniform plasma with those specific fluctuations. Inflation is our best theory of those processes, and it fits the data. But it is not proven, and it leaves open the question of what came before inflation and what set its initial conditions. That question is where the 7 theories we have explored come in. Each one is an attempt to go one step deeper than inflation, to explain not just how inflation worked, but why the universe was in a state where inflation could occur. The observational constraints on these deeper theories are necessarily indirect. We cannot observe the pre-inflationary epoch directly because inflation erased the direct signals from that epoch by stretching everything far beyond our horizon and diluting the density of any particles or radiation from before inflation to negligible levels. What inflation cannot erase are the quantum fluctuations generated during inflation itself, because those fluctuations are stretched to superhorizon scales during inflation and become the seeds for structure after inflation ends. And it cannot completely erase the effects of pre-inflationary physics on the quantum state of the inflated field, because those effects can influence the probability distribution over inflationary histories. This is why the statistics of the primordial perturbations are so important. They are not just a test of inflation. They are a potential window into what came before inflation, because the statistical properties of the perturbations depend on the quantum state of the universe at the beginning of inflation, which in turn depends on whatever physical processes produced that state. If the state was set by a quantum bounce, the perturbations might show specific non-Gaussian signatures or specific anomalies on large scales. If the state was set by a brane collision, the perturbations might show a preferred direction or a specific tilt. If the state was set by the no-boundary wave function, the perturbations might show a specific spectrum on the very largest scales. The challenge is that these pre-inflationary effects are typically suppressed by the same factor that makes inflation so effective at erasing the prior state. Inflation works by stretching the universe enormously and diluting any pre-existing structures, and the same stretching that dilutes the pre-inflationary matter and radiation also dilutes the effects of pre-inflationary quantum states on the perturbations. The effects can persist, but they are small, and detecting them requires extremely precise measurements of the largest angular scales in the CMB, where the cosmic variance limitation is most severe. This fundamental tension between the effectiveness of inflation and the persistence of pre-inflationary signals is one of the deepest challenges in origin cosmology. Inflation is so good at its job that it is almost too good. It solves the flatness and horizon problems by erasing almost all information about what came before. That is exactly what we need to explain the smoothness of the observed universe, but it is precisely what makes detecting pre-inflationary physics so difficult. The same mechanism that explains why the universe looks the way it does is the mechanism that hides where it came from. The practical implication is that detecting pre-inflationary physics, if it is possible at all, will require the most precise CMB measurements achievable, combined with the most sophisticated statistical analysis available. The next generation of CMB experiments, particularly CMB S4 and future space missions, will push the measurements to the limits of what cosmic variance and foregrounds allow. At those limits, the faint imprints of pre-inflationary physics, if they exist and if they are large enough, might be detectable. If they are not detectable at those limits, we will face a fundamental observational barrier imposed by inflation's effectiveness, and the question of what came before will remain forever beyond direct empirical reach. That prospect is sobering, but not entirely discouraging. Even if the pre-inflationary state cannot be directly detected, the consistency requirements of quantum gravity and the theoretical constraints on viable inflationary models provide indirect information about the pre-inflationary regime. The swampland conjectures in string theory constrain which effective theories can be consistently embedded in a complete quantum gravitational theory, and if those conjectures are correct, they rule out large classes of inflationary models and indirectly constrain the pre-inflationary state. The development of a complete non-perturbative framework for quantum gravity in de Sitter space would provide a mathematical framework in which the pre-inflationary state is determined by the theory itself, without relying on observational input. And the philosophical analysis of what time and causality mean in quantum gravity continues to refine what questions can even be meaningfully asked about the pre-inflationary epoch. The combination of all these approaches, observational, theoretical, and philosophical, is what gives origin cosmology its vitality and its intellectual richness. No single approach is sufficient. The observational constraints without the theoretical frameworks to interpret them are just numbers without meaning. The theoretical frameworks without observational constraints are beautiful mathematical structures with no connection to reality. The philosophical analysis without both the observations and the theories is speculation without substance. The synthesis of all three is what constitutes genuine progress on the origin question. That synthesis is ongoing, and it is one of the most collaborative intellectual enterprises in human history. Origin cosmology draws on observational astronomy, theoretical physics, mathematics, quantum information theory, philosophy of physics, and the history and philosophy of science. It requires people who can work across these disciplines and communicate across the boundaries that normally separate them. The development of such interdisciplinary understanding is itself one of the achievements of origin cosmology, and it may turn out to be as important for the future of science as any specific answer to any specific origin question. The universe does not care whether we understand it. It has been expanding and cooling for nearly 14 billion years, producing stars and galaxies and black holes, and eventually chemistry and biology and consciousness, all without any regard for whether any of it makes sense to the consciousness it has produced. But we care, and that caring is what makes us scientists and philosophers and thinkers. The question of where we came from is not just a cosmological question. It is a question about what we are and what we can know. It is a question that we ask not because the universe requires us to ask it, but because we cannot help ourselves. We are the universe asking about itself, through the imperfect but remarkable instrument of human consciousness and human science. That the universe has produced beings capable of asking where it came from is itself one of the most remarkable things about it. Whether it has produced beings capable of answering that question remains to be seen. But the asking, rigorous and persistent and honest, is already a form of answer, because it shows that the universe is the kind of place that can produce beings who care about such things. And a universe that can produce such beings is a universe that is doing something very interesting with the matter and energy and laws that have been its content since whatever moment counts as its beginning. The Big Bang was not the beginning of the story. It was the beginning of the chapter we can read. The chapters before it, if there were any, are written in a script we are still learning to decipher. The chapters after it, which will unfold over timescales that dwarf the current age of the universe, are written in a future we cannot foresee. We live in the middle of the story, at a moment of unusual clarity and unusual capability, asking the oldest question in the newest language, and the asking goes on. The 7 theories we have explored in this journey are not the last 7 theories that will be proposed. They are the best 7 that current knowledge supports, and future knowledge will add to them, modify them, and perhaps replace some of them with better ones. The history of science suggests that the theories that eventually explain the origin of the universe will will be ones that we cannot currently imagine, just as the theories of quantum mechanics and general relativity could not have been imagined from the perspective of classical physics. The conceptual revolution that a complete understanding of cosmic origins will require may be as profound as any that has come before. What we can predict with some confidence is that the revolution, when it comes, will not make the universe smaller or simpler or more familiar. Every major advance in cosmology has made the universe larger, stranger, and more surprising than it was before. The Copernican revolution removed the Earth from the center of the solar system. The discovery of other galaxies removed the Milky Way from the center of the universe. The discovery of the cosmic microwave background revealed a history that extends far before any human experience. The discovery of dark matter and dark energy revealed that the matter we are made of is only a small fraction of the universe's content. The development of quantum mechanics revealed that the substrate of reality is stranger than anything classical intuition had prepared us for. The understanding of cosmic origins that is still to come will likely continue this tradition of expanding strangeness. The pre-Big Bang universe, whatever it is or was, will not turn out to be a simple extension of our familiar physics. It will be something genuinely new, requiring new mathematics and new concepts to describe. The question of what came before the Big Bang will eventually be answered, or transformed, in a way that makes the current state of confusion look like the natural prelude to a profound clarity. That clarity is what all the work described in this journey is aimed at. And while it has not arrived yet, the work is real, the progress is genuine, and the destination, however distant, is worth the effort. The universe began, or it emerged, or it always was, or it is a necessary mathematical structure. We do not yet know which of these is true, but we are learning, carefully and honestly and rigorously, with the best instruments and the best minds that human civilization has produced. And learning at this depth and at this scale is one of the most important things we can do. The question remains, the work continues, the cosmos awaits. The cosmos awaits, and we have been waiting with it, turning the origin question over in our hands like an artifact from an unknown civilization, examining every surface for marks that might tell us where it came from. We have followed 7 theories through their mathematics and their observational implications, through their philosophical assumptions and their honest limitations. Now, in this final section of the journey, we turn to what has not yet been fully said. Not new theories, but a deeper reckoning with the ones we have, a confrontation with what they collectively imply, and an honest account of what it means to live in a universe whose origin we do not understand. The central question one last time, not because it needs to be asked again, but because asking it again changes what we hear in it. Did anything exist before the Big Bang? And if time began there, what could before even mean? We have heard this question as a cosmological question about prior physical states. We have heard it as a quantum mechanical question about boundary conditions on the wave function of the universe. We have heard it as a question about the nature of time and whether it is fundamental or emergent. We have heard it as a mathematical question about which structures necessarily exist and why. And we have heard it as a philosophical question about the relationship between existence and explanation, between contingency and necessity, between the universe as we find it and the universe as it had to be. Now we hear it one more time, in a register that has been present throughout but has not been the focus. It is the register of what the question does to us, to the person asking it, to the civilization that produces people who ask it, and to the strange self-referential loop of a universe that generates beings capable of wondering about its own origin. This is not a detour into sentiment. It is a recognition that the origin question is not just about the universe. It is about what kind of universe produces questioners, and what that tells us about the universe's deepest nature. The universe is self-aware in at least one sense. It contains beings who are aware of it, who model it mathematically, who interrogate it observationally, and who ask questions about it that go all the way back to whatever preceded its earliest detectable state. This self-awareness is localized and limited. It exists in a thin layer of biological complexity on at least one planet, possibly on others we have not yet found, and it has existed for only a tiny fraction of the universe's history. But it exists, and its existence is a fact about the universe that is as real as the expansion rate or the temperature of the CMB. The fact that the universe is self-aware in this sense is not a trivial cosmological fact. It is connected to all the fine-tuning arguments we discussed in Chapter 3. The constants of nature that allow complexity, chemistry, and biology also allow consciousness and science. The universe is not just fine-tuned for stars and galaxies. It is fine-tuned for self-examination. Whether that fine-tuning is the result of selection in a multiverse, of mathematical necessity, of a quantum boundary condition, or of something else entirely, the fact of self-examination is part of the universe's story. It is the part of the story where the universe tells itself what it is, imperfectly and incompletely, and always with the knowledge that the telling is itself part of what needs to be explained. The origin question is therefore a moment of peculiar self-reference. The universe, through the instrument of human science, is asking where it came from. The answer, whatever it turns out to be, will be a piece of the universe understanding itself. And the understanding, when it comes, will change what the universe is, not physically but informationally, in the sense that the universe will then contain an accurate account of its own origin. That account does not change the physics. But it changes the meaning of the physics, and meaning is part of what the universe has become through the development of minds capable of caring about it. This self-referential quality of the origin question is not just philosophically interesting. It is connected to the deep questions about observers and quantum mechanics that have been implicit throughout. In quantum mechanics, the role of the observer is central and contested. The measurement problem, the question of how quantum superpositions resolve into definite outcomes, is one of the deepest unsolved problems in physics. Different interpretations of quantum mechanics give different answers to this problem, and the differences have implications for cosmology. In the Copenhagen interpretation, quantum states are defined relative to a classical measuring apparatus that exists outside the quantum system. This works fine for laboratory physics, but becomes problematic in quantum cosmology because the universe has no outside, no external classical measuring apparatus against which to define its quantum state. The Copenhagen interpretation in its original form cannot be consistently applied to the universe as a whole. The many worlds interpretation avoids this problem by denying that there is a collapse, treating the quantum state as universally real, and allowing all outcomes to be realized in different branches of the wave function. Applied to quantum cosmology, this means the universe's wave function branches at every quantum event, producing a vast superposition of different cosmic histories. Our history is one branch of that superposition, and asking what came before the Big Bang is asking about the structure of the wave function in the region of configuration space corresponding to the very early universe. Relational quantum mechanics, as we discussed, takes a different approach by making quantum states relative to observers rather than absolute. This resolves the measurement problem by denying that there is an observer-independent quantum state of the universe. Each observer has a valid description of the quantum state relative to themselves, and the consistency of physics arises from the consistency of these relational descriptions, not from any absolute underlying reality. Each of these interpretations has different implications for quantum cosmology and for the origin question. The many worlds interpretation implies that the Big Bang is a feature of our branch of the universal wave function, and that asking what came before is asking about the structure of the wave function in the pre-Big Bang region of configuration space. The relational interpretation implies that the origin question is inherently relational, asking about the quantum state of the early universe relative to some observer, and that without specifying the observer, the question is incomplete. These are not merely interpretational curiosities. They have different implications for what a satisfying answer to the origin question would look like. In the many worlds picture, a satisfying answer would be a complete specification of the universal wave function, and a demonstration that our branch of the wave function naturally contains a Big Bang of the type we observe. In the relational picture, a satisfying answer would be an account of how the relational quantum state of the early universe is consistent with what observers like us can observe, given the relational nature of all quantum descriptions. In the Copenhagen picture, applied carefully, a satisfying answer would be an account of the classical boundary conditions that define the quantum state of the early universe, accepting that those boundary conditions are external to the quantum system they define. The choice among these interpretations is not yet empirically constrained, because no observation has distinguished between them at the precision available. But the theoretical implications for quantum cosmology are significant, and advances in quantum gravity may eventually provide theoretical grounds for preferring one interpretation over others. The resolution of the measurement problem is one of the deepest open problems in physics, and its resolution will have direct implications for origin cosmology. The connection between quantum mechanics and the origin question runs even deeper through the concept of quantum information. Information is not just a human concept imposed on physics. It is a physical quantity with its own dynamics and its own conservation laws. In quantum mechanics, information is encoded in the quantum state, and unitary evolution preserves information. The black hole information paradox arises because black holes appear to destroy information by converting quantum states into thermal radiation, which violates unitarity. The resolution of the information paradox, which is still not fully settled, has implications for what happens to information in extreme gravitational regimes like those near the Big Bang singularity. If information is preserved through the Big Bang, as bounce models suggest, then the quantum state of the universe before the Big Bang is encoded in the quantum state after it, and in principle recoverable. If information is lost through the Big Bang, then the pre-Big Bang state is genuinely unknowable, not just in practice but in principle. The question of whether information is preserved through the Big Bang is therefore a question about the fundamental nature of quantum gravity, and its answer will determine whether the origin question has an answer within physics or whether it exceeds what physics can address. The holographic principle, in its strongest form, implies that information is preserved even in extreme gravitational regimes. If all the information in a region can be encoded on its boundary, then the information cannot be lost, because the boundary description is unitary. Applied to the Big Bang, this suggests that the information about the pre-Big Bang state is encoded on the cosmological horizon, and that in principle, if not in practice, that information could be recovered. The origin question would then have a definite answer in principle, encoded in the quantum state of the cosmological horizon, even if extracting that information is practically impossible. This is a hopeful picture from the standpoint of the origin question, because it suggests that the universe's origin is not lost behind an impenetrable barrier, but is encoded in the universe's current quantum state, waiting to be read by instruments and theories sophisticated enough to read it. The development of such instruments and theories is the long-term goal of origin cosmology, and the holographic principle suggests that the goal is achievable, at least in principle. The practical barriers to achieving it are enormous. The cosmological horizon is not a surface we can access. It is a causal boundary defined by the speed of light and the expansion of the universe. The information encoded on it is inaccessible to direct observation. Extracting it would require a level of theoretical understanding of quantum gravity and holography far beyond what we currently possess. But the existence of a principle that guarantees the information is there, in principle encoded and in principle recoverable, is itself meaningful for the direction of the research program. It tells us that the origin question has a definite answer, even if we do not yet know how to find it. The swampland program in string theory is connected to this information-theoretic perspective in a specific way. The de Sitter conjecture, which suggests that stable de Sitter vacua may not exist in quantum gravity, has implications for information preservation in de Sitter space. De Sitter space has a cosmological horizon, and if de Sitter space is unstable, then information about the interior of the horizon is not permanently isolated from the exterior. The instability of de Sitter space could provide a mechanism by which information about the pre-inflationary state is not permanently lost, because the inflationary de Sitter phase eventually decays and the information encoded in its quantum state is released into the post-inflationary universe. This connection between the swampland, de Sitter instability, and information preservation is speculative and not yet worked out in detail. But it illustrates how the different strands of quantum gravity research, string theory, holography, the swampland, and quantum information are becoming increasingly interconnected. The origin question sits at the intersection of all these strands, and progress on any one of them has implications for the others. The development of a unified framework that brings all these strands together may be what is needed to make decisive progress on the origin question, and there are signs that such a unification is beginning to emerge, tentatively and incompletely, in the current theoretical landscape. The timeline of this development is impossible to predict. Major theoretical advances in physics do not follow a schedule. General relativity took Einstein a decade to develop and was not understood or accepted immediately. Quantum mechanics took a generation of physicists and multiple rounds of conceptual struggle to reach its current form. String theory has been developing for 50 years and has not yet produced unambiguous experimental predictions. The theory of quantum gravity that will ultimately address the origin question may take as long or longer to develop, and its development may require conceptual innovations as profound as any that have come before. In the meantime, the work goes on. Observations accumulate, theories are refined, and the conversation between physics and philosophy deepens. Each step in the work is meaningful in itself, not just as a step toward the eventual answer, but as an expression of the human capacity for rigorous inquiry into the deepest questions. The process of science is not just a means to an end. It is itself a human achievement, a collective intellectual practice that represents one of the most remarkable things that has emerged from the universe's 14 billion years of evolution. The universe that produced beings capable of asking where it came from is a remarkable universe. The beings who ask the question, imperfect and limited and confused as they are a remarkable product of that universe's history. And the question itself, which has resisted complete resolution for as long as humans have been capable of asking it, is a remarkable question. The resistance is not a failure. It is evidence of the question's depth. The deepest questions are the ones that outlast the best attempts to answer them, and in outlasting those attempts, they drive the development of new tools, new concepts, and new understanding that would not have been reached without the question. The origin question has driven the development of general relativity and quantum mechanics, of inflationary cosmology and quantum gravity, of holography and quantum information theory, of the philosophy of time and the analysis of physical necessity. It has been one of the most productive questions in the history of human thought, generating more genuine understanding than it has resolved, leaving the inquirer always on the edge of the next insight rather than settled in the comfort of complete understanding. That is the character of the best questions, and it is the character of the question of what came before the Big Bang. Let us turn now to the specific implications of each of the 7 theories for our understanding of the very long-term future of the universe, because the origin and the future are connected in ways that are often overlooked. How the universe began determines, through the laws of physics, how it will end, and how it will end may determine whether another beginning is possible. The connection between origin and terminus is one of the most important and least discussed aspects of origin cosmology. In the standard cosmological model with a positive cosmological constant, the universe will continue to expand indefinitely. Accelerated expansion driven by dark energy will eventually cause all galaxies outside our local group to recede beyond our horizon, becoming permanently inaccessible. Stars will exhaust their fuel over trillions of years, leaving white dwarfs, neutron stars, and black holes. Black holes will eventually evaporate through Hawking radiation over astronomical timescales, leaving only a diffuse sea of particles and radiation in an ever-expanding, ever-cooling universe. The final state is sometimes called the heat death of the universe, though it is more accurately described as a cold death, a state of maximum entropy and minimum temperature in which no further work can be done and no further complexity can develop. This future is not certain because the nature of dark energy is not certain. Dark energy with a constant equation of state, the cosmological constant, leads to eternal accelerated expansion. Dark energy with an equation of state that changes with time could lead to different futures. If dark energy becomes less repulsive over time, the expansion could slow and eventually reverse into a big crunch. If dark energy becomes more repulsive over time, it could lead to a big rip in which even atoms, and eventually protons and neutrons, are torn apart by the accelerating expansion. The current observational data is consistent with a cosmological constant, but does not rule out time-varying dark energy, and future surveys will constrain this more tightly. For cyclic cosmologies, the long-term future is connected directly to the origin because the future collapse or conformal transition is what enables the next cycle. In the ekpyrotic picture, the slow approach of branes after a long expansion phase prepares the conditions for the next collision. In conformal cyclic cosmology, the cold, radiation-dominated far future is what conformally maps onto the next Big Bang. In loop quantum cosmology bounce models, a future recollapse, if it occurs, would bounce into a new expanding phase. The future of the universe in these models is not a final end, but a preparation for another beginning, making the origin and the terminus not opposites but aspects of a continuing process. The entropy problem for cyclic models is most sharply visible in this long-term context. If the universe undergoes cycles, each cycle must begin with a lower entropy than the previous cycle ended, or the cycles must be structured so that entropy does not accumulate in a way that prevents future cycles. The current universe has a very low entropy compared to its maximum possible entropy, and that low entropy is what allows the complexity and structure we observe. If future cycles inherit entropy from previous cycles, the entropy will accumulate over time, making future cycles less and less hospitable to complexity. The mechanisms for managing this entropy accumulation are central to the viability of cyclic models, and they are connected to the mechanism that set the low entropy initial conditions of our current cycle. For multiverse models, the long-term future is less clearly defined because different bubbles in the multiverse will have different long-term futures depending on their vacuum energy and their laws of physics. Our bubble will have whatever future its cosmological constant determines, and other bubbles will have different futures. The multiverse as a whole may never have a final state because new bubbles are always being created in the inflating background, so the multiverse's future is an eternal continuation of its present state of bubble production and bubble evolution. For quantum creation models, the long-term future is determined by the laws encoded in the boundary condition that created the universe. If the no-boundary wave function selects a universe with our specific cosmological constant, then the long-term future of our universe is the cold death described above. Whether the no-boundary wave function predicts exactly our cosmological constant, or whether it predicts a distribution over cosmological constants with our value being one possibility, is a question about the details of the proposal that has not been fully resolved. For emergent time cosmologies, the long-term future has a different kind of significance. If time is emergent from quantum correlations, then the question of what happens when the universe reaches its maximum entropy state is a question about what happens to the quantum correlations that define time. In a maximum entropy state, the correlations that support the emergence of classical time may break down, and the universe may transition to a state in which time is no longer a well-defined concept. This would not be an ending in the temporal sense because there would be no time to end in. It would be a dissolution of the framework that supports temporal concepts, including the concept of beginning and ending. This connects to the question of whether the universe's final state is analogous in any way to its initial state. In conformal cyclic cosmology, the analogy is explicit and mathematical, with the final radiation-dominated state mapping conformally to a new initial state. In other approaches, the analogy is less explicit but still present as a conceptual echo. The universe begins in a state of very low entropy and high order. It ends, in many models, in a state of maximum entropy and minimum order. These are the two extremes of the thermodynamic range, and the universe's history is the trajectory from one to the other. Whether that trajectory is linear, cyclic, or something more complex depends on the origin theory. The arrow of time, as we discussed in Chapter 5, is determined by the low entropy initial state. The fact that entropy increases, that time has a direction, that the past is different from the future, all of these features of our temporal experience are consequences of the Big Bang beginning in a state of very low entropy. If the universe had begun in a maximum entropy state, time would have no preferred direction, and experience as we know it would be impossible. The low entropy beginning is therefore not just a cosmological fact. It is the source of the temporal structure that makes experience possible. Understanding why the universe began in such a low entropy state is therefore not just an origin question. It is a question about the preconditions for experience itself. The fine-tuning of the initial entropy is as important for the existence of observers as the fine-tuning of the constants of nature, and any complete origin theory must explain both. The Penrose-Hawking singularity theorems show that the initial singularity is generic in classical general relativity, but they do not explain why the singularity was approached from a low entropy direction rather than a high entropy direction, which is statistically the overwhelmingly more likely case. The explanation must come from quantum gravity or from some principle that selects the low entropy initial state preferentially. The no-boundary proposal is one attempt to provide such a principle. If the wave function of the universe is peaked on smooth, regular geometries, and if smooth, regular geometries correspond to low entropy initial states, then the no-boundary boundary condition might explain the low entropy beginning. But there are technical questions about whether the no-boundary wave function actually selects low entropy over high entropy initial conditions, and recent analyses have raised doubts about the standard interpretation. The question remains open. The connection between the origin of the universe and the arrow of time is one of the deepest and most important themes in origin cosmology, and it connects the very early universe to all of human experience. Our ability to remember the past and not the future, to feel causes before effects, to experience time as flowing in a definite direction, all of these are consequences of the low entropy initial state. If we understood why the universe began with such low entropy, we would understand something deep about the structure of time itself and about why we experience it as we do. This is not an abstract philosophical point. It is connected to the physics of the very early universe in a direct way. The initial conditions of the universe, set by whatever process the origin theories describe, determine the direction and magnitude of the entropy gradient that drives the arrow of time. A different initial condition would produce a different arrow of time, or no arrow of time at all. Understanding the origin is understanding the source of the temporal asymmetry that makes experience possible, and that connection elevates the origin question from a cosmological curiosity to a question about the foundations of existence itself. The tools of modern cosmology extend further than telescopes and detectors. They include the mathematics of general relativity and quantum mechanics, the computational tools of numerical simulation, the statistical tools of Bayesian inference and hypothesis testing, and the conceptual tools of philosophy and the history of science. All of these tools are being applied to the origin question, and all of them are producing insights that advance our understanding, even when they do not produce definitive answers. Bayesian inference is particularly important for origin cosmology because it provides a rigorous framework for updating beliefs in the light of evidence. In the Bayesian framework, we start with a prior probability distribution over possible theories and update it using the likelihood of the observed data given each theory. The result is a posterior probability distribution that reflects our updated beliefs after incorporating the evidence. This framework is especially useful in origin cosmology because many of the theories are difficult to test directly, and the evidence for or against them is often indirect and ambiguous. Applying Bayesian inference to origin theories requires specifying priors over the space of theories, which is itself a difficult and controversial step. The choice of prior reflects assumptions about which theories are a priori more or less plausible, and different choices of prior can lead to different conclusions even with the same data. This is not a defect of Bayesian inference. It is an honest acknowledgement that our evidence is always interpreted through a framework of prior beliefs, and that making those beliefs explicit allows them to be examined and challenged. For origin cosmology, the relevant priors include beliefs about the likelihood of inflation occurring, the probability distribution over inflationary models, the likelihood of a pre-inflationary phase, the probability of different quantum gravity effects, and the priori plausibility of the various explanatory frameworks we have discussed. Physicists disagree about these priors, and that disagreement is a large part of why there is genuine scientific debate about which origin theory is most plausible. Making the priors explicit through Bayesian analysis, at least, allows the disagreements to be identified and discussed rather than hidden in vague appeals to simplicity or naturalness. The concept of naturalness, which has been influential in particle physics, is connected to the Bayesian framework through the idea of fine-tuning. A theory is said to be unnatural if its parameters require fine-tuning to very specific values to reproduce the observed physics. Fine-tuning is often quantified by the sensitivity of observational predictions to small changes in the parameters, and highly sensitive theories are considered unnatural because they seem to require special coincidences. The cosmological constant problem is the most severe naturalness problem in physics because the observed value of the cosmological constant is 120 orders of magnitude smaller than the naive field theory estimate, which represents an extreme fine-tuning. The multiverse and anthropic reasoning can be seen as a Bayesian response to fine-tuning problems. If the prior over the cosmological constant is set by the distribution of values across the multiverse, and if the anthropic constraint restricts attention to values compatible with observers, then the posterior distribution of the cosmological constant given our existence is concentrated in a range much smaller than the full prior, potentially making the observed value not particularly special within the restricted range. This reframes the fine-tuning from a coincidence to be explained to a selection effect to be accepted. Whether this Bayesian reframing is scientifically satisfying is a matter of ongoing debate. Critics argue that without a definite measure over the multiverse, the prior is undefined and the Bayesian framework cannot be consistently applied. Proponents argue that the framework is at least conceptually valid and that the measure problem is a technical issue to be resolved rather than a fundamental objection. The debate reflects the deeper tension between the desire for a unique theoretical explanation of the constants and the pragmatic acceptance of environmental selection in a large multiverse. The model selection aspect of Bayesian inference is also relevant for comparing origin theories. Given the available data, which theory is most strongly supported? Bayesian model selection uses the ratio of the marginal likelihoods of the data under different theories, which automatically penalizes theories with more free parameters through the Occam factor. Theories that fit the data well with fewer parameters are preferred over theories that fit equally well but with more parameters. This is the quantitative expression of Occam's razor, and it provides a principled way of comparing theories with different levels of complexity. Applying this to origin theories, inflation with a simple inflaton potential fits the current CMB data well with a small number of parameters and would be strongly supported over alternatives that require many more parameters to fit the same data. But if a distinctive prediction of inflation, like a specific amplitude of primordial gravitational waves, is not detected by future experiments, the model selection calculation would shift toward alternatives that naturally predict smaller tensor amplitudes. The future of origin cosmology is therefore in part a Bayesian story of how the evidence will update our model preferences as new data arrive. The interplay between model selection and prior beliefs is particularly important for the most speculative theories in our list: the mathematical universe hypothesis, necessary existence, and the various quantum gravity approaches. These theories are difficult to connect to specific observational predictions, which means they are difficult to update through Bayesian model selection in the usual sense. They are more like frameworks within which more specific models can be formulated than like models themselves, and evaluating them requires a different kind of assessment than the standard Bayesian approach. One way to evaluate framework-level theories is through their track record of generating successful specific models. A framework that has consistently generated models that fit the data is more credible than one that has not, even if the framework itself does not make specific predictions. Inflation is a framework in this sense, and its track record of generating models that fit the CMB data is one of the strongest arguments for taking it seriously. Loop quantum gravity and string theory are also frameworks, with mixed track records of generating successful models in different domains. The track record of a framework is a form of evidence, even if it is not the same as a direct observational test of the framework. The history of science also provides a form of evidence about which kinds of frameworks tend to be productive and which tend to be sterile. Frameworks that have internal mathematical consistency, that connect to established physics in appropriate limits, and that generate novel predictions that are subsequently confirmed have historically been more productive than frameworks that are internally consistent but do not connect to established physics or generate novel predictions. This historical track record is a prior on the kinds of frameworks that are worth pursuing, and it shapes how physicists allocate their research effort. The origin question benefits from this historical perspective because it reminds us that the most important advances in our understanding of origins have come from frameworks that, at the time they were proposed, seemed speculative but had internal mathematical consistency and connected to established physics in appropriate limits. General relativity was speculative in 1905 and was later confirmed by the observation of light bending around the sun. Quantum mechanics was speculative in the 1920s and was later confirmed by countless experiments. Inflation was speculative in 1980 and has been progressively confirmed by CMB observations since then. The frameworks we're currently developing for understanding cosmic origins, loop quantum gravity, string theory, holography, emergent time, may be at a similar stage of development. They have internal mathematical consistency, and they connect to established physics in appropriate limits. They have generated some confirmed predictions, particularly in the context of the holographic principle and the anti-de Sitter conformal field theory correspondence. And they continue to develop in ways that produce new insights and new predictions. The historical track record of similarly situated frameworks in the past suggests that continued investment in these approaches is likely to be productive. None of this guarantees that any of the current frameworks will ultimately explain the origin of the universe. The history of science also includes frameworks that seemed internally consistent and productive, but were eventually superseded by better ones. The ether was a productive framework for 19th century physics that was eventually replaced by special relativity. The S-matrix bootstrap program of the 1960s was a productive framework that was eventually replaced by quantum chromodynamics for strong interactions. The current frameworks for quantum gravity may similarly be superseded by a better framework that we cannot currently envision. But the best strategy in the face of this uncertainty is to pursue the most promising current frameworks rigorously while remaining alert to the possibility that they need to be replaced. The rigor is what allows us to identify the failure modes of the current frameworks when they become apparent, and the alertness is what allows us to recognize when a genuinely better framework has been proposed. This combination of rigor and openness is the scientific temperament that origin cosmology requires, and it is the temperament that the best practitioners of the field consistently exhibit. The universe does not make the origin question easy. It has arranged its earliest epochs in such a way that direct observation is impossible, having erased or hidden most of the information about what came before the hot Big Bang phase. It has arranged its laws in such a way that the regime near the Big Bang singularity is precisely where our best theories break down. And it has arranged its complexity in such a way that understanding it requires a synthesis of physics, mathematics, and philosophy that no individual can fully master. The universe, in a sense, has made the origin question as hard as any question can be while still being a question worth asking. And yet we ask it, rigorously and persistently, with every tool we have. We ask it because we cannot help asking it. We ask it because asking it has produced the most important intellectual advances in cosmology. We ask it because the answer, whatever it turns out to be, will tell us something profound about the nature of time, existence, and the universe we inhabit. And we ask it because we are the universe asking about itself, and the asking is part of what the universe has become. In the beginning was the question, not the answer, not the beginning, but the question. The question of where everything came from, of what was there before the first thing, of whether before even makes sense when applied to the first thing. The question is as old as human consciousness, older than writing, older than science, woven into every attempt the human mind has made to understand its situation. Modern cosmology has transformed the question without dissolving it. We know now that the universe is approximately 14 billion years old, in the sense that the scale factor of our best models goes to zero at a time about 14 billion years ago, according to our clocks. We know that the universe was once hot and dense enough to fuse hydrogen into helium, and that the helium we observe matches what the fusion should have produced. We know that the universe was once opaque, and that the light released when it became transparent is the cosmic microwave background we detect today. We know that small density fluctuations in the early universe seeded the large-scale structure of galaxies and voids that we map today. We know all of this with remarkable precision and remarkable confidence, and the knowing is one of the greatest achievements of human civilization. But we do not know what came before the hot, dense phase. We do not know whether the classical singularity at t=0 represents a genuine first moment or a breakdown of our description. We do not know whether inflation occurred before the hot phase, and if so, what preceded inflation. We do not know whether the universe had a quantum origin from a state with no classical spacetime, or whether it is connected to a prior cycle of cosmic history, or whether it is one of infinitely many bubble universes in an eternally inflating background, or whether it emerged from a brane collision in a higher dimensional spacetime, or whether time itself is emergent from a more fundamental timeless description. We do not know whether the universe is a mathematical structure that necessarily exists or a contingent physical system that required some specific mechanism to come into being. Not knowing these things is not a comfortable position, but it is an honest one. The history of science shows that honest acknowledgement of ignorance is the most productive stance for a scientist to take, because it directs attention toward the genuine questions and away from the false security of premature conclusions. The questions we do not know the answers to are the questions that drive the field forward, the questions that motivate the next generation of experiments and the next generation of theories. The students studying cosmology today will be the scientists who develop those theories and design those experiments. They will inherit the 7 frameworks we have discussed and will push them further, test them harder, and perhaps replace some of them with better ones. They will develop new mathematical tools for quantum gravity, new observational techniques for probing the primordial universe, and new conceptual frameworks for thinking about time, causality, and existence. They will ask the origin question in ways that we cannot currently imagine, and some of them will find answers that change what the question means for everyone who comes after them. The origin question is a gift that each generation of scientists passes to the next. Not a solved problem, but a live one, not a settled conclusion, but a productive tension between what we know and what we do not know. The tension is what drives the science, and the science is what drives the understanding. And the understanding, when it comes, will not be the end of the question, but its transformation into a better question, deeper and more precise and more productive than the one we currently ask. The universe is older than its oldest light, or it began with that light, or it began before that light in a phase we cannot directly observe, or it did not begin at all in any sense that makes the concept of beginning applicable. We do not yet know which of these is true. But we know how to ask the question more precisely than any previous generation, and we have more tools for approaching an answer than any previous generation, and we live in a moment when the question is more alive and more productive than it has ever been. That is where we are. On the edge of what can be known, with the tools of a civilization that has spent centuries learning to ask questions carefully and to pursue answers rigorously, facing a question that has resisted every previous attempt to resolve it, but that has, in resisting, driven the development of general relativity, quantum mechanics, inflationary cosmology, quantum gravity, holography, and the philosophy of time. The resistance has been productive. The question has been worth asking. And the asking will continue. The Big Bang was not a simple beginning. It was the beginning of the story we can tell with confidence, and the beginning of the question that is still driving us. Whatever came before it, if anything did, is the next chapter of the story, the chapter we are still learning to read, using instruments we are still building, guided by theories we are still developing, constrained by evidence we are still gathering. The work continues, the cosmos awaits, and the question, persistent and deep and endlessly productive, remains. What came before the Big Bang? We are still finding out. There is one final thing to say, and it is the simplest thing of all. The universe exists. Whatever its origin, whatever preceded it or did not precede it, whatever quantum state it nucleated from or bounced out of or has always been, it exists. The galaxies are real. The stars are real. The atoms that make up everything we can touch are real. The light that has traveled for billions of years to reach our telescopes is real. The cosmic microwave background is real. The history of 14 billion years of expansion and cooling and structure formation is real. And we, who ask questions about this reality, are also real, part of the universe, made of the same matter that was forged in the first minutes and in the hearts of stars, carrying in our bodies the record of the universe's history in the ratio of our atoms. Whatever came before the Big Bang, it produced a universe capable of this, capable of self-examination, capable of science, capable of reaching back toward its own origin with the tools of mathematics and observation and reason. That capability is the most remarkable thing about the universe we know, more remarkable than its size, more remarkable than its age, more remarkable than the precision of its laws. The universe has produced minds that ask where it came from, and that asking is itself the most cosmic thing that has happened since the Big Bang, because it is the universe turning its attention to itself. The question will not be answered today. It may not be answered in this century. But it will be pursued, rigorously and honestly, by the community of scientists and philosophers who have dedicated their intellectual lives to understanding where everything came from. And the pursuit, whether or not it reaches its destination, is one of the most important and most distinctively human things that our species has ever done. The cosmos began, or it did not. Before means something, or it does not. The question is answerable, or it is the wrong question, or it is a question that will generate better questions. We do not know which of these is true. But we know that asking the question well is worth everything we can bring to it, and we know that the universe, whatever its origin, has given us the capacity to bring a great deal. That is enough. That is, in fact, remarkable.